DKIM fall up under. It's called Domain-Based Message Authentication Reporting and Conformance. I couldn't even remember that. But anyway, we're just going to repeat it until we get a little bit of it, okay? Domain key, everybody with me? Domain-based message authentication, reporting, and configure. Yeah, that thing, okay? That deals with securing email, looking for spammo. Kevin, you got me with the with that thing, D-Mark. I'll tell you, it gets you. So you try to look for embedded links, or you should have your email analysis tool look for those links that look suspicious and or fines. Okay. What can I have in place? Y'all know me, I'm about to be really sneaky. A lot of email can be looked at or signed into via an application. So, I want to monitor all application stuff leaving an organization. What should I implement?
For that reason, we may want to use a non-terrestrial form of connectivity known as satellite network.
Even something simpler than a network tap.
Satellite dish to
Dang it, Olivia.
and begin sending and receiving data from the satellite.
She's the first one to get
This
it.
obviously adds additional cost,
Application-based firewall.
and the speeds of satellite networking, although
Because a portal, when I click on it, it's web-based. It's going somewhere. An application-based firewall can now look at packets. It can give me telemetry about protocols being used, originating address, destination address, all this stuff in between, right? Yes. So that'd be the easiest thing to implement. Now inside your proxy firewalls, you can, inside of there, can give you an application tool, layer tool, to do it as well. All right, here we go. Then with file analysis, now we're looking at
another challenge with satellite networking is that it
hashing.
line of sight to the satellite that's in orbit above the Earth.
Can somebody tell me what a hash is? It's crypto, right?
Satellite receiver and the satellite, then we may have
Word up is crypto. I know it's crypto. Hashing is crypto. Dang it.
For example, if a thunderstorm was to come through, we would suffer through what we call rain fade.
Told my wife the other day, y'all too smart for y'all britches. Listen, you're correct. It's integrity. Integrity of the file, y'all got it. It is not crypto. Please don't pick that. It's an easy way to get tripped up. Now, can I add crypto? Some form of cryptography, right?
Yeah, as an addition.
What's the easiest crypto I can implement on my computer right now? The easiest. Bitcoin. Oh, wrong answer. There you go, Mr. T. I got what you were saying, Aaliyah. Okay, so listen. You were thinking BitLocker. There you go. Wait a minute. Let's back up a minute. I think Charles jumped the gun on that one. Now I'm realizing what's happening. The telemetry's coming in. Did y'all see his answer? He said Bitcoin.
Yeah.
That's Mike's like,
to connect any device in the world to any Ethernet network and be able to have this connectivity.
oh my God, that's funny. All right, so Leo, all y'all.
Those standards are created
Give
by
me
the
that.
IEEE 802.3.
But y'all got the gist of it. So BitLocker's the easiest thing to implement. What do I implement if I want a hard drive to go from Jesus' computer that he uses at work to his home computer
For example, a very
somewhere
common
else?
Ethernet network would be 1000 base T.
Remember I said key thing I said was hard drive.
That operates over
I want his hard drive to be secure at his work computer and connected to another computer that's
The
authorized.
newer version of that standard is the 10G base T or the 10 gigabit Ethernet.
I got y'all on
This also
finally.
uses twisted pair
No
copper cabling and
leak.
operates at a speed of 10 gigabits per second.
It's the same hard drive I needed to work on at work. It's
Okay,
all
so it
encrypted
should be
because you got
ICS.
BitLocker.
Which is a gigabit Ethernet network.
I see what y'all doing. Y'all bait me to give you more information. I'm not doing it.
1 gigabit per second. This is just a
Mouth
sample
is
of
shut.
a few of the more
not
popular
TPM.
Ethernet standards
Jesus, the TPM has a lot to do with it.
supporting different speeds.
I want to use this
The
hard
IEEE
drive
has told us that the names they
on a
use
work
for the
computer
standards don't necessarily
and another
relate back to
authorized
the details
home
of the
computer.
standard.
Same
But
hard
there's
drive.
usually some information that we can
It is
discern
data loss
from the name
prevention.
itself.
It is an
example, if we look
implementation
at a
of data
standard
loss.
such as 1000 base
Come on,
T,
Jesus,
we
give me
should
some
be
more.
able to break that term
BitLocker.
apart and determine what type of media and technology
BitLocker. Two more words.
For example, the number that's used in the name of the standard is often related to the speed of the standard itself. For example, the 1000 base T,
That's encryption
that
files.
1000 refers to the 1000
Martin got it.
megabits per second.
BitLocker
BitLocker.
2 go.
Per second overall speed. If the
BTG.
standard started with 10G, then it would be related to a
All right, you
10
can set that up.
megabit per second
All right.
network. We often see the term base in the name of the standard, and that's referring to the term baseband.
Can somebody tell, can somebody type in the chat,
send this data over the network. This
what is
in
a
contrast to
traversal
something
attack
like
look like?
broadband, which uses many different frequencies to be able to communicate across
Show me the
that
commands.
network. And very often you can determine what
Bingo.
type of media
Dang,
is
Leader,
associated with that
are your
standard
keys
by
still
looking
on
at
fire?
additional letters
Golly,
of the standard.
smoke.
For
Hold on,
example,
smoke coming out my
1000 base T has a T at the end,
Golly.
and we can
I didn't even get the last
T means
verb
that
out.
this is twisted pair copper. If there was an F at the end, it's very
Need a
possible
fire
that this
extinguisher.
particular standard would use
Her stuff
fiber
moving in
optics.
nanoseconds.
There may be
Listen.
additional letters at the
All
end
right.
of the standard. For example, if there's an SX at
Might
the end
need,
of the standard,
Mr. T
it
says, might need to get a
refer
fire
to a short
extinguisher.
wavelength light that is sent over that fiber optic
All right.
connection.
She was quick, I had to recognize. I know it's the AI Aaliyah. That's not the real Aaliyah. That's AI Aaliyah.
So that it would be
She's got a script running.
That is not a requirement
Right?
of the name
All right.
of the standard itself. If you were interested in the details of what that standard
T2000
supports, you
Aaliyah.
would need to read the
Aaliyah
entire
Intelligence.
standard,
Oh, I
not
like
just look
that.
at
That's
the
her
name
name.
of the standard.
I like that nickname, Aaliyah Intelligence. All right, her AI. All right, patent that. All right, let's keep it moving. Good stuff, though. All right, let's look at some programming languages.
Many of us are accustomed
Here we go.
to using twisted pair
I know y'all know
copies,
JSON,
especially
JSON,
when use at home or
X-
even in our
XML.
office. But you may occasionally have a need for
Please
fiber
tell
optic
me
connectivity.
the file
Fiber
extensions
optic
for,
connectivity allows
type
us to
in
send
the file
traffic
extension for
across the
JS.
network using light.
Okay, Charles put PowerShell. Okay, we'll start there. PowerShell is PS1.
Difficult to tap into a fiber optic connection without having some type of notification. This is very
He's
different
Aaliyah
from
Intelligence
fiber-based
version
networks.
2.0. Okay, here we go.
It is relatively
Quick on
easy
the draw.
to tap and gain information.
J.
Fiber optics are also used over very long distances because
All right, so that's what's the one for shell scripting?
So the same signal that we can send over 100 meters of a copper network
You
might
got
be
it.
able to be sent over kilometers if you were using
All right, moving
fiber
on.
optics. And of course, light
Let's talk
is
threat
not
actors,
susceptible
1
to
4.
any type of radio
So we have
frequency
advanced persistent threats.
interference. And if
Usually
you're working
advanced
in an environment
persistent
where
threats
there
will
is
come from
interference,
organizations
you might
like
wanna use fiber
nation
optics to avoid
states.
any type of problem with your network.
If we were to assimilate or match. Okay. Y'all said it before when we first started to review APTs. You have created some way to stay in that system, even through updates, through patches, through backdoors, as Charles said. For whatever reason, you're still in there, and you're still attacking, and they ain't figured it out yet. Okay, that's an advanced persistent threat. All right, living the dream, yo. So hacktivists, okay, they are a threat. But hacktivists do what? They go after what? As a reminder, I mean a hacktivist. What would they make? What might they do?
Is a low reflective cladding, and the entire fiber optic run is protected.
Yeah, they want the
with a
cause
buffer
now.
coating around the
So they might
outside.
deface a website or
Here's the
something like
connector
that.
that's
Do they do it
embedded
for
in
money?
the fiber optic cable. It has a protective
Yeah.
ferrule around
Yeah, it's
the
all
outside of the fiber. If you look very closely
yeah, that
at the
word
very
burn.
middle of this connection, you can just barely make out the core
Mr.
of the
Cool over
fiber
there. I know he got another cup of coffee.
highlighted here.
Anybody
So
ordered
you can
Martine's
see where that
cafe
happens.
coffee yet?
Let's
Not yet?
Martine's
Okay.
coffee.
Now you can
So,
start to see that
then you have the
distribution
organized crime mode,
is connected on
the
inside of
OCs.
cable.
What's their
We
motivation?
install one of two different types of fiber optic cables. One is
Heck yeah, the
multi-mode fiber,
dollar
and the
bill,
other is
y'all.
single-mode fiber.
Script kitties.
Multi-mode fiber is commonly used for relatively short-range communication. This would be up to around 2 kilometers
Yep,
in
noobs.
distance. And often this uses an
We already know the insider threat. I'm not insulting your intelligence on that. But what's the third party? What's the supply chain?
The fiber optic is relatively large.
Amateur hackers, yep.
Larger than the wavelength of the light, and because of
MSPs,
the light itself,
you can get it.
use different
I'm
modes
glad you
to
said
be
that,
able
Mr.
to
T.
transmit through that fiber, and you can see the different
MSPs
modes
provide services for other companies,
because there are different modes
right?
that are being
My buddy
used
had
through this
issue with the
fiber.
yes, there you go. I'm glad he brought it up because the third party supply chain today are the actual third party infrastructure companies that provide services to other cloud companies. That's why when he said MSP, I'm like, today's IT, that's the threat. That's the third party. Because they're using CASB and containerization and virtualization and blah, 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 CrowdStrike, and everything's connected. Cloudflare, AWS, right? Those are the third party that they're hiring. So for the Walmart chain, they're no longer trying to get in through the thermostat light bulb that's in the closet, right? They're trying to get in through the MSP and find a way to get through there.
Cabling is the foundation.
So they all have some identical TTPs, tactics, techniques, and procedures. What is the direct reflection of TTPs?
Once the cabling is installed,
What framework?
it's very difficult to uninstall or
MITRE.
remove that cable and replace it with something
Charles,
else.
both of
So
y'all.
make
Look at
sure
Charles.
you're using the right cable
All right.
for the right
So
infrastructure.
now you have to use what they call confidence levels to really make sure what you're getting is up to par. So timeliness, relevancy, and accuracy. How fast how old is, let's put it this way. How old is the information? Let's put it, that's timeliness, right? How old? Is it something that just hit the street yesterday? Or is it something after 9 months somebody dug up on the team? Hey Charles, can you take a look at this? This directly affects us. He's like, this article is like 9 months old. Like, is it, okay, we'll take a look at it. Relevancy. If you're in automotive and the post or the threats for banking, right? Does it really have something to do with you? Maybe not. And then the accuracy of the information. Is it hearsay? Does it come from a white page? Is it through a published journal? Or is this stuff you're hearing out on the internet? On the dark web, which I think sometimes the dark web is reliable information. That's ground zero for a lot of stuff that's about to happen. So you got to have threat hunters and see what's going on. So that could be it.
Another interesting part is that
next, you look at your collection methods. Use all of these things to collect.
At an individual cable, you'll notice that some pairs of cables
Social,
are twisted
government,
much tighter than other pairs.
And I just said it right there.
One
The
common
dark web.
I often hear about cables is that
A lot of threat hunting teams are sitting on the dark web.
But in reality, the
But you have closed source, paid
Copper is
feeds.
literally
People are
just
sharing
a
information.
single
You're paying for this
cable.
information that's vetted and verified. It's coming directly to your organization. Of course, open up your mouth and share it to other people. Like, hey, that's where you go to conferences, stuff like that. Talk to other colleagues, and then some internal sources. Yep, coffee shop, at the coffee shop. What? Just a rumor is good to have fun for 0 day coffee shop.
What type of cable you should be using for the type of
Person with the pineapple sitting in the corner could be Kevin.
2.3 standards. Those
Right.
standards will specify the minimum cable type that's allowed.
And then with all the threat intelligence sharing, here you go.
Signal and the total throughput expected.
Now for threat
to
hunting,
be able to easily determine
you're looking for
the type of cable
IOCs.
that's appropriate for a specific Ethernet standard.
Focus on these
We create a
areas,
set of
which is,
standards for
to
the
me,
cables
if you
themselves.
ask me,
We refer to these
this is
standards as a
constant through
category of
all
cable. For
security.
example, you might find category
Period.
5,
All it
category
is.
6, or category 7. If you check the Ethernet standard, it will specify the
What's the first thing you should have on a running network?
that is required for that particular standard.
I mean, with
For
every,
example,
there you go,
using
baseline.
1000 base T,
How many times do you update a
1000
baseline?
base T standards from the IEEE, and it will tell you that the minimum cable category for that specific Ethernet standard is a category 5 cable. If you install category 5 cable or anything above category 5, it will work properly
Quarterly,
with the
every day.
1000 base T standard. Although twisted pair wiring is very common for our local area networks,
After
another
attack.
type of Ethernet cable that's very often
Then you might get this
is a
one today.
coaxial cable.
Actually,
This describes a cable where two
there
or
is
more
no
ports
time.
within that cable share a common axis. For example, you can see the.
That's why all of your answers are right.
In the middle of this coaxial.
You should at least have a minimum base. You're right. It was a trick question. It all depends on your architecture for your organization, the information you're holding. How is your now I will agree. The only thing that is constant is that what causes you to make sure all this stuff is right is an audit.
If we put two conductors inside of this,
that's a natural progression of making sure you're doing your job correctly.
Yeah.
Would you agree?
Twin X. Twin X
Yeah,
is a type
so-
of cable that you can commonly associate
But
with
all of y'all are
10
right.
per second Ethernet. It's often
All right.
installed as part of an SFP plus interface. This allows for full duplex communication.
And then last but not least, for domain one,
But it limits
explain the importance and efficiency of process improvement and security
about 5
operations.
meters.
Standardized processes. Make sure everybody's following a set of rules. Nobody's John Wayne in it, right?
Compare it to using something like a twisted pair connection.
We don't want nobody out there like that.
And you look at the ceiling.
I ought to take 6 paces and turn around and get you.
Instead, you're seeing a drop ceiling and something.
Nope,
acoustic
not at the OK Corral.
above the
Not
actual
today.
ceiling. There is a space.
Good old
between the drop
Charles,
ceiling
right.
And the actual
So,
ceiling. We refer to that space as
look for
the
things you can
plenum.
automate,
We may
because
have
what you're
network
trying
cables,
to
there might
do
be heat
is you're
sensors,
trying
there might
to,
be
Leroy
power,
Jenkins, oh my
there may
gosh.
be other
What you're trying to do is
pieces that are
minimize
inside the plenum
your
as well.
attack
In some
vector,
environments, there may be a drop ceiling, and above
right?
the drop ceiling may be
Right.
ductwork where
Hold
all
on.
of the air supply happens to flow.
Something
We have air
repeatable that can
supply
happen
as
every
part
day
of
that
the
will
heating
cut down on
system,
mistakes.
that ductwork, and there may be
Coordinate with your
return
team,
air
streamline that automation.
to go
Again,
back
here
to
we
the
go.
heating or cooling system.
But
Since
the
a
one
plenum
thing
implies that
right
there is
there,
a shared air
can anybody
space,
explain to me
a
data
configuration
enrichment?
such as this, where only ductwork is used to transfer the air, there would be no plenum. But if there's no ductwork and we share this same airspace with all of our network,
This is one of them words you'll see on the exam.
that we're using the proper type of network cables in that shared plenum. This would obviously be a concern
Look at Leah's
for fire,
picture.
especially if
Oh
we're
my
using
gosh.
a network
She's
cable
got the
type
gat gun,
that
the
produces
Tommy
small
gun.
trap smoke or
There you go.
hazardous fumes
Couldn't have said it
if
better.
was to catch on
Adding
fire.
value to
If
data,
this was in a plenum, that smoke
whichever
and
way
those
you
fumes
can.
would be
Ex-
distributed
ex-
to everyone.
Even Charles said it just as good too.
This means we need
Enhancing
to make sure
existing
we're
data.
installing the correct type of cable.
What can make it
We're
verbose?
installing this into
There you go.
a shared plenum.
All right.
Ethernet
Then
cables
minimizing
have a
human
jack cable
engagement,
on
then
the
with
outside of the
technology
cable,
tools and
and
integrations,
those Ethernet cables are
APIs.
with a polyvinyl
Uh,
How you guys doing?
He's
How you guys
a help us, but again, that's another attack vector. So we have to shore that up.
Cable, and that cable is
A
usually
webhook.
manufactured with a fluorinated ethylene
In your
polymer.
own words, can you
No, this is
describe to me
IT
a
class.
webhook?
You're
How does
asking
it
what I'm
work?
doing. This is IT
This
class.
polymer cable is designed to be much safer in a fire than one that is not designed for a plenum. One challenge when working with plenum-rated cable is it may not be quite as flexible as non-plenum-rated cable. So if you're going around a lot of twists and turns, it may be a bit more of a challenge to install that cable into the plenum. So if you're installing cable into
See what y'all come up with.
or you're
I see your
replacing
minds
cable in an
turning,
existing
all y'all.
building,
Wait, what was the?
Looks like he's got his hand on his chin and a pen in the other hand. He's formulating his sentences. The lane is on ChatGPT. I can see it. Yes. Okay. All right.
Transceiver is a combination of two words, transmitter and receiver, and these are usually combined with
Here we go.
piece
First
of equipment
telemetry
or the
coming
same
in.
component.
Mr. T
Transceiver allows for
says,
modularity. You may have
send
a switch
message
like this one.
automatically
You can see there are
when
a number
an
of
event
interfaces in this
or
switch.
something
Slide in
triggered
the
from an
transceiver
event.
that's appropriate for the medium.
Basically just something triggered it and sent a message. You are
Now
correct.
that particular interface will operate
Yeah.
with that particular configuration.
We gave the example of automotive repair. Real time, correct. Yes, real time. Where we said, yep, user defined callback enables the time of data sharing between.
Yeah.
Yes.
This means that you could have
All of y'all getting rockets.
on the switch.
You know, that's one of the hardest points students understand is webhooks.
You were planning to use. There are different.
We gave the
types of
example of your
transceivers,
car got dropped off,
factors, and
right?
different transceivers
Michael dropped off
on the medium.
his Aston
For example,
Martin.
if you are using an Ethernet switch, you need an
He's in there sipping on his coffee.
If you're
He's
using
getting lost in
fiber
the
channel switch,
pages
you
of
will
the
need
Wall
a
Street
fiber
Journal.
channel transceiver.
Right.
You can't
Yeah.
use fiber
But
channel transceivers in an
before he can
Ethernet
sit down,
switch
he
or
gets a
vice
text
versa.
message from
This
the
means you get to decide what media
dealership
type works best for your configuration.
because they use his personal
How you doing?
identifier
You were
information.
asking earlier what
As a webhook to the dealership
doing?
information base about
this
their
is
repair
currently
system.
IT class, pretty much.
Gave permission to link his phone number to their server for updatable real-time information. So before he sat down with his latte from Cafe Martini,
but it does provide you with a way to plug into what
it says they scanned his VIN number and said, Mr. Raymond, your vehicle has been intaked. It is now proceeding to the first stage of repair. Right? So he's getting these updates. Before he can finish, 2 hours into the Wall Street journey, he gets a repair. Mr. Raymond, your vehicle is ready to speed watch right now. Go deeper in 5 minutes. Look, no need for the service attendant to keep walking back and forth. Hey, Michael, kind of on the street. Right? So that is a web. Leah says, when this happens, send that information to this URL. This person It's like when you look for car insurance and they send you a link. Yes, you are correct. Yes, I forgot about that. Yes. Webhooks. Then, last but not least,
first, the equipment is only 19 inches wide, and the total amount of space available in the rack is limited by the amount of space you have in the data center. So we want to be sure that we can put as much
single pane of glass
into a single space as possible.
Because we do all of this that we talked about.
Quad small form factor pluggable. This effectively allows you to have
all
4
of
times the amount of
in its whole
throughput
course.
into a space
That allows you to look at your organization's threshold as a single pane of glass. There's no longer you versus me or that versus that. We get to look at everything and audit it as we go and fix what we need to fix as we go. Right? There's no separation of duties.
Gigabit throughput. The same thing applies for the SFP Plus. There is a quad SFP Plus.
That's domain one.
SFP Plus.
That's the biggest
Since it's
one.
common to see
That's the big. I know that was just domain one. That's
Yeah.
the biggest one.
Plus. A quad SFP Plus can support 4.
Don't worry, we'll hit domain 2 after lunch. You know at least we do the 2 highest domains, right?
Not only in the amount of space that
Because that's the biggest probability.
Yeah.
But we can
And if
take
we'll
a single
fill in
fiber
with some other
connection
stuff, right?
and
So
effectively
at least we gotta do domain 2 after lunch.
over that single fiber.
Then we do a
There's
Jeopardy.
cost benefit
Jeopardy fills in all the little stuff,
itself.
right? In between.
Although the names are very similar,
Did
the
y'all
form
get the
factors
link I
are
put
slightly
up in the
different
chat about
between an SFP and SFP
the
Plus
CYSA
and a quad
boot
SFP
camp that was
or
on
quad
LinkedIn
SFP.
that I showed you?
On the left is an SFP
Oh, it
or
was,
SFP Plus.
Oh, client
The
system text?
SFP
Heck
and
yeah,
SFP
client
Plus
system
use
text.
the same
Heck
form
yeah,
factor,
I would do that.
Although the transceivers are obviously very different. The
Okay,
quad
here we go.
SFP or quad SFP Plus
You can make
also
some good
shares
money
the
as a
form
client
factor,
system
but
tech.
you can see it's slightly larger
Picture this,
than
Mr.
the
T.
traditional
You wake up in the
SFP
morning.
or SFP
Yeah.
Plus. Although it is slightly
6 in the
larger
morning,
than
boogies at my
SFP,
doors.
it's not
Fresh
4
as
times
we
the
could
size
go
of
back
an
from the
SFP, so
out
we
the
are
back
getting an
window
efficiency
of
in
iced tea.
space by using
All right,
the
listen.
quad SFP or quad SFP
Gotta have the
Plus.
AK. Have a good day. Tupac was not the only original East Coast rapper that turned West Coast. Ice-T did it first. He was born in New York.
Fiber optics, one of the first things you
Went out on the West
notice
Coast.
is that
Actually got a
the
record deal
connector
with no
types
record being made.
that you use the
He was the
right
first one to
type
do that. He
or
said,
the
yo,
right
I got an
connection.
idea
The
for a
common
record.
fiber
Walk
connector
in,
type is the
right?
SC connector,
It's gonna be
or
like
the
this. Boom, boom,
subscriber
boom, boom.
connector.
It's gonna be
We
like
also
that.
have
Some
other
stuff.
names
Boom,
that
boom,
we
boom.
associate with
I
this
just need a
connector.
budget.
One is a
They said,
square
okay.
connector because the
Get him the money.
shape is rather square when you look at it. You
Yeah.
might also see this referred
All right,
to
so
as
this is
a
what
second
happens. As a
connector,
tech,
although there are certainly other types
you
of
wake
fiber
up,
connectors that you might
he
use.
checks his computer.
Use an SC connector.
Mr. T, we need you to go here today, here today, here today, here today, here today, here
It
today.
snaps in place with a lock.
It's your world.
Once you have that connector in
Prioritize-
place, it's not
prioritize.
accidentally
Here's all the
slip
clients.
of that connection.
See ya.
You first have to pull
He usually
on the
uses his
connector
own
to
vehicle.
unlock
He
it,
gets paid
and then it
mileage,
can be
80 cents a mile,
removed from that interface.
sometimes 60
This
cents
is
a
a
mile.
common connector type, and if you're plugging into
Takes his own lunch.
data center, you're probably using some
Gets
connections
overtime.
that are identified as
He can
SC.
pick up shifts.
The connectors themselves.
Heck, if there's a 24-hour client, he might be on call, which is more money.
Into a pair.
That's why I say client system tech,
Transmit, and the other is commonly used.
you pretty much make your own hours.
Another
Wow.
common fiber connector is
And it's in your
LC
area.
or local connector.
They'll give you like a
This is
20-mile radius or
smaller
something like that.
than an SC connector, and as you can see, it has a
Or if you want to go further, if they need you, They could put in a ticket and say, hey, Mr. T, we don't have anybody available. I know you don't do this, but on your job app, you said you're willing to go up to like 100 miles. They'd be like, yeah. Yeah, this is gonna cost for an overnight stay. We'll put you up. You'll get per diem. Like, yes. That is a mobile computer tech.
The LC connector can also be combined in a pair, looks like this. And
You're on your own.
both of
You're
them
running your own show.
simultaneously, and again, one is used for transmit and the other used for
Yep.
receive.
So those kind of jobs,
This is the
you're in demand. And you get paid. Now you're a contractor.
It uses a bayonet connector.
You're a contractor.
Into an interface.
So they'll say no vacation and stuff like that, but you can put on for a day off. If you have Michael and Elaine and Aaliyah and everybody, they're on the same like kind of geographic. He could ask, hey, Elaine, can you cover my clients? I'm like, I need to take 4 days. He'd be like, bet, I got you. That's more overtime for me, right? So that's how that works. But yes, definitely do
Here's a
that.
closer view of
Baby,
the
baby,
SC
yep,
connector.
Tupac and Biggie were best friends. That's how I started out.
Which you can barely see in this picture.
Until
You can
Diddy
easily
got
see
in the middle. But we gonna
a
talk
net
about that.
connector where you would plug it in and twist it in place so that it's
All right.
locked into that interface.
It's 12:30.
One of the challenges with the connector types that we've seen
Do you
so
know
far
Suge's brother?
is that those fiber connections take up a lot of real
Suge's brother
estate.
was.
It would be a lot more efficient if we could put
Bobby
more
Brown
fiber
goes
into
Suge's
a
brother's
smaller
money.
connection.
But we gonna talk about that.
There is
That's
a
a,
connector
yeah.
type for that
Mm-hmm.
called the
All right.
MPO, which is multi-fiber push-on.
I'm gonna let you get to it.
Inside the MPO are 12
Get in your
individual
study
fibers that are
above
contained
hope
in
or
that
lunch,
single
and
cable
then when we
connection.
meet back,
This
after
also
you have to
has
take a quick break,
lock
go
in
ahead.
place that's very similar to the SC connector, where you would push it in place and you would have to pull it out slightly to unlock it from the interface. You might also see this connector referred to as an MTP. That name is provided by Corning, and they refer to this as an MTP MPO connector. Here's a side view of the connector. It has this lock on the top, and the individual fibers are these smaller dots you can barely see in this picture. If we look at it straight on with some light being sent through the fiber, you can see that all 12 of those fibers are much easier to see on the MPO connector. One common copper connector we use on our networks today is an RJ11. This stands for Registered Jack Type 11. It is a 6-position connector, but we only use 2 conductors inside of this connector. Sometimes you'll see this referred to as a 6P2C, or 6-position 2-conductor. We commonly associate an RJ11 connector with an analog telephone, but you'll also see RJ11 used for DSL connections, since those use exactly the same wires as a telephone connection. Here's a better view of the RJ11 connector, and you can see the 6 positions, 1, 2, 3, 4, 5, 6 are clearly marked, but you notice that there are the 2 conductors in the middle that are used for RJ11. If you're using an Ethernet connection, then you're using an RJ45 connector, and this stands for Registered Jack Type 45. It is an 8-position connector with 8 conductors inside, so we're using all of the conductors available on an RJ45 connection. This is slightly larger than an RJ11 connector, and it's what you would use if you're plugging in an Ethernet connection. Here's a device that has both RJ11 and RJ45 connectors on it. You can see this is a DSL connection that uses the RJ11, and these LAN connections or Ethernet connections are using the RJ45. You can see that they're very similar in shape, although the RJ11 is slightly smaller than the larger and wider RJ45. If you're using a cable modem connection, then you're probably bringing coax connections and plugging it into a cable modem. And the connector that you're probably using is the F connector. The F connector is a standard connection type. It usually has threads inside that allow you to fasten it very securely to the connector. And if you are using a cable modem, this is probably the connection type that you're using from the cable television infrastructure. This is also referred to as a DOCSIS connector. That stands for Data Over Cable Service Interface Specification. The connection that brings the signal is this single copper connection on the inside of the cable. This is what you would plug in and screw into a cable modem using that F connector connected to the coaxial cable. Another common connector used for coax is a BNC connector. This is a bayonet connector, that's what the B stands for, where you push it into the connector and twist it slightly to lock it in place. The NC in the BNC connector stands for Neil Conselman. This stands for Paul Neil from Bell Labs and Carl Conselman from Amphenol. They both were involved in creating this standard for a BNC connection. If you're bringing in a WAN connection or any other type of coax, it's very possible you might use a BNC connection to lock this in place. That is one of the benefits of using BNC, is that you're able to push the connector in and twist it, and it's not going to easily remove itself from that connection. You would need to untwist before removing that from the interface. Here's a close-up view of the BNC interfaces on a device. You can see where you would plug in the BNC connector, you twist that connector slightly, and it's locked in place onto that device. Networks can connect to each other in many different ways, and in this video we're going to look at a number of different network topologies and how those different network topologies can be deployed in an enterprise network. This can be very useful during the planning process where you're designing the network. It's also useful during the troubleshooting process so that you can tell how different networks are connected to other networks. This is also useful during the troubleshooting process so that you can visually see how one network might connect to and send data to another network. Let's start this conversation with one of the most popular network topologies in use. That would be a star network. Sometimes you may hear this referred to as a hub and spoke network. This is what we use in most large networks to connect devices together. There is a central device that is used as the central networking component, and then everyone on the network is all connecting to that same central device. A good example of a star network or a hub and spoke network is one that we have with switched Ethernet. Our Ethernet switch sits in the middle of the network, and all of the other devices connect to that same Ethernet switch. If each of these spokes around the network would like to communicate with each other, they all must communicate through this central hub. A mesh network design is if one location or device connects to another location or device over more than one network connection. This means that we can have one link communicating to another, and it might follow one path to get to that location, or it may follow an alternate path to be able to get to that location. One reason we design a network this way is so that if one link in the mesh was to fail, we can use one of the other links to complete that communication. We might also perform load balancing over these links, where half of the data is sent over one connection and the other half of the data is sent over a different connection. Although we can certainly design mesh networks for local area networks, we often see them deployed in wide area networks so that we can maintain connectivity to a remote site regardless of what network connection might be available. If you were to look at a large enterprise network, you would notice there are a number of different architectures all being used in different parts of the network. And when we combine all of those together, we've created a hybrid network. One part of the network might be a star network, another part of the network may be point-to-point, and a third part of the network might be a mesh network. Once we combine all of these together, we've created a hybrid architecture. Many data centers take advantage of a spine and leaf architecture. This is where you would have individual switches at the top that are the spine of the network. There would be switches in the middle that are leaf networks, and then you would have different devices connect to the leaf. You'll notice that the spine network is connected to all of the leaves, and the leaves are connected to each of the spines. However, those leaf switches do not connect directly to each other, and the spine switches also do not connect directly to each other. This works very well for an architecture we use in many data centers known as top-of-rack switching. In top-of-rack switching, every rack has a leaf switch at the top of every physical rack. We would then connect all of the physical devices in that rack to the leaf switch that is at the top of that rack. This keeps your cabling very simple because all of your cabling is self-contained within that same rack. There is redundancy because you have this rack connected to multiple spines. This also increases the overall performance of the network because we're no more than one switch away from any other device in the data center. If your data center only has a handful of racks, this may be a relatively inexpensive way to connect all of these devices together. But when you have tens or hundreds or even thousands of racks in a data center, you would need a separate switch for every rack, and of course the cost of that will increase for each rack you have in the network. When looking around the network, you may find some wide area network connections that are point to point, and as the name implies, there is a single point connected to a single point. This was a very common design on older wide area networks where you would use something like a T1 or a T3 connection. We refer to those as point-to-point T1 or point-to-point T3. We might also use this design in local area networks. If you work on a campus, you can connect one building to another over two connections, and the connection between those two buildings would be a point-to-point connection. Many enterprise networks take advantage of a three-tiered architecture. This is a very common design, and you'll find many organizations use a three-tiered network design for their network. This starts with the core of the network, and this is where we might have the central point for all of our resources. So our servers, our applications, our databases, and other critical points are going to be contained within the core of the network. The second tier in a three-tiered architecture is the distribution layer. This distribution is the midpoint between the users and those core resources. This is usually a series of switches that provides redundancy and connectivity for those users to access those critical resources. And lastly, our users need somewhere to connect, and they often connect to an access layer. These are switches that are usually located very close to the user, usually on the same floor of a building, for example, and that access layer allows us to connect to the distribution, which then connects to the core of the network. This three-tiered architecture is very common to what we might see in a large city. The downtown area of the city is the core of the city, and all of the major resources for that city may be located in a very small geographical area in the center or core of that location. To be able to get to downtown, we need some type of distribution method. For example, we need some type of highway that might connect our homes to the downtown area. And our homes are usually connected to these larger highways through access roads. This allows us to use our local roads for all of our daily chores, but when we need to get to the core downtown, we may need to use those distribution highways. Here's what this three-tiered architecture looks like in a network diagram. The core of the network usually has core routers that are allowing us to connect to other resources in the core. The distribution layer in the middle is the one connecting the core to the access switches. And at the very bottom, the access layer is the one that all of the users are connected to. You'll notice there are multiple links between the access and the distribution, and occasionally you might even find multiple links between the distribution and the core. So if one component happens to fail, we can always use other parts of the network to complete that communication path. This is often combined with multiple buildings. So here on a single campus, we have two separate buildings. All the users are connected on each floor of the building to an access switch. Each access switch in the building is usually connected to one or more distribution switches, and those distribution switches are connected to the core of the network, which may be located in a central data center. If you're a smaller organization, there may not be a need for a much larger three-tiered architecture. Instead, you might want to use a collapsed core architecture. This is a two-tier architecture that combines the core and distribution layer into a single collapsed core. And you can see the access layer is still exactly the same as it was before. This allows for a more simplified design and hopefully a much easier design when you're troubleshooting. This is also a lot less expensive to implement because you have less devices that you have to purchase and install onto the network. However, as you can tell by this diagram, there's not a lot of options for redundancy, so this may not be quite as resilient if you happen to lose any of these individual components. When you're describing the flow of traffic within a data center, it's important to know where the traffic originates and what the destination is for that traffic. One way to describe traffic flow is an east-west traffic flow. This means that the origination and destination for this data flow is all within the same data center. This also means that we probably have very good response times from one device to another since they're all located on the same local network. If the traffic flow is one that is leaving the data center or is coming into the data center from an external source, You would refer to that as north-south traffic. This would probably have a bit of a different security posture than something that is east-west traffic, because we really don't know where this traffic is going once it leaves the data center, and any inbound traffic could be coming from potentially anywhere. Here's a better view of this traffic type. If data is coming into the network from the internet, or we're sending information out to the internet, we refer to that as north-south traffic. Any traffic that is inside this local data center, for example, if we have a file server that is sending information to an image server, all of that traffic is staying within the data center and would be considered east-west traffic. In the next part of this course, we're going to talk a lot about IP subnetting. And a big part of subnetting is the ability to convert between decimal and binary. So I thought it would be useful in this video if we step through the fundamentals of performing binary calculations. Binary, of course, is a type of numbering that uses two different numbers, either a 0 or a 1. This means that there are only two possible options when doing mathematics in binary. The answer is either going to include a 0 or it's going to include a 1. Each one of these zeros or ones is referred to as a bit. And when we combine 8 of these bits together, we have a byte. Occasionally you will see a byte referred to as an octet to be sure that everyone understands that this is an 8-bit byte. In this video, we're going to perform a lot of calculations between binary and decimal. So what we need to create is a conversion chart to convert between binary and decimal. We'll create this chart by starting on the right side, and we'll simply put the number 1. Then we're going to double that number and put it to the left. So doubling 1 makes the number 2. If we double the number 2, we have the number 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32, and so on. This is the conversion chart that we will use for almost all of our decimal to binary conversions. We created this chart with 8 individual places, but you could keep moving to the left with this chart and go past 128. We'll double it to 256. We'll double that to 512, and so on. You can keep continuing this process so that if you have a very large binary number, you can still perform the same type of conversion back to decimal. Let's now use this chart to answer this question. What is the binary 00000010 in decimal? First, let's write down this value in decimal. So it's 00000010. And of course, we want to know what the decimal equivalent is of that binary value. We'll then layer on top of this our conversion chart. So of course, we start on the right side with a 1, then 2, 4, 8, 16, 32, 64, and 128. Now we have everything we need to perform this binary calculation. In each of these places where we have a binary 0, we're going to bring that 0 down to the bottom line. In every place where we have a binary of 1, we're going to take the number just above that and bring it down onto the bottom line. We're then going to add all of these numbers together on the bottom line. So 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 2 plus 0 equals 2 in decimal. So the answer to this question of converting binary 00000010 is the same as 2 decimal. Let's do another one. What is the binary 10000010 in decimal? We will write down our binary value, and then we'll layer on top of that our conversion chart. Every place there is a 0, we're going to pull that down and put a 0. And every place there is a 1, we're going to pull down the number just above that 1. And you can see we only have 2 binary 1s in this number, and that's associated with the 2 and associated with the 128. So we'll bring down the 128, we'll bring down the 2, we add those together, and we've got 130 in decimal. So the binary value 10000010 is the same as 130 in decimal. And finally, let's do one more binary to decimal conversion. This binary value is 11111111. We'll bring down that binary value, and we'll layer on top of that our conversion chart. And because each one of these spaces has a 1, we're going to bring down all of the numbers of our conversion. And if we were to count 128 plus 64 plus 32 plus 16 plus 8 plus plus 2 plus 1, you would have the value of 255 decimal. So the conversion of 1111, 1111 in binary is the same as 255 in decimal. Now let's do the same conversion, but in reverse. Let's take a decimal number and convert it to binary. This question asks, what is the decimal 154 in binary? It's the same process. We're going to bring down our binary number, but of course we don't know what that binary number is yet, so we'll put some place marks here, and then we'll layer on top of this our conversion chart. Now we need to determine which one of these binary values will be a 0 and which one will be a 1 to make up 154 decimal. And there is only one combination of zeros and ones in this chart that would equal that decimal value. We'll start on the right side where we have our 128 column, and we'll ask ourselves, is 128 less than or equal to 154? This is obviously less than 154, so we'll put a 1 in that column, and we'll bring down the 128. Now let's look at our next column of 64, and we'll combine that next column with the numbers that we've currently brought down previously. In this case, the number 128. So 128 plus 64 is 192. And we have to ask ourselves, is 192 less than or equal to 154? In this case, 192 is more than 154, so the answer is no, and we'll put a 0 in that column. Now we move to the next column, which is our 32. We'll add 32 plus anything that we brought down. That would be 128 plus 32, which equals 160. Is 160 less than or equal to 154? It is not, so we'll bring down a 0 in that column. We'll continue with this process by looking at the fourth column, which is 16. We'll add that to anything that we brought down. So 128 plus 16 is 144. Is 144 less than or equal to 154? It is, so we'll put a 1 in that column and bring down the 16. Our next column is the 8, so we'll add 8 to anything that we've previously brought down. So 128 plus 16 plus 8 is 152. Is 152 less than or equal to 154? It is, so we'll put a 1 in that column and bring down the number 8. Our next column is the number 4. We will add 4 to everything that we brought down into that bottom row. So that all adds up to 156. And is 156 less than or equal to 154? It is not, so we'll put a 0 in the 4 column. The next column is the number 2. We'll add the number 2 to everything that we brought down so far. And if we add all of those up, it would be 154. Is 154 less than or equal to 154? It's obviously equal to 154. So we'll put a 1 in that column and bring down the number 2. And obviously we've hit the number 154, so we know that the number 1
All right, it's
on the
lunch.
last column
I'll see
will
you in
not
an
be
hour.
added to this final value. And if we add up everything in that last row, we see it does equal 154. And now all we have to do is look at the middle row to determine what the binary value of this is, and it would be 1001, 1010. If we look at 154 decimal, we know that that is exactly the same as 1001, 1010 in binary. With these 8 individual bits, we can convert a number between 0 and 255. So take any number you would like, put it into this particular format, and see if you can perform the conversion between binary and decimal. As you're increasing the number of bits in a binary value, you're increasing the total possible number of decimal results. For example, if you have 2 bits, there are only 4 possible outcomes: 0, 0, 0, 1, 1, 0, and 1, 1. And if you were to perform that conversion between binary and decimal, that's the same as 0, 1, 2, and 3. If you have 3 bits, then you can have 8 possible outcomes. If you use 4 individual bits, you have up to 16 different options. 5 bits moves you up to 32. 6 would be 64. 7 bits is 128 possible options. And if you were to increase the number of bits into 9 bits, 10 bits, 11 bits, and so on, you would also increase the total decimal number. You can see that this value is listed in this chart. And notice that I've also added the powers of 2 on top of this. This is effectively what we've been doing the whole time. 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8, and so on. So as we increase this powers of 2, we are also increasing the total decimal value. you've done anything with networking, then you've probably run into an IP version 4 address. In this video, let's look at the different configuration options for IP version 4. The IP address is the unique identifier that every device on the network must have if it wants to communicate using that IP protocol. An IP address is a series of 4 numbers separated by a period. This would be something like 192.168.1.165. To be able to properly communicate on the network, every device needs to have its own unique IP address. The IP address is combined with another value referred to as the subnet mask. The subnet mask is also a 4-octet value, for example, 255.255.255.0. The subnet mask is used in conjunction with the IP address to determine what IP subnet this particular device is on. This isn't something that's usually transmitted across the network. It's instead used by your local device to make the determination of what devices are local on this IP subnet and what IP addresses may be outside of this local IP subnet. This becomes especially important when you need to send traffic outside of your local subnet, and you do that through the use of a default gateway. The default gateway is the IP address of a device that's on your local subnet that allows you to communicate outside of this subnet. For example, if we have an IP address of 192.168.1.165 and a subnet mask of 255.255.255.0, a common default gateway could be 192.168.1.1. This is an IP address that is configured and assigned to the router on your local subnet by your network administrator, and it must be an IP address that is on your local network. There are also other IP addresses you should be familiar with. One of these is a loopback address. This is a way to define your local device without having to know a specific IP address. Every device on the network has a loopback address, and it's a number that is between 127.0.0.1 through 127.255.255.254. So if you wanted to ping your local device, you could ping 127.0.0.1, and hopefully your local device would be able to respond to you. This is often used to confirm that your local IP stack is working properly, and it would then be able to communicate to other devices. We also have a range of IP addresses that we set aside as reserved addresses. This is a range of IP addresses that should never be assigned to other devices. They're used for future use or for testing in the future. This range of reserved addresses is 240.0.0.1 through 254.255.255.254. Anything that is a Class E address is also a reserved address. We'll talk about classes of addresses in just a moment. And another address type you might run into is one that is not real. It's a virtual IP address, or a VIP. Virtual IP addresses are not associated with a physical Ethernet adapter. Instead, VIPs are addresses that you would assign to the internals of a device so that you can always reference that device using that virtual IP address. For example, you might assign a VIP to a virtual machine, or the VIP may be part of an internal address that you're associating with a particular router. The IP protocol and IP version 4 operate at OSI layer 3. So anytime you're working with an IP address, you're working at that network layer of the OSI model. Let's break apart an IP version 4 address and really see what it's made of. Let's take the address 192.168.1.131. We refer to these 4 values as octets. That's because they consist of 8 individual bits. And you can see the representation of that same IP address broken out into those 4 groups of 8 bits. Sometimes you'll see these 8 bits broken out and described as 1 byte or sometimes 1 octet. So if you were to count up all of these bits, there are 32 total bits in an IP version 4 address, and that is the same as 4 bytes or 4 octets. Since each one of these individual groups inside of IP version 4 consists of 8 bits, the maximum value that you would ever have in decimal for any of these groups would be a maximum of 255. In the early days of networking, we had to manually configure the IP address, subnet mask, and default gateway all in a manual way. We had to visit that device, change a configuration file, and then that device would be able to communicate on the network. If anything changed with our network configuration or we needed to change the IP address of that device, we had to revisit the device and manually make those changes. Today, of course, we can plug in any of our devices and it automatically receives an IP address. The way that we are able to receive this automated IP addressing is through a protocol known as DHCP, or Dynamic Host Configuration Protocol. When we plug into a wired Ethernet network or a wireless network and we're automatically able to communicate out to the internet, it's because we've received all of our IP configuration settings via DHCP. But if you've ever connected to a network that does not have a DHCP server, you may notice that you're still assigned an automatic address. But this address is not quite as capable as a DHCP address. Instead, it's what we call a link local address because it can only communicate to other devices that are on your local subnet, and we cannot route that traffic outside of your local subnet. For example, if you're assigned a link local address, you can't communicate to the internet because that's outside of your local subnet. In IP version 4, this link local address is assigned through a process known as Automatic Private IP Addressing, or APIPA. This range of IP addresses automatically assigned through APIPA is 169.254.0.1 through 169.254.255.254. There are also reserved sections of that range. The first and last 256 addresses are reserved and they're not assigned to end stations. So if you receive an APIPA address on your device, it's between 169.254.1.0 through 169.254.254.255. Just as DHCP works automatically to assign your address, APIPA also has an automated process to assign this address. It uses ARP to confirm that no one else on your local network has that link local address, and if nothing responds to that address resolution protocol query, then it will assign a random number between that functional block. One of the challenges with IPv4 is that there are far more devices in the world than there are IP version 4 addresses. And in recent years, we've used up all of the available blocks of IP version 4 addresses. There are no other IP version 4 addresses that can be assigned in these blocks, so we need to find other ways to be able to communicate via IP version 4. One way that we've been able to extend the functionality of IP version 4 is to create an assignment of IP address ranges that can only be used on the inside of a network. We refer to these as a private IP address range, and anything that is a private IP address cannot be routed on the public internet. Fortunately, these are very large ranges, and we're able to use those ranges on the inside of our corporate networks. If you were to look at the IP address that's assigned to your device right now, it's likely that it's a private IP address. So if your device is currently using a private IP address and you're watching this video on the internet, how are you able to communicate on the internet with an address that is not able to be routed across the internet? We're able to do that through a functionality called Network Address Translation. This allows us to convert a private IP address into a public IP address and use that public IP address to communicate on the public network. We'll learn more about network address translation as we go through this training course. If you want to learn more about private IP addresses, you may want to reference a request for comment, or RFC. RFC 1918 is the standard that defines these ranges of private IP addresses and how they can be used on our networks. If we were to look into the details of RFC 1918, you would see 3 different ranges have been set aside for private IP addressing. These 3 ranges are 10.0.0.0 through 10.255.255.255. And if you were to count up all of the possible addresses in that range, it would be over 16 million addresses. We often refer to this as a single Class A block of addresses, and we often write it as 10.0.0.0/8. If you were to write out the subnet mask of that /8 address, it's 255.0.0.0. This means the host size of this particular IP address range is 24 bits in length. Another range is 172.16.0.0 through 172.31.255.255. This gives us a total of just over 1 million addresses that we can assign in 16 contiguous Class B address ranges. If we were to write this out in CIDR block notation, it would be 172.16.0.0/12. The decimal subnet mask for a /12 network is 255.240.0.0, which means our host ID size is 20 bits in length. And the last range is 192.168.0.0 through 192.168.255.255. This allows us to assign over 65,000 addresses as part of 256 contiguous Class C address ranges. The CIDR block notation for this would be 192.168.0.0/16, and that /16 subnet mask is the same as 255.255.0.0. Half of this address is assigned per host, so your host ID size is 16 bits in length. As we step through the next series of videos, you'll learn more about CIDR block notation, the different classes of IP addresses, and other details that you see associated with these private address ranges. When you start working with IP version 4, one of the things you'll hear about are classes of IP addresses. And in casual conversation, we might even refer to an address as a Class A address, a Class B address, or a Class C address. This was a method of describing an IP address as it related to its subnet mask. Anything that is a Class A address has 8 bits assigned for the network address and 24 bits that are associated with the host address. This means that the subnet mask for a Class A address would be 255.0.0.0. A Class B address default subnet mask is 255.255.0.0, and the default subnet mask for a Class C address is 255.255.255.0. This style of class-based subnetting is one that we have not used since 1993, but we still refer to some of these addresses in a very colloquial sense. And although you may hear someone refer to an address as a Class A address or a Class C address, in reality, we no longer use a class-based form of subnet masking. So if we don't use classes, why are we doing a video on class-based networking? That's because these classes do act as a starting point when we begin any type of subnetting on our networks. If you're going to subnet a network, it's important to know where to begin the subnetting process, and this class-based system is the starting point. These Class A, Class B, and Class C addresses have an obvious demarcation between the network part of the address and the host part of the address. With Class A, that line is drawn after the first 8 bits. In a Class B address, that line is after the first 16 bits. And in a Class C address, that line is after the first 24 bits. Here's a table that defines the different subnet classes for Class A, Class B, Class C, Class D, and the reserved Class E. And you can see if you look on the right side, the default subnet masks are the ones we just saw, where Class A has a default mask of 255.0.0.0, Class B is 255.255.0.0, and Class C is 255.255.255.0. The way that you can look at an IP address and tell immediately what class that IP address is associated with is the very first octet of the address. If the decimal octet is between 0 and 127 as the first number of that IP address, it's a Class A address. If the first number of the IP address is between 128 and 191, that's a Class B address. And if the first number is between 192 and 223, that is a Class C address. If you were to look at that address in binary, if the first bit was 0, it's a Class A address. If the first bits are 10, it's a Class B address. And if the first 3 bits are 110, it's a Class C address. Class D addresses are used for multicast communication, and therefore they are not assigned to an individual device. But there is a range for Class D addresses, and that is between 224 and 239, or the first 4 bits of a Class D address are 1110. And there is a range of IP addresses that are not used for any purpose. This is a reserved range. We refer to this as the Class E range, between 240 and 255, or the first 4 bits of 1111. So based on that chart and those ranges of IP addresses, let's see what class a particular IP address would be part of. Let's start with the IP address of 17.22.90.7. To be able to determine the class, we need to look at the first octet, which in this case is the number 17. And if you refer back to that chart, the number 17 is in a Class A address. Let's do another one. IP address is 220.10.77.40. If we look at that first octet, it is 220, and 220 is in the C class. The next IP address is 165.245.0.1. We need to look at that first octet. In this case, that's 165, and 165 is in the range of a Class B address. Next on our list is 128.90.10.2. That first number is 128, which means that is also a Class B address. The IP address of 191.77.24.250 has the first octet as 191, and if we refer to our chart, 191 is in the range of a Class B address. And lastly, 192.1.12.5, we're looking at that first octet of 192, which falls in the range of a Class C address. When you start calculating an IP subnet, there are 4 different values that are very important to know. The first is the IP address associated with the network address. This is the one that defines all of the other devices on this particular subnet. To calculate a network address, you set all of the host bits of that address to 0 and then determine what the decimal representation of that might be. The second important piece of information you need for an IP subnet is the first usable host address on that subnet. This is always going to be one number higher than this previously defined network address. You also need to know the network broadcast address. This is the last IP address of this particular network address. To be able to calculate the network broadcast address, you would set all of your host bits to 1, which is the same as 255 decimal, and perform the conversion between the binary and the decimal. And just as you need to know the first usable host address on the network, you also need to know the last usable host address. And to calculate that, you look at the network broadcast address, and it's one number fewer than the broadcast address. So let's calculate those 4 important subnet values. And let's start with the IP address of 10.74.222.11. If we look at our chart, we know that this starts with the number 10, therefore this must be a Class A address. And the default subnet mask for a Class A address is 255.0.0.0. Since we're using this Class A subnet mask, we know that everything that's on the left side of our bar, or this first octet, is going to be our network address, and everything on the right side will be associated with the host ID. So let's add those to our chart. We have a network column and a host column. Obviously, the 10 dot is going to be in the network column. That's what's on the left side of that bar. And then everything on the right side is going to be the host address. We first need to calculate the network address, and to do that, we set all the host bits to 0. This means that everything in that second column will be 0, and the network address, therefore, will be 10.0.0.0. The first host address is one more than the network address, so our first host address would be 10.0.0.1. To calculate the broadcast address for this subnet, we set all the host bits to 1, which means that the broadcast address is 10.255.255.255. And as you recall, to calculate the last usable address on this subnet, we need to subtract 1 from the broadcast address. So the last usable address on this network is 10.255.255.254. With these 4 values, you'll be able to determine the network address. You'll know if an IP address happens to be one of the usable addresses within that range, and you'll know what the last or broadcast address is with that entire network. Let's do another one. In this case, the IP address is 172.16.88.200. If we look at that first octet, we can see that that is a Class B address, which means the default subnet mask for this network is 255.255.0.0. This means that we would draw our line right in the middle between the first 16 bits and the last 16 bits. So everything on the left side is associated with the network address, and everything on the right side is associated with the host address. Now let's perform those exact same calculations. We want to determine what the network address is, so we will set all host bits to 0. This means that the network address for this particular subnet is 172.16.0.0. To be able to calculate the first host address, we need to add 1 to that value, or 172.16.0.1. To calculate the broadcast address, we set all host bits to 1, which means the broadcast address for this subnet is 172.16.255.255. And to define the last usable host address on this network, we subtract 1 from the broadcast address, which means the last usable address is 172.16.255.254. Let's see if we've figured out this process and step through another IP address, in this case 192.168.4.77. Looking at this first octet of 192, it fits into the range of a Class C address, which means the default subnet mask is 255.255.255.0. If we were to draw our line, the network side of the address is the first 3 octets, and the host side is the last octet. Let's put that into our chart. So our first 3 octets, 192.168.4 is the network side, and .77 is the host side. To be able to calculate the network address, we set all host bits to 0, so the network address for this particular subnet is 192.168.4.0. If we add 1 to that address, we get our first host address of 192.168.4.1. To be able to calculate the broadcast address, we set all host bits to 1, which means the broadcast address is 192.168.4.255. And if we subtract 1 from that broadcast address, we get the last host address. That would be 192.168.4.254. Although we no longer use class-based subnetting, we can still use this same process when we look at anything that may be class or non-class based. And as we go through our additional subnetting videos, you'll notice that the same process is used over and over again, regardless of the IP address and the subnet mask. In a previous video, we talked about class-based subnetting and how IP addresses can be assigned a Class A, Class B, or Class C address. But since 1993, we've not used class-based subnetting. Instead, we use classless subnetting. Sometimes you'll see this referred to as classless interdomain routing, or CIDR. This classless addressing means that we can assign a subnet mask that doesn't fall into those same Class A, Class B, or Class C arrangements. And instead of referring to the subnet mask in its decimal form, we can simply refer to it as the number of bits. That number of bits is referred to as a CIDR block notation. For example, a decimal subnet mask of 255.0.0.0 is the same as a /8 CIDR block notation because it has 8 individual bits as part of the subnet mask. So it would be very common to see an IP address written as 192.168.1.44/24. Everything with the /24 is referring to the number of bits in a subnet mask, and a /24 mask would be the same as 255.255.255.0. When you're configuring a device, you're often giving it an IP address, a subnet mask, a default gateway, and very often a series of DNS servers. Most of the time, an operating system is expecting you to put the subnet mask in as a decimal mask. So for example, of Windows, you may put the IP address and then you might add in the decimal version of the subnet mask. But if you're using a router or a switch, it may be expecting the CIDR block notation for those masks. So instead of using 255.0.0.0, you would simply input /8. Make sure you check the documentation of the device you're using to see what notation it prefers for the subnet mask. As you've probably seen in our previous examples of subnet masks, the mask consists of a contiguous series of 1s followed by 0s. So the 1s would be on the left, the 0s would be on the right. For example, here is a subnet mask. You can see the contiguous set of 1s on the left and the 0s that are on the right. In this example, you can see 3 separate octets that are set to 1. So there are 24 1s in this particular mask, and there are 8 zeros at the end. If we were to write this out in decimal, it would be 255.255.255.0. And if you were to write this out in CIDR block notation, You would count how many ones are associated with the subnet mask. In this case, there are 24, so the CIDR block notation would be /24. The subnet mask is obviously used to separate the network part of the address from the host part of the address. So for this particular subnet mask, the network address is 24 bits in length, and the host address is 8 bits in length. Let's convert a binary subnet mask to one that is the CIDR block notation for a subnet mask. And we'll take this subnet mask that we have on the screen, which has all ones in the first 2 octets and all zeros in the last 2 octets. If we were to count the number of ones in this subnet mask, we have 8 in the first octet, 8 in the second octet, none in the third, and none in the fourth. That means the total number of ones in the subnet mask would be 16, so the CIDR block notation would be /16. This means that the first 16 bits of this subnet mask are associated with the network, and the last 16 bits are associated with the host ID. Let's do another one. In this example, the first 3 octets are all ones, but the last octet has 2 ones and 6 zeros. So let's count the number of ones in this subnet mask. There are 8 in the first octet, 8 in the second octet, 8 in the third octet, and 2 that are in the fourth octet. If we count all of those together, we have 26. So the CIDR block notation of this subnet mask would be /26. The /26 means that the first 26 bits of this address are the network part of the address, and the last 6 bits are reserved for the host ID. And here's one more. In this subnet mask, we have the first octet of all ones. The second octet has 4 ones and 4 zeros, and then the third and fourth octets are all 0. Since we are counting number of ones, we have 8 in the first octet and 4 in the second octet. And if you count those together, the subnet mask in CIDR notation would be a /12. That means that the first 12 bits are for the network ID, and the last 20 bits would be for the host ID. We've looked at the subnet mask in binary, and we've calculated the CIDR block notation, but we often refer to the subnet mask as a decimal value. If we were to convert these binary subnet masks into a decimal value, there are only a certain number of these that you would run into. For example, all zeros would obviously be a decimal 0, but anything that starts with a binary of 1 and no less zeros would be a decimal of 128. If there are 2 ones, it's 192, 3 would be 224, and so on. This means that you can create a chart that shows all 8 of the bits within a single octet and what the decimal equivalent would be. We can now use that chart to calculate the CIDR block notation and what the decimal representation of that subnet mask would be. So let's look at a subnet mask of all ones in the first octet. There are 4 ones in the second octet, and the rest of this would be all zeros. If you remember our chart, you can see that all ones is 255, 4 ones and 4 zeros would be 240, and then of course all zeros would be 0. And if we recount the number of ones, we know that correlates back to a /12. So a /12 CIDR notation is the same thing as 255.240.0.0 in decimal notation. And of course, since there are 12 ones, the network section is 12 bits in length, which leaves the remaining 20 bits available for the host ID. Let's look at a subnet mask we've not seen yet. This one is all ones in the first octet, all ones in the second octet. There are 3 ones in the third octet, and of course the rest of this is zeros. If we look at our chart, we can see that of course all ones is 255, and in the octet that has 3 of these ones, we refer to the chart that is the same as 224 in decimal. And obviously all zeros in binary is the same as 0 decimal. If we then count the number of ones in all of these octets, they all add up to 19. So your CIDR block notation would be /19, which corresponds back to the decimal representation of 255.255.224.0. This of course means that the network part of this address is 19 bits in length, and the host section is 13 bits in length. Of course, we can do this in reverse as well. Let's say that we have a subnet mask that's been given to us as a /26 in CIDR block notation. If we were to write this out in binary, that means that we would have all ones in the first 3 octets and 2 ones in the last octet. And if we would refer back to our chart, all ones would obviously be 255, and the last octet that has two ones correlates back to a 192 in decimal. So a /26, where your network ID is 26 bits in length and the host ID is 6 bits in length, is the same as a /26 in cider block notation, or 255.255.255.192 in decimal. Let's do another one where we've been given a /20 in cider block notation. That means there are 20 ones in this particular subnet mask. So your first two octets are all one, and the third octet has 4 ones and 4 zeros, and of course, the last octet will be all 0. If we refer to our chart, we know that the decimal version of that binary subnet mask will be 255.255.240.0, which is the same as a /20 cider block notation. That means the network part of this address is 20 bits in length, which leaves us 12 bits available for host IP addresses. In this video, we're going to look at a detailed calculation of subnets and hosts using IP version 4. If you stumbled across this video, I highly recommend you go back and look at our video on binary math, classical subnetting, and IPv4 subnet masks. As we've been going through these subnetting videos, you may be asking yourself, why do we have to go through this process of calculating IP addresses, their mask, looking at default gateways, and understanding what the first and last available IP address might be? Well, that's because it would be functionally impossible to have one device that would know where every other device in the world might be. Instead, we create smaller networks and we build routers that are able to get information between all of these smaller networks. This allows us to communicate to anywhere in the world without knowing exactly where that destination location might be. We simply send out the packet, and the routers every step of the way allow us to get that information to the final destination. Well, this means that we need to create these smaller networks, and we do this by using a process known as VLSN, or Variable Length Subnet Masks. As the name implies, these subnet masks are not like the class-based networks that we looked at earlier, which have a very fixed number of bits in the subnet mask. Instead, we can create a subnet mask that has a different number of bits on every network, therefore creating a variable length of a subnet mask. This means you, as the network administrator, can build a network that is exactly the right size with the right number of networks and the right number of hosts. And you have complete control over what the subnet mask might be for that network. This is a lot like cutting a pizza into smaller pieces. How many pieces do you need in the pizza? Should the pizza be cut in 2 pieces? Should it be 4? Should it be 8? Or should it be even more than that? If we apply this to IP, we can look at a Class A network, which has 10.0.0.0 and a subnet mask with a /8. But if we wanted to cut that pizza into smaller pieces, we might have a subnet mask of a /24 or even a /26. Since we're using a different number of bits than 8 in the subnet mask, we're using a variable length subnet mask that we can define to be whatever we'd like. Let's perform some of this variable length subnet masking, but let's first look at the default subnet mask for a Class A address. This would be 10.0.0.0. The default is Class A, since that starts with the number 10, and the default subnet mask for that would be 255.0.0.0. This would be the default subnet mask if all we did was have classful addressing. If you were to look at this classful address in binary, the first 8 bits would be 1, and the remaining bits would be 0. In decimal, that means it would be 255.0.0.0, and if you were to use the cider block notation, this would be a /8 subnet. This means that the network bits would be those first 8 bits of the address, and the host bits would be the last 24 bits of the address. Since this is a /8 subnet mask, we are drawing our line after those first 8 bits of the subnet mask. But in reality, of course, we could pick a different number of subnet bits. We just need to decide what works best for our network. For example, let's draw our line right after the third octet. This means that we still have our default first 8 bits as part of that class A address, but we're going to borrow the middle 16 bits as what we call our subnet bits. This means those subnet bits would now be turned into 1, and the host section of the IP address would shrink down to 8 bits. This means that the decimal subnet mask would be 255.255.255.0, and the CIDR block notation for this new subnet mask would be /24. We've been doing a lot of these calculations in binary, and then we've been converting that binary back to decimal. But that process tends to take time, and one of the faster ways to perform these calculations is to look at a list of the powers of 2. For example, you can look at 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, and so on. If you want to calculate the number of subnets and the number of hosts, you can calculate the number of subnets as 2 to the number of subnet bits, and the number of hosts per subnet would be 2 to the number of host bits minus 2. That subtraction for the 2 means that we are subtracting the number that we would use for our network address and the number that we would use for our broadcast address. Everything in the middle would be our host addresses. So let's now use this chart with our powers of 2 to calculate the number of subnets and the number of hosts per subnet. Let's take the IP address of 10.1.1.0/24. If we perform our calculation in binary, we would write out all 24 of those bits as 1s, and the last 8 bits would be 0. The default for a class A address such as this one, though, would normally have our network address as the first 8 bits. But we are moving that line another 16 bits over so that we are borrowing an additional 16 bits for the subnet. That leaves us with 8 bits left over for the host. If we were to calculate the number of subnets using these powers of 2, we would take 2 to the number of subnet bits. And since we have 16 subnet bits, 2 to the power of 16 is 65,536. If we were to calculate number of hosts per subnet, it's 2 to the number of host bits minus 2. We have 8 host bits, which means 2 to the 8 minus 2 is 256 minus 2, or 254. So for this IP address of 10.1.1.0/24, we can have a maximum number of subnets of 65,536, and on each of those subnets, we can have a maximum of 254 devices. Let's calculate another one. We'll look at an IP address of 192.168.11.0/26. If we were to write out that /26, you can see there are 26 ones. That leaves us with 2 ones in the last octet, and we have 6 zeros left over at the end. If we calculate the class of this address, we look at the first octet, which is 192, which means this is a Class C address. That means it has a total number of 24 bits as the network address by default. But we borrowed a couple of extra bits into the last octet, so there are 2 additional bits available that we will call our subnet bits. And then, of course, we have the last 6 bits available as the host bits. Let's perform our calculation again. To calculate the number of subnets, we use 2 to the number of subnet bits. We have 2 bits left over as the subnet bits. 2 to the second power is 4. To calculate the host per subnet, we have 6 bits, so we take 2 to the 6th power and subtract 2 from there. That means we have 64 minus 2, or 62. So for this IP address of 192.168.11.0/26, we can create a total of 4 subnets, and on each of those subnets, we can have a total of 62 devices. This same process works with any type of subnet mask. Let's take, for example, 172.16.55.0/21. If we looked at this in binary, we would have 21 ones, which means we have 8 in the first octet, 8 in the second octet, and 5 ones in the third octet. Everything else, of course, would be zeros. And if we look at this IP address, it starts with 172, which by default would be a Class B address. So by default, the first 16 bits would be your network address. We borrowed some additional bits, in this case, 5 additional bits to be our subnet bits, and then everything left would be our 11 host bits. Performing our calculation again, we have 5 subnet bits, so to calculate the number of subnets, it's 2 to the 5th power, or 32. We have 11 host bits left over, so if we calculate that as 2 to the 11th power minus 2, that would be the same as 2048 minus 2, or a total of 2046 devices. So for this IP address of 172.16.55.0/21, we can have a total of 32 subnets, and on each of those subnets, we can have a maximum of 2046 devices. If you use this powers of 2 to perform these calculations, it can be a very quick way to determine what the number of subnets might be and what the host per subnet might be. But there are some shortcuts available that might get you to these values much faster, and in the next couple of videos, we'll give you some different options for calculating this process using those shortcuts. If you've been with us with the videos just prior to this one, then you've learned a lot about subnetting, masks, cider block notation, and other important fundamentals when it comes to subnetting via IP version 4. All of that work has brought us to this point where we can start to answer questions like this one. Here's a network layout, and it says, here's your IP address assignment. We've been given the IP address of 192.168.1.0/24. And this says we need an IP addressing scheme with more than one network address that can support 40 devices per subnet. That is the optimal number we're looking for, and we need to determine how to subnet this network address to be able to get 40 devices per subnet. Now, you could, of course, write out all of the possibilities in decimal and binary and be able to calculate what the differences are with the number of networks and the number of hosts per network. For example, if you look at the default subnet mask that we were given, which is 255.255.255.0, you can see this is the binary representation of that subnet mask, and the CIDR notation, which is a /24. That gives us one single network with 254 hosts per network. If we borrow one bit from the host side, so that we are at 255.255.255.128 as our subnet mask, or a /25, we would be able to create 2 networks with 126 hosts per network. We are getting closer to that number of 40. Let's keep going by borrowing another bit so that our subnet mask is 255.255.255.192, or a /26. This allows us to have 4 networks with a total of 62 hosts on each of those subnets. This is certainly getting close to 40, but let's go one more step to see if we're getting even closer to that 40 value. The next step would be to borrow one more bit from the host side, so now we're borrowing 3 subnet bits, which means our subnet mask is 255.255.255.224, or a /27. If we subnet in this way, we can have a maximum of 8 networks, but it would only allow for 30 hosts per network. This means that the optimal subnet mask, if we're looking for a total of 40 devices per subnet, would be the next one up, or the /26, which would give us 4 networks and a maximum of 62 hosts per network. Now, we can certainly speed this process along by performing a calculation based on powers of 2. Let's look to see how we might do that. We have a starting IP address of 192.168.1.0 and a subnet mask of 255.255.255.192. And based on this information, we can show the network address and the subnet mask in binary. And you'll notice in the subnet mask, we have the default number of bits for that address, plus the 2 extra bits that we borrowed from the host side. Visually, you can see where the 24 subnet bits might be, the 2 extra bits we borrowed for the subnet, and the 6 bits that are left over on the host side. If we were to now calculate the number of subnets and the number of hosts per subnets using this powers of 2 formula, we would take 2 to the 2nd power, because the 2nd power would be 2 bits, and that would be a total of 4 networks. We would determine the number of hosts per subnet by taking those 6 host bits that are left over at the end and calculating 2 to the 6th power minus 2, which would be 64 minus 2, or a total of 62 hosts per subnet. This is a relatively straightforward way to calculate the number of subnets and the number of hosts per subnet, but it requires you to perform a binary conversion and then count the number of bits to be able to calculate what that total might be at the end. There are some shortcuts that we can use, and in this video, we're going to look at a shortcut that uses the magic number method. These calculations are intended to give us 4 separate pieces of information. First, we need the network address or subnet ID. This would be the first address in the subnet. We also need a broadcast address. This is the last address in the subnet. We need the first available host address. This is an address that we can assign to a device on this subnet. And then we need the last available host address. We need to be able to calculate these as quickly as possible. Now, obviously, we can calculate this by converting everything to binary, looking at the subnet bits, and then calculating for every possible scenario what this particular network address might be and the subnet mask for each one of these. And for this particular IP address, where we determined there were 4 separate subnets, these are all the calculations that we would need to do to be able to calculate all of that information for all 4 of those subnets. You can see, looking at this screen, that there are a lot of separate binary to decimal conversions you have to do just to calculate those specific details for all 4 of those subnets. We can simplify this process by using the magic number shortcut. This allows us to perform subnet calculations very quickly, and very often we can do all of these calculations in our head. There's still a little bit of math involved with the magic number method, but it's limited to powers of 2 and some very simple addition and subtraction. You could even create a few charts that might help you with the process, but once you get accustomed to using this method, you'll find that you memorize very easily what's in the charts. You may not have to write them down at all during your exam. One chart that might help you is a chart that easily converts between a cider block notation and the decimal subnet mask notation. You can see an example of this might be to use a /9 is 255.128.0.0, /10 is 255.192.0.0, and so on. You will notice that there are some patterns after a while. For example, a /9 has the 128 as the number that is a bit different than a 0 or a 255, and a /17 also has a 128. So we could write this chart in a simplified form that shows a /9, a /17, and a /25 use the 128 as the decimal value. In the magic number method, we have a number of different tasks that we perform based on the octet that we're working with. So we might want to modify this cider to decimal chart to have something that's a little bit different. For example, if you wanted to see the cider notation for interesting octet 2, you can see it ranges from a /9 through /16. The cider block notation for interesting octet 3 would be /17 through /24, and the cider block notation for interesting octet 4 ranges from /25 to /30. You notice that we don't use /31 by default because it doesn't leave any room for any hosts on the subnet, and we don't use a /32 because that leaves 0 bits available for any hosts. For each of these columns with the cider block notation, you'll notice there is a magic number, and in a moment we'll learn how to use that magic number value. We can also put in this chart the subnet mask for an interesting octet, and you can see those mask values are also listed as well, starting at 128 and working all the way up to 255. Optionally, you can also create a host range chart where you can take an address block and then separate out what the differences are for that particular block. For example, an address block of 128 splits the network into 2 different pieces, 0 through 127 and 128 through 255. An address block of 64 hosts per block would be 0 through 63, 64 through 127, and so on. And you can continue this process with a host block of 32 hosts, 16 hosts, 8 hosts, and so on. So let's see how the magic number method works. It's a series of steps, and once you go through these a couple of times, they become very second nature. The first step is to convert the subnet mask to decimal if it's not in decimal already. From there, we need to identify the interesting octet. We'll talk about the interesting octet in just a moment. We then need to calculate the magic number, which is 256 minus the value this IP address of 165.245.77.14, and we've been given a subnet mask of 255.255.240.0. Our first step would be to put the subnet mask into the chart. You can see that it's already in decimal form, so we simply need to copy it over with 255.255.240.0. We can then also fill in the IP address that we've been given, which is 165.245.77.14. From here, we can start to make some decisions about what to put into this chart. For example, if the mask is 255, we simply copy the IP address down. So in this case, the mask is 255 in the first octet, so we're going to copy that down, which means our subnet ID will be copied down with the same number that's in the IP address row. Let's perform that same task again with the second octet. It is also 255, so we're going to copy that through. This 245 then will be brought down into the subnet ID row. We no longer have any octets with the 255, so our next step will be to look at any octets where the mask is 0. And if the mask is 0, we bring that 0 down to the subnet ID row. In this case, our last octet does have a 0, so we're going to copy that 0 all the way down and put it into the subnet ID row in the last octet. In our example, the subnet mask in the third octet is a 240. It is obviously not 0 and not 255, so that octet is our interesting octet. Now that we know the interesting octet, we can use that to calculate the subnet ID value for that particular octet. To be able to do that, we need to subtract the interesting octet subnet mask from 256. In our interesting octet, the subnet mask is 240. So if we subtract 240 from 256, we have the value of 16. This means our magic number is 16, and there would be 16 hosts available on that particular subnet. If we put our chart at the bottom that shows the 16 different hosts that you would have and the delineation between each one of those subnets, you can see that we have a range between 0 and 15, 16 through 31, 32 through 47, and so on. Now, if we look at the IP address, we can see the IP address is 77. And if we look at our chart, we can fit the 77 IP address in the range between 64 and 79. Since we're trying to determine the subnet ID, we take the very first number in that particular range, which would be 64, and we add that 64 into that subnet ID in our interesting octet. So for the IP address 165.245.77.14 that has a subnet mask of 255.255.240.0, the subnet ID is 165.245.64.0. Of course, not only do we need to know the subnet ID, but we also need to know the broadcast address. To calculate the broadcast address using the magic number method, it's a very similar process. We use the same chart with the same subnet mask and the subnet ID, but at the very bottom, we have broadcast address instead of subnet ID. The rules for determining the broadcast address are very similar to the rules we used for the subnet ID. If the subnet mask is 255, we copy the subnet ID all the way down into the broadcast address row. We have two of our octets that show a 255, so we'll do this for the first and the second octet. Here's where the rules are a little bit different when calculating the broadcast address versus calculating the subnet ID. If the mask is 0, we're going to write into that column a 255. And of course, if the subnet mask octet doesn't contain a 0 and it doesn't contain a 255, then that octet is our interesting octet. This will obviously be the same interesting octet when we're calculating the broadcast address as it was when we were calculating the subnet ID. To calculate the magic number, we perform the same process that we did earlier. We take 256, we subtract from that the value that's in that interesting octet mask, leaving us with a magic number of 16. To calculate the broadcast address for that interesting octet, we take the subnet ID and we add the magic number and subtract 1. So in this example, we use 64 because that is the number in our subnet ID. We add 16, which is our magic number. We subtract 1, and that leaves us with 79. So in this example, the broadcast address is 165.245.79.255. Now that we know the subnet ID and we know the broadcast address, Calculating the first available IP address and the last available IP address is relatively straightforward. To calculate the first host, we would take the subnet ID and add 1. So the first address on the subnet is 165.245.64.1. To find the last usable address on this subnet, we take the broadcast address and subtract 1. So the last usable address on this subnet is 165.245.79.254. And that is the magic number process. Without doing any type of conversions between binary and decimal, we were able to calculate the subnet ID, the broadcast address, the first available IP address, and the last available IP address. Let's see how well we can use this magic number method with another example. We'll use the IP address of 10.180.122.244, and the subnet mask is 255.248.0.0. We will first fill in our chart, so we'll put our subnet mask in that mask row, and we'll put our IP address in the IP address row. We'll now look at our subnet mask, and everywhere there's a 255, we will use that to copy down the IP address. So in this case, in the first octet, we'll copy down that value of 10. Every place there is a 0, we're going to copy down the 0 and put that into the subnet ID row, and the third and the fourth octets both have a 0. Since we don't have a 0 or a 255 in this second octet, that means that this octet is our interesting octet. To calculate the magic number, we use 256, subtract the value that we have in that subnet mask range, which means we use 256 minus 248. So in this example, our magic number is 8. This means that each subnet has a total of 8 IP addresses that can be assigned, including our subnet ID and our broadcast ID. And we put the chart at the bottom that separates this into those multiples of 8. Now we need to find the IP address that is the starting for this particular block. If we look at our interesting octet, we know that the IP address is 180. So if we look at our chart, we can find that 180, which is in the block starting with 176. Since that starts with 176, we can simply fill that in, which means the subnet ID for this example will be 10.176.0.0. Now we need to find the broadcast address for this example. We'll use a similar process we did before, where if we had a 255 in the list, we're going to copy and bring down that subnet ID. So the first octet will simply copy down the number 10. Anywhere that we have a 0, we're going to copy down and put a 255. We have zeros in both our third octet and our fourth octet. As we already know, the second octet is our interesting octet. So we're going to perform our calculation, taking 256, subtracting 240.
All right, everybody, welcome back from lunch. We'll go ahead and continue working on some coursework.
Obviously the same magic number.
Do you study into his practice test at 2? It's just 2 o'clock now. At 3 o'clock, we'll go into domain 2. Domain 2.
So the example here would be 176 plus 8, since that's our magic number. And if we subtract 1, that leaves us with a number of 183. We'll add this to our broadcast address row, which means the broadcast address for this example is 10.183.255.255. Now that we've calculated the subnet ID and the broadcast address, it's relatively easy to determine the first host ID because we take the subnet ID and add 1. So the first available host on the subnet is 10.176.0.1. To determine the last address, we take the broadcast address and subtract 1. So in this case, it would be 10.183.255.
Don't forget to clock back into class.
Hopefully now you can see that the magic number method is a bit faster than going through the steps of converting to binary and then back to decimal again. But there are some ways to make this process even more efficient. If you've already created a chart that shows all of the possibilities of an interesting octet cider block notation and has the magic number predefined along with the subnet mask for the interesting octet, you can perform this entire process in one single chart. Let's take the example of 172.16.242.133/27. If we look at our predefined chart, we know that /27 falls into the cider block notation for interesting octet 4. This means that octet 4 will have a decimal value of 224. So if we wanted to write out the entire subnet mask, it will be 255.255.255.224, because because 224 is in that interesting octet number 4. The process for calculating the magic number is exactly the same as it was before. We take 256, we subtract that subnet mask in the interesting octet, which in this case is 224, which means our magic number is 32. There are 32 available addresses on each subnet of this particular IP address and subnet mask combination. Here's our chart, which is written out with 32 numbers in each of those sections. And if we look at our IP address that has a 133, we can move forward to where the 133 would be, and it is in the block that starts with a 128. Since we know it starts with a 128, that means that we can now change our fourth interesting octet to be that value as the subnet ID. So the subnet ID in this example would be 172.16.242.128. If you recall from our earlier calculations, to be able to calculate the broadcast information, we need to take the subnet ID value in the interesting octet, add that to the magic number, and subtract 1. So we'll take 128, we'll add 32 to make 160, we'll subtract 1, and that makes 159. So the broadcast address on this subnet is 172.16.242.159. Now that we know the subnet ID and the broadcast, we can calculate the first available IP address and the last available IP address. We add 1 to the subnet ID to determine the first IP, so the first IP would be 172.16.242.129. If we subtract 1 from the broadcast address, we would get 172.16.242.158. So there is the faster way to be able to calculate our subnet ID, our broadcast address, the first IP address, and the last IP address using the In previous videos, we've gone through the process of manually converting an IP address and subnet mask to binary, performing the proper calculations, and converting it back to decimal. We also looked at a shortcut called the magic number method that allows us to very quickly calculate the same information without performing that binary to decimal conversion. This shortcut is the 7-second subnetting shortcut, and this is the process that I use when calculating subnetting on an exam. This is a process very similar in structure to the magic number method, and indeed most of the shortcuts you find will have some variation of this within them. The part that's very different to the 7-second subnetting is that there is no math involved. You don't have to perform any calculations to determine a magic number, and everything you need will be predefined in the chart that we create at the very beginning. You'll find that the only math you end up doing is adding and subtracting the value of 1 to be able to calculate the first IP address and the last IP address. This is one of many available shortcuts to help you with the subnetting process, and I highly recommend you look at a number of different ones to find one that works for you. This 7-second subnetting process works equally well whether you are online taking this exam and using the online whiteboard, or if you have a physical whiteboard in front of you at a testing center. The process of calculating the subnet is really about splitting the network into smaller pieces. You may start with a network that has 256 total hosts available, or you might break it up into smaller subnets such as a .128 where you might have 2 different subnets, a .192 which separates it into 4 different subnets, a .224 that separates it into 8 individual subnets, and so on. The core to the 7-second subnetting process is creating this chart. We will start with a chart that defines the subnet masks. This allows us to very quickly determine what the decimal mask might be if we're given a CIDR block notation and vice versa. You can see this is very similar to the chart you would create with the magic number method. We're simply performing the same math on the 7-second subnetting. We also have a networks column. You would calculate that by starting with the number 2 and doubling it all the way up until 256. And then you have an addresses column which starts with 128, and you would divide by 2 all the way down until you get to the number 1. And to help with the conversion between the CIDR block notation and the decimal mask, we have a subnet mask in decimal column that we'll add in as well. Once you've created this chart, you have everything you need to be able to calculate everything necessary for a subnet without having to perform any type of additional math. If you're like me and you have problems determining what the start of a subnet might be on a subnet that has 16 hosts or 32 hosts, you may want to write out those subnet boundaries into a separate chart so you can very quickly find what those might be during the process of performing your calculations. For example, a network that has 128 hosts per network would have host boundaries at 0 and 128. A network that has 64 IP addresses per subnet has network boundaries at 0, 64, 128, and 192. And you can calculate similar boundaries for networks with 32 IP addresses, 16, 8, and 4. The 7-second subnetting process is a 4-step process. The first step is to convert the IP address and the subnet mask to decimal. This is necessary if you're provided the subnet mask in CIDR block notation, but fortunately we have a chart that can very quickly translate between CIDR block notation and decimal. The second step is to determine the subnet address. This is something you may be able to do in your head, or if you're like me, you've written out that second chart that shows you where the delineations are for each individual subnet. That same chart shows us what the broadcast address might be, because we can simply look at the last address in that particular range. And from there, it's very easy to determine what the first and last usable IP addresses might be by adding 1 to our subnet address and subtracting 1 from our broadcast address. Let's use this process to subnet 165.245.12.88/24. The /24 needs to be converted from the CIDR block notation into decimal notation. You may be able to do this one in your head very easily, but you can also reference your chart by finding the /24. You can see that our chart shows the /24 as part of that third octet, and it shows that that third octet will have a mask of 255. Everything after that will have a mask of 0. So performing that calculation means that our subnet mask is 255.255.255.0. Now we need to calculate the network or subnet address. If the mask is 255, we need to bring that address down. And if the mask is 0, we're going to simply bring down a 0. So if the mask is 255, we bring down the address. And you can see in the first, second, and third octets, the mask is 255. So we'll bring down the 165, 245, and 12. And if the mask is 0, we bring down a 0. So in this example, our network address is 165.245.12.0. To calculate the broadcast address, we look at the subnet mask again, and if it's 255, we bring down the address number. If the mask is 0, we use 255. In this example, the first, second, and third octets all have 255, so we will bring down our address numbers as 165.245.12. And if the mask is 0, we bring down 255. So in this case, the last octet does have a mask of 0, and we'll put a 255 in that last octet for the broadcast address. Now that we have our network address and our broadcast address, it's relatively easy to calculate the first available IP address and the last available IP address. To calculate the first IP, we take the network address and we add 1. So that would be 165.245.12.1. And the last IP would be the broadcast address minus 1. So that would be 165.245.12.254. There is the 7-second subnetting process using our chart and using those simple rules to be able to define the network address, the broadcast address, the first available IP, and the last available IP. Let's do another example that doesn't fall on those simple 8-bit ranges of the subnet mask. We're going to use the same IP address, but with a different subnet mask. In this case, it will be 165.245.12.88/26. The first step will be to take the /26 CIDR block notation and convert that mask to decimal. If we look at our chart, we can find the /26, and we can see that it is the 1, 2, 3, 4th octet, and in that 4th octet, we want to put a 192 decimal. That means that our subnet mask is 255.255.255.192, which is the conversion from the /26. If we look at our chart where it has the /26 or the 192, you can see the number of addresses is 64. And since our IP address has an 88, we can look at the different blocks in those 64 ranges to determine where the 88 might be. And in this case, it's in the range that starts with the block of 64. We'll follow the same rules we had before. If the mask is 255, we're going to bring down that address. And if the mask is 0, we're going to bring down a 0. In this example, we have 3 masks that are 255, so we'll simply bring down the address values for each of those octets. In this last octet, the mask is 192. If we refer to our chart, we can see that we have that range of 64 addresses. We look at our IP address of 88 and determine in which one of those 64 address blocks 88 might be, and it's in the range that has 64 as its starting point. This is what we're going to bring down into the 4th octet, is that value of 64. To calculate the broadcast address, we look at the subnet mask again, and if it's 255, we bring down the address values. If it's a 0, we use 255. In this particular case, our subnet mask does not have any zeros, so we need to refer to our chart. Again, we know that this is the range with 64 addresses per subnet, and we know that .88 fits into that second block. We know looking at the chart that the next block starts with a 128, which means that the broadcast address must be the one prior to that number, so that would be 127. So the broadcast address is 165.245.12.127. And of course, to calculate the first usable IP address, we add 1 to our network address, so our first IP is 165.245.12.65. The last IP address is determined by taking the broadcast address and subtracting 1, so that would be 165.245.12.126. We can perform this same shortcut with any IP address and subnet range. Let's take the example of 165.245.12.88/20. If we look at this address, we take the /20 and convert it to a decimal subnet mask. We can determine this by finding the /20 in our chart. It is in the 3rd octet, and that 3rd octet will be a 240. So everything to the left of that will be 255s, and everything to the right will be zeros. So our subnet mask of a /20 is the same as a 255.255.240.0. You also notice in this chart that the number of addresses in each of these subnets will be 16 addresses. And if we look at our chart, we know that we have an address that has 165.245.12.88. So we need to determine where the .12 might be in our list. That .12 fits between the 0 and 16, so it's this very first subnet that we're going to look at in this particular range. Let's calculate our network address. If the mask is 255, we bring down the address, and if the mask is 0, we use 0. In this case, we have a 255 in the first 2 octets and a 0 in the last octet, so we simply bring down each one of those. Since we're looking at the range that has the .12, and we know that there are 16 hosts on each of these subnets, then that .12 is in that range between 0 and 16, and the first number being 0 means that that is our network address, and so we'll bring that down as our 3rd octet. This means that our network address is 165.245.0.0. To calculate the broadcast address, we look at every place there's a 255, and we bring down that address, so that would be our first 2 octets. And if there is a 0 as part of the subnet mask, we use 255, and we'll bring down that 255 for the 4th octet. Since we have a 240 as the subnet mask in that 3rd octet, we need to look at our chart again and determine what number we would bring down. Since we know there are 16 addresses in each of those blocks, we know that the next subnet will start with a 16, so one number prior to that 16 would be a 15. And the broadcast address for this subnet is 165.245.15.255. Now we can calculate the first available IP address by looking at the network address and adding 1. That would make it 165.245.0.1. And we can calculate the last available IP address by subtracting 1 from the broadcast, and that would be 165.245.15.254. Let's go through the process again with an IP address of 18.172.200.77/11. First thing we're going to do is convert that /11 to a decimal mask, and if we look at our chart, we'll find the .11 is in the 2nd octet, and it has a value of 224. So our subnet mask is going to be 255.224.0.0. On the same line as that subnet mask is the number of addresses, and you can see in this particular example, there are 32 addresses per subnet. Since that /11 is in the second octet, we're going to look at that IP address to determine where it fits in those blocks of 32 IP addresses. So if we were to look at our chart of these 32 address blocks, we know that 172 fits in this range between 160 and 191. So to calculate the network address, if the mask is 255, we're going to bring down the 18 that's in that block. And if it's 0, we're going to bring down zeros. And since this block starts with a 160, our network address is 18.160.0.0. To calculate the broadcast address, if the mask is 255, we bring down the address. And if the mask is 0, we use 255. This means in the first octet, we'll simply bring down the 18. And in the third and fourth octets, where the mask is 0, we'll write 255. In this third octet, we'll go back to our chart, and we know that's the range between 160, and in this case, the next range starts at 192. Therefore, the broadcast address for the previous range would have to be 191. And to calculate the first and last available IP addresses, we will add 1 to the network address and subtract 1 from the broadcast address, meaning the first IP is 18.160.0.1, and the last available IP address is 18.191.255.254. Let's perform one more calculation to see how well we've captured this shortcut. We'll use the address of 18.172.200.77/17. If we go to our chart, we can find the /17 is part of the third octet, and it matches that 128 value as the decimal part of the mask. So if we were to write out the mask, it would be 255.255.128.0. If we were to look at our chart, that /17 is on the same line as blocks of 128 hosts. So we know that there were 128 IP addresses in each one of these subnets. So let's calculate from there what the network address might be. If the mask
Is
is
your hours
255,
as
we
of
write
the
down the address
punch
value. If
to
the mask is
lunchtime?
0, we will use 0. To calculate the broadcast address, we look at the subnet mask, and if it's 255, we bring down the address, and if the mask is 0, we use 255. In this example, we have subnet mask of 255 in the first two octets, so we'll bring down those address values. We have a 0 in the fourth octet, so we'll use 255. In this example, that value of 200 is in that third octet, which puts us in the second block, starting with 128 and ending with 255. So in this case, the broadcast address would be the last address in that block, which is 255, meaning your broadcast address is 18.172.255.255. And of course, to calculate the first IP address, we add 1 to the network address, making it 18.172.128.1, and we calculate the last IP by subtracting 1 from the broadcast address, making the last IP 18.172.255.2.
So as a reminder, you would just need
As you
the
can probably
hours
tell, the key to
as
this
far as
7-second
percentages
subnetting process is
have to
being
be
able to
above
reference that chart. So you might want to try writing this down in a
83.20
chart
by
if you're
6
going to be in a
p.m.
testing
today
center,
to
or you may
be
want
on
to try
track for
typing it
passing.
into a notepad or WordPad to see how quickly you can type
So,
it in if you're going to be taking
You're
the
right.
exam
I mean,
online.
would it still make
If
sense
you
to
go
just
to
stay
a
in the
testing
course?
center, you may find that the
say
dry
what?
erase pins that they
If
use
you aren't
may
like
not allow you to make a
close or
very
above those
easily
hours,
readable
would it
chart.
make
So you
sense
may
just to
want
stay
to
in the
bring your
course?
own
Did
pen.
you do anything?
Make sure you check with the testing center that it's okay to bring your
No,
own
you
fine
what
tip
happened is
dry
if you
erase
ever had
pen
to, if you
into
failed
the
because of
testing center.
hours,
And whether your
you would just
shortcut
have to
is
repeat
the
the course.
7-second subnetting process, the magic number process,
VA
or
VA
any other
usually gives you one
process,
shot to
make sure
repeat
you
the
find the
course
shortcut that
without
works best
question.
for you and
Yeah.
decide to use that for your exam.
Yep. You'll fill out a form to say this is why I couldn't. This is what happened. I mean, you still have to fill that out, but other than that, yeah, the VA's good for giving you one shot to say, oh, okay, you were just off this course. You just got to do it again.
One of the
So I can stay here
challenges with
longer?
the virtual world is we have to somehow
Yeah.
take the
Well, you
functions
wouldn't get
that we
me.
would
You get
normally
somebody
use in
else.
our physical devices and move it
Hmm.
into a more virtualized environment. This challenge
Okay.
exists
Oh, man,
for
look
our
at Mike. He's
servers
like
and
formulating
operating
a plan.
systems, but it also exists for our routers, switches, and other networking devices. If we were to break out the different functions of these networking components, we would see there was a data plane, a control plane, and a management plane. If we could take those individual functions that are handled in hardware and create virtualized software versions of each of those, we would be able to deploy this nearly anywhere in a virtual environment. This would not only provide us with a way to create these virtualized systems, but it would also give us additional functionality on the network. If we were to take a switch or a router and look at how that device functions and how it forwards data, we would categorize that particular capability into the infrastructure layer, or the data plane. This is the part of the device that does the heavy lifting. It does the forwarding of traffic, it transfers information from one interface to another, and it provides forwarding, trunking, encrypting, and network address translation. These networking devices also need to reference other data to determine how to perform this function in the data plane. This ability to control where the data may be going is part of the control layer, or the control plane. So if you look at routing tables, switching tables, network address translation tables, or anything else that determines how this device functions, it's probably located in the control plane. And ultimately, you as the network administrator will need to manage this device. We do this through the application layer, or the management plane. Anytime you SSH it to a console or control a device from a web-based front end, you're using this management plane. So let's take a physical networking device and turn it into this software-defined networking device. Let's start with a physical firewall. Firewall generally has functionality within it to be able to connect different networks together. We have logic inside that is able to determine how information is forwarded from one interface to another, and we have ways to manage the device on the front console or through a web-based front end. We'll start with all of the interfaces on the front of the firewall, where we will connect all of our networks. This is the data plane, or the infrastructure layer, and this is where all of the data is forwarded from one interface to another. Inside of the firewall itself, we have tables that allow us to control what traffic is forwarded and what traffic is not forwarded. We might also keep routing tables or switching tables inside of this control plane. And anytime we're managing the device, either by connecting directly to the console or through a web-based management front end, we are using the management plane. One of the ways that we're able to take advantage of this software-based networking functionality is through the use of an SD-WAN. This stands for Software Defined Networking in a Wide Area Network. This is a wide area network that was specifically built to manage the complexities of a cloud-based environment. We've created this SD-WAN because we've changed where we manage and connect to all of the different resources on our network. We used to have everything in one data center, and anytime we needed to access our email or perform a query on a database, we simply access those resources in our existing data center. But now we've taken those email services and we put them into the cloud. We've taken our applications and we've also moved those to the cloud. It's now not quite as simple as connecting to a central data center to gain access to all of our resources, because our emails, databases, and other applications might exist anywhere in the cloud, and that location may change at any time. Here's a view of what we had before the cloud, where all of our services were in one centralized data center. If we had remote locations, we would simply have wide area network links from that remote site to our centralized data center. This made it very easy to set up wide area network connections. That connection was always connected between the remote site and the data center, and that provided everyone with access to the data that they needed. But now we've moved much of that data from our data center into the cloud. So the cloud may have databases, it might have web services, it might have our email access, and these cloud-based services may be located in multiple cloud providers anywhere in the world. SD-WAN was created because we needed some type of wide area network that was application aware. It would know if we were using email, and it would be able to immediately send our data to the closest email service specific to us. An important characteristic of an SD-WAN is its ability to know what application is being transmitted through the network. If it knows the application, it will know where to forward that application data to gain access to an email, a database, or some other application. Since these cloud-based services can move anywhere at any time, we need all of the systems that are connected to this wide area network to automatically update themselves anytime there happens to be a change. This is called zero-touch provisioning, and allows us to have all of our remote routers and switches know exactly how to reach those services wherever they might be and wherever they might be moved. This means if anything changes with the network or anything changes with the location of these services, our SD-WAN routers will automatically update themselves without any type of user intervention. We also need to keep in mind that the connectivity to these sites may be very different based on the cloud provider. Some cloud providers might be accessible through high-speed fiber, whereas others may be connected through 5G or DSL type connections. For that reason, SD-WAN is designed to be agnostic to the transport type, so no matter how you're connected, we'll be able to connect to that remote location. And instead of configuring the policies used for this network through each individual SD-WAN router, we have central policy management where we make all of those changes on one central management console, and those changes are pushed out to all of those SD-WAN routers automatically. So if there are resources in the data center that need to be accessed from a remote site, those locations can still go directly to the data center. But if someone in a remote site needs to access a database or their email system, they can go directly to that cloud-based service using this SD-WAN technology. Many organizations will distribute their applications, their servers, and other devices across many different data centers. Instead of treating each of these data centers as an individual entity, it would be useful if we could have data center interconnection, or DCI, a way to connect these different data centers seamlessly with each other. If you're a service provider, you may have hundreds or even thousands of customers using resources that span across multiple data centers located anywhere in the world. And of course, we use the cloud to distribute our applications to multiple data centers that may be located in many different locations, and those applications may move at any time to any of these cloud-based data centers. When you have devices located,
that's one thing employers have liked, at least the ones I've applied to and gotten to at least their first interview.
Those different data centers.
It's because
one IP addressing scheme for
you took the time to read the website.
Completely different IP addressing scheme.
Like every area, the about page, HR, Glassdoor, how many people work there, retention, average salary. They love that stuff. They're kind of like, what? Because it's attention to detail. You're just not throwing out resumes and not doing the homework. You're just trying to see what sticks to the wall. That's just my personal opinion. I may not have gotten the job with the company, but I've gotten their attention for at least the first interview or second interview.
Application should work without any type of issue. We need a way to seamlessly connect these data centers together without a concern about IP address schemes or the underlying network infrastructure. The solution to this problem is a virtual extensible LAN, or VXLAN. This technology was designed to support thousands of different customers, all using the same data centers located across the world. You may already be familiar with VLANs, or virtual local area networks. VLANs are designed to span across multiple switches at layer 2 so that you can have different areas of the network supporting the same IP subnets. Unfortunately, VLANs have a limited scope because they can only support around 4,000 different virtual networks, and they are limited to layer 2, which makes them non-routable. With VXLAN, we can support up to 16 million virtual networks, and those virtual networks can be connected to each other over a layer 3 network, which makes it very easy to route over the existing public internet. This is designed for the large virtual environments that we've created and allows us to support our applications wherever they might be. Let's take a scenario where we have two data centers. In one data center, we have a virtualization server. Inside of that virtualization server is a virtual switch and 3 separate virtual machines, A1, B1, and C1. In a different data center, we have a similar virtualization server with its own vSwitch and a virtual machine A2, B2, and C2. And in this example, virtual machine A1 is associated with virtual machine A2, virtual machine B1 is associated with B2, and virtual machine C1 is associated with virtual machine C2. This virtualization server is contained within a rack that has a top-of-rack switch that contains a VXLAN tunnel endpoint. In one data center, that VTEP is numbered 1.1.1.1, And in a different data center, there's a completely different IP address for this VTEP of 2.2.2.2. Notice that both of these VXLAN tunnel endpoints will support a VXLAN network identifier, or VNI. You can see there is a VNI 2000, a VNI 3000, and a VNI 4000 in both of these data centers. So the challenge is connecting VNI 2000 in one data center with VNI 2000 in another data center, VNI 3000 in one data center to the other, and VNI 4000 in one data center to the other. The way that we would accomplish this is through the use of a VXLAN tunnel. This uses an existing IP network to be able to provide the transportation, and we're able to encapsulate information in one data center, send it through this tunnel, and decapsulate it on the other end. Here's how this would work. We have our original frame in the first data center. This is a standard Ethernet frame with an Ethernet header, an IP header, and the payload that we would like to send to the other data center. We're going to encapsulate that original frame within a VXLAN header that sits inside a UDP header, and an IP header, and an Ethernet frame. This information is routed across a VXLAN tunnel, where on the other side it is decapsulated from the tunnel, and the original Ethernet frame is then in the second data center and added to the existing virtualization server. This allows us to connect virtual machines in two completely different data centers, but still have those virtual machines feel that they are both directly connected to each other. Traditionally, we've always done a good job at protecting the edges of our network. This allowed us to control who may be entering the network and who might be leaving the network. But once you're on the inside, all of the network tends to be very accessible. This obviously creates security concerns if you want to be sure that you have the highest level security on your network. In recent years, many companies have transitioned to more of a zero trust approach. This is a holistic approach to security that affects every user and every application being used on the network. With zero trust, every user, every device, and every application is inherently untrusted. We want to check and verify any type of traffic going over our network to ensure that only the right users are accessing the right type of data. This means that we'll be implementing technologies inside of our network such as authentication, encryption, additional firewalls, monitoring of this network, and many other security controls. When you connect to a resource, there's generally an authentication process that occurs. There's usually a username and a password that you have to enter, and there may be additional authentication factors as well. Many organizations may also create a policy-based authentication, and one of the characteristics of that is an adaptive identity. With an adaptive identity, every authentication process considers who's trying to authenticate to the network. Is this an individual who's been employed with the company for 10 years, or is this a vendor who just started working with the company only a few months ago? We might also consider where this person may be authenticating from. Are they located in our local geographic area, or are they trying to authenticate from a different country? We might also evaluate the IP address that's in use and the type of connection that's being used during this authentication, and we might want to combine all of those together to determine how risky this authentication process might be. If a user's inside of the building, they may only need to use a username and password. But if they're coming from an unknown IP address in a different country using a VPN connection, we might want to require additional authentication factors. We might also want to add additional rules and processes based on the information we're gathering during this authentication process. If someone is using the correct username and password, but they're connecting at an unusual time of the day from an unusual location, we may still choose to deny that particular authentication. If this same person was trying to authenticate from inside of the corporate headquarters during normal working hours, then instead we may want to allow that authentication. Once the authentication process has completed and is successful, we can trust that that person really is who they say they are. Now that that trust has been created, we need to understand what type of access that user should have. This may depend on the user who's provided the authentication. If they're part of the help desk, they may be able to view the hardware database for the entire company. If they're the manager of the help desk, they may be able to make modifications to that database. And if they're not part of the help desk or managing the help desk, they may have no access at all to that data. We might also want to consider someone's location. If they happen to be in a different country, they might have a completely set of rights and permissions than if they were inside of the corporate headquarters. And if the user is accessing the systems using a laptop that has been provided by the company and we can verify the certificate on that laptop, then we may give them additional rights and permissions. A good best practice for IT security is to only provide rights and permissions to a user that match the requirements for their job. If your job requires that you have read access to a database, then we shouldn't provide that user with any ability to change that database. This means that we would not arbitrarily provide someone with administrator rights just to be able to access a certain type of data. All users should be accessing these applications with a limited set of rights and permissions. One of the reasons we don't want to provide administrative access to everyone on the network is that administrators have full access to all data on all systems. And if a device is infected with malware and the user on that device has administrative access, then effectively the malware now has administrative access to all of our systems. One of the challenges with providing the right type of authentication and authorization is that users can be located anywhere. Some users may be located in the corporate office, others may work from home, and others may have a field service position which takes them across the world. And the applications that we use may be located on a public cloud, across the internet, or they may be in our private data center. We need some way to provide a secure mechanism for communication regardless of where the user happens to be and regardless of where the application resides. One way that we can create this secure environment is through the use of SASE. This stands for Secure Access Service Edge, and you can think of this as a next generation virtual private network. This moves our security technologies into the cloud itself, very close to where the application data might be. And we would have a SASE client installed on every user's device. So no matter what system they're using or where they happen to be, they're able to take advantage of this Secure Access Service Edge. At the top of this SASE diagram is a public cloud, data center, software as a service, or an internet connection. This is where our applications reside. Our users may be at our corporate office, they may be working from home, or they may be mobile users. As the users are accessing these resources, we're able to provide network as a service, so there's quality of service and routing that we can provide. We might also have security built into this. Zero trust network access, firewall as a service, and DNS security are just a few examples of what SASE can provide. And because the SASE clients are installed on all of the devices and these connections are made automatically, the users don't have to worry about turning on or turning off this SASE functionality. The users simply use the devices they've always used, they connect to the applications that they need to access, and security is built into the entire process. Infrastructure as code, or IAC, is a concept where we can take a piece of networking technology and describe it in terms that are best described as code. This means that we can build a configuration file that could accurately describe everything in our infrastructure. Every server, all of the network devices, firewalls, switches, routers, and all of our applications can be configured as this code. This means instead of manually building, installing, and then configuring all of these devices, we can do all of that work inside of this code and then simply tell the cloud to build out all of these systems to our specification. We can even use this to create versions of this infrastructure, so we can build out infrastructure as code configurations, deploy that configuration, and then make minor changes and redeploy the configuration, and all of those changes will take effect. This also means that if we need to build another exact duplicate of this configuration in a separate data center, we simply take our code, we move it to the other data center, and we apply that infrastructure as code to build out a completely new application instance that is identical to the original. This is obviously one of the most powerful features of cloud-based technologies, and it allows us to have flexibility in where and how we deploy these systems. This is a very simplified version of an infrastructure as code configuration file. You can see all of the definitions are in here to create a host that's called mail.example.com. This infrastructure as code also includes children devices such as web servers and database servers, and you can see the host names are included in there as well. Inside of this same configuration file, we might want to include other details such as the type of CPU, how much network configurations, IP addressing, the applications that need to be installed, and everything else we need to get these systems up and running. If we can automate the process of building out a series of devices, then we can also automate the process of responding to issues. This is done through a process known as a playbook. A playbook is a series of steps you would follow in order to be able to resolve or address a particular issue. For example, if you needed to investigate a data breach, you could create a playbook that would step through that process. Or if you needed to recover from ransomware, there may be a set of very well-defined steps, and those steps would be contained within a playbook. This is obviously things that we do manually when we're addressing issues one by one, but putting it into a playbook allows us to automate this process. Perhaps you have a system that identifies the malware. It then references the playbook to know to remove that device from the network, delete everything on the storage drive, re-image the system, and then redeploy that system into your infrastructure. This can obviously be reused over and over again. So anytime you run into that particular issue, you simply apply the appropriate playbook. Playbooks are commonly implemented into SOAR platforms, that SOAR, that stands for Security Orchestration, Automation, and Response. This is a management console that allows you to centralize the operations of everything you're doing with security in your environment. And if you want to implement playbooks, this would be a perfect console for a centralized deployment and monitoring of those playbooks. This automation with playbooks and with infrastructure as code become very handy when you run into particular situations. For example, you may want to avoid instances of configuration drift where there are minor changes to configurations between different application instances. Or perhaps you want to be sure that all of your systems remain in compliance with a set of standards. We can do that using infrastructure as code. We can make sure that every single one of those systems is created using the same infrastructure as code definitions, and therefore you would have identical systems wherever you deploy them. Or perhaps you're configuring a testing environment and you want to be sure that that testing environment is identical when you deploy it into production. Infrastructure as code would be a perfect choice to be able to completely document what you have in the test environment and deploy that identically into your production environment. And if you want to be able to duplicate this same configuration across all of your data centers wherever they might be in the world, you would obviously use infrastructure as code. This would also be valuable if you needed to make a configuration change or an upgrade to an existing piece of software or system you may have already deployed. You simply make that definition change within your infrastructure as code definition file, and then you deploy that to those systems. It will note the difference and make those changes that you need to be able to upgrade those systems. We can also use infrastructure as code to be able to document the configuration that's been made to an existing system. So we may want to scan through a system that we would like to duplicate, have all of those configurations implemented within an infrastructure as code definition file, and then we'll not only have documentation of that system, but we'll be able to duplicate that system at will. As you can imagine, in large environments, these definition files become extremely important, and you want to be sure that you're running the latest version of that configuration file when you deploy these systems. To be able to ensure that level of control of the configurations, you need source control. This allows you to manage any type of change you may want to implement into those definition files, and then you'll be able to test those configurations and then ultimately deploy those into a production state. This prevents many different people from making their own minor changes to a configuration file, and instead you have one central repository where all of these changes are kept. And if somebody wants to make a change, they would need to make that change into your source control system. Sometimes we refer to this as a version control system for that very reason. A A very popular type of a version control system is Git. We use that often on the internet to be able to maintain these source codes across multiple users wherever they might be in the world. So you might have this central repository of a production system. You might want to make some changes, and those changes would be tracked and merged together into the final version. There can be many people making their own changes and merging all of those changes into the final config. This means that we can have many people working on these infrastructure as code definition files. They can be making changes to the area that's specific to their part of the build, and then we can merge all of those changes together into one centralized configuration. There might be occasions where one person makes a change to a line within the code, and another person makes a different change to the same line within the code. If you try to merge all of those together, there will obviously be a conflict. So your version control software not only needs to recognize these conflicts, but also give you a way to manage what change you would really like to make into the final code. This might be something that the version control software can do automatically, or it may require manual intervention by one administrator who can decide which configuration is really the best one. This change control software also allows us to create branches of different types of code. So we can create a version of an infrastructure as code definition file. We can branch that code off to do our own testing with, make some changes, and then later we can merge that into the original code to create a new version. This allows us to have a production definition and then take that and configure it in a testing environment for upgrades, changes, and optimization. And then once we've tested that, we can then merge it back into the production environment. Our current estimates put the total number of devices connected to the internet somewhere around 20 billion with a B. One of our ongoing challenges associated with this huge rise in number of devices is that IP version 4 can only support 4.29 billion of those addresses. The rest of this, we very commonly use network address translation or other methods to be able to communicate with all of these devices with such a limited number of addresses. And as you may already be aware, there are no more IPv4 addresses to be assigned. We have hit the limit to the number of IP version 4 addresses that we're able to use. We've been able to provide ongoing support for IP version 4 using network address translation. And the internet configuration that you use at home and at your office uses network address translation to be able to connect hundreds or even thousands of devices to the internet using a minimal number of IP version 4 addresses. Although this works with most of the applications that we use, there are certain apps that would prefer not to use network address translation, and this simply creates more complexities and difficulties for those of us that need to communicate over these IPv4 networks. Fortunately, we have a solution to this limited number of addresses, and that solution is a new version of IP referred to as IP version 6. IP version 4 addresses are 32 bits in length. IP version 6 addresses have a 128-bit address, which gives us a much larger address space to use when we're assigning these addresses to all of those many devices on the internet. Another way to visualize this would be to say that every grain of sand on Earth could have 45 quintillion unique IP version 6 addresses. You can see that this larger address space with IP version 6 resolves that IP address constraint that we have with IP version 4. There are a number of differences between an IP version 4 address and an IP version 6 address. This is an IP version 6 address, FE80:5D18:5D1A:6FFD:8F52. You can see that is a very different style of addressing than IP version 4, where we were only dealing with decimal numbers and periods. In IP version 6, we are using hexadecimal values, and we're separating those with a colon. If we were to write out that entire address into its entire 128-bit form, you can see that it is completely completely listed here, and that is a much larger address than we deal with IP version 4. If you wanted to view this in a binary form, you can see that we have the representation of that same address listed in binary. You can see here that each section of an IP version 6 address that we separate with colons is 16 bits in length. You can see the 16 ones and zeros listed in each one of those sections. This also means that each section is 2 bytes in length, and you may also see it represented as 2 octets in length. So in total, the IP version 6 address is a total of 128 bits, or 16 bytes in total. You might see an IP version 6 address written out with all 128 bits being shown on the screen. But you might also see these addresses listed in a compressed form, which makes it much easier to be able to read. When we're using this compressed form of an IPv6 address, there are a number of rules to keep in mind. One of those rules, if there are groups of zeros that are together, we can abbreviate that entire group by simply replacing those zeros with a double colon. We can only do this one time in an address, but usually that's all we need to make this address much easier to read. We also can remove leading zeros from each group within the IP version 6 address. Let's take an IPv6 address and perform this compression to see what that would look like. The IPv6 address we'll work with is 2600 colon delta 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 colon 1111 colon 0001 colon 000, and you can see the zeros go all the way through to the end to the number 1. Our first rule here is that we can remove any of these leading zeros that might be in all of these groups. This means that our IPv6 address with those zeros removed would be 2600 DDDD1111, and then each of those leading zeros in all of the remaining groups would be removed. You'll also notice that there are 3 individual groups here that are simply zeros. And one way that we could simplify the writing of this IP address is to abbreviate 2 or more of those groups together with double colons. So all 3 of those zeros would be removed, and we would replace them with one series of double colons. This means that we would have a very simplified form of this address. Instead of having all 128 bits of that address shown on the screen, the address is now simply written as 2600 DDDD1111 1 double colon and 1. Let's look at another IPv6 address and perform the same compression. This IPv6 address is 2601.04c3 4002 BE00, 3 groups of zeros, and it
so just pick a couple things that you like when you go to their about section. Just pick a couple things that you like, and how that matches your personality, your work style, your interests. Like sometimes you can make it as simple as you want. There's no I don't like this term. I love that. I need a job. That's why I like your company. I need money. Not recommended, but
As you can see,
just don't make that one too complicated. Just pick a couple things that you like about their company and how they match to you and your lifestyle or whatever. It's not.
directly communicate with each other.
Don't make that difficult. It's the same as like when they ask you, tell us about yourself. Just keep it simple and don't say too much or say something that'll require them to ask you follow-on questions, that you don't want to answer.
But fortunately, there are a number of different ways to bridge this gap. One of these methods would be to tunnel the traffic. We would either tunnel IP version 4 within IP version 6, or tunnel IP version 6 within IP version 4. This would give us a way to communicate
just like a recruiter
even across networks that were very
This is
different than the protocol that we were using.
Popular belief, I might have been a recruiter at one point in my life. I knew it.
With both IP version 4 and IP version 6.
I did it for the Army, and then I did it for a sales company when I got out.
Yeah, you sound like a recruiter.
I mean,
He's got it like, you know why? Because he has no pressure.
Obviously, these
But-
are stopgap measures, and they're not designed
but it's up to
be
you.
a long-term solution for connecting these
I might be able to sell water to a whale, but you know.
the best long-term solution would
I
be
believe
for
it.
all of us to move to IT version 6.
The craziest part is trying to get a job as a recruiter in the real world. It's silly. I'm like, I can recruit for anything. Anything. I just need to know what it is or whatever, and I can talk about it and whatever. And they all want specifics. They want healthcare recruiting. They want IT recruiting. They want, and I'm like, guys, recruiting's not hard. It's not. Especially when you get to use, in the art, when you're recruiting for the military, and this goes for all branches, you don't get to use LinkedIn or Indeed. You gotta go out there and find these people. You gotta sucker them into coming into the office.
Into the office. Into the military.
Yeah, but you know what I'm saying? Like, you have to like convince people to do stuff. Where in the real world,
because of both those limitations and because
yeah.
we have more devices these days,
Here's a free meal.
Where
Where in the real world, people are looking for the jobs that you have. You just have to figure out where to find them and if they actually match that job. That's it. It is the simplest stuff in the world. But they won't hire an old recruiter because I don't have the technical like designation or the healthcare designation or whatever. I could just lie to them, I guess. But then they
No, but you know what it is? They look in the field because they take, like if, like my nurse, my wife would be an excellent medical recruiter because she's been a nurse for almost 25, 30 years. Just to know what to talk about it. And then IT, you could be a recruiter in IT because you have the certs, you have the professional certification.
I've been looking.
So now you have the background and you have the professional certificate. So to be a recruiter for IT, you can do that. That's an IT position. Listen, you know what, Charles? Thank you very much. You just segued into something that's very important. You have to be very creative. If one thing's not biting in IT, you gotta shift to something else. Don't be pigeonholed into thinking I have to get something in the system admin. I got to be a network administrator. I got to be. Kevin was looking at. Was it Kevin? You were looking at earlier about the help desk, right? And then somebody brought it up. Hey, what's a computer tech? Oh, you drive around and make your own schedule. I think that was Mr. T. Maybe, I don't know, or client tech. So be creative. There's so many different things to do in IT until you get the job you really want. But there's other ones that can fill the void until you get what you want.
Also, don't be afraid to shoot your shot. There's roles out there, and as a former recruiter, someone might not have the right resume bullets or whatever, but when they talk to you, if they reach out to you, they say maybe you don't know like what they might really be looking for in their role. And sometimes what's worked for me to get at least an interview is using my veteran, I'll use the veteran card, and because the recruiter might be a veteran or the hiring manager might be a veteran, hopefully both. That's the golden goose. I've applied for, even with IT, I've applied for jobs that are probably above my skill set. But maybe they go, you know what? He can learn stuff, So it's just all about whatever you try to do. Yeah, absolutely. Always.
I've seen people get jobs not really having a firm grip on what they just learned. It's something about them that the person likes. And it could go both ways. Charles is right. It's a 50-50 shot. The only time it's a 0% if you never try.
Here's an IT role that I applied for. I'll just give you what they're looking for. Coach, mentor, and grow cross-functional, exceptional engineers. I, as a former leader in the military, definitely coach, mentor, and all that. I mean, were they engineers? No, but they were kind of like they can break stuff. Whatever. It's leadership skills that they're looking for. Fast-paced, agile environment. That's military. All day, every day. Hiring, training, mentoring. It's a $200,000 job. I'm not going to get it, but I shot my shot.
You never know.
You never know.
You never know.
And it's remote? Yes, please.
The other device only understands IP version 4.
You never know. I'm gonna tell you a story what happened before we go on break. Let's see. Jesus says, fake it till you make it. I believe in you. Yeah, we do. Yeah. Way to go, Jesus. Kevin says, man,
Routers that
even
we
getting
use in our homes
fired
and
after
our
a month,
offices
they have a
have
good
an
chunk of
important
yeah,
job
you
of
would.
forwarding traffic between one IP
I put in for a job. It was like
it's a relatively straightforward process,
2020
although there is a lot of technology under the surface that makes this
or
happen.
2019.
But if we were
I hadn't
to
got my
look at
Sec
this
Plus
in a very
yet.
simplified
But I
way,
had all
we
this
see
knowledge
that
in the
the
world about
router is
IT and
performing a
database
series of
admin. And the
relatively
recruiter
simple
called me
steps. The
immediately.
first
I
step
said,
is to
I'm obtaining
identify
my
what the
Sec Plus. He's
destination
like,
IP address might be.
he
First,
literally
traffic
called me
into the
within
router.
24
It looks
hours,
into the
and it
packet,
was for a
identifies what
deployable
the
position,
destination IP address is,
right,
and
to go
makes
to
a note
Kuwait.
of where it should be sending this
And I was
traffic.
like,
The
I'm
router
ready to go.
examines
He
some
was like,
tables to
great,
determine
great,
what
great.
the best
Just noticed
route
one
will be
thing.
for this
Got Sec
particular
Plus.
packet. If the destination IP address
Job's yours,
of
man.
this particular
You don't need to
packet
know
is
this. I can see
associated
you
with
have
a
this.
subnet
That's
that
what he
is
said
directly
on the
connected
phone.
to this router, then the router
He said,
simply
job's
sends
yours.
the packet
Really
onto
don't care
the
about you. Got the
subnet.
time and
But
experience.
in many cases,
You're
the
just gonna be
destination
doing
IP
help
address
desk
is
stuff.
on
That's
a
what he
subnet that
said.
is not locally connected to
Got
this
Sec Plus.
router.
I was like,
The router will
no, I'm
examine
having it
that
in like 3
routing table,
weeks. He's
determine
like,
what the best next hop might be.
he said, I needed you to
and then
have
send
that
the traffic
yesterday.
out that particular
This job,
interface.
you'd be leaving
This
within 2
next hop
weeks.
is the IP address of the
Like,
next
you
router
gotta have
down
it
the
now.
line.
Can you go in and
That
test
router
tomorrow?
receives
I'm
the
like,
packet, it performs
no,
a
man, I
simple
don't have my
process
voucher.
again
And he's
until
like,
the
ah,
packet
man, I gotta give it to
finally
somebody
makes
else.
its way to its final destination. As you can
That's what he said.
imagine,
He's like,
that
I gotta give it to
routing
somebody
table
else. I
becomes
still
very
wound up getting
important.
overseas,
When we're
though.
troubleshooting routers,
After
we
that,
refer often to the routing table, what
wound
the
up
next
in
hop might be, and determine
Afghanistan
where these
and
packets should
Abu
be going
Dhabi.
once they leave
At
our
that time, at that
If a
juncture,
router refers to
I
this
couldn't take
table
that
and
position
does
because I
not
didn't have
find
Sec
a
Plus yet.
next
I
hop
was
for
just
that
about to get it.
destination IP address, it will simply discard that traffic. So you can see why having a valid routing
Yeah, they're
table
like,
becomes very
if you're
Let's
applying
look
for
at
an
this
overseas
network
job,
diagram.
those jobs
There are
I've shown you for
three separate routers
deployable
in this network
positions.
diagram, and three
If
individuals
you don't
that
have
like
Sec
to
Plus,
communicate
they ain't
with
gonna
each
touch
other.
you.
In this case, let's focus on
They want
router
you
one.
ready to
You
go.
can see router one
Like,
is
like
connected
they want
to
you
three
gotta have
different
that. You can have no
subnets.
cert in the
You have
world.
subnet
You
10.10,
better have Sec Plus. That's the one you better
10.20.
have.
There's another subnet between router one
Because a
and
lot
router
of
two
folks
that's
won't
the
touch you
10.10.20
if you don't have it.
network, and then another
Yep.
subnet between router one and router
Is it high
three.
position
That's
or is
the
it entry level?
10.10.50
Entry level.
subnet.
It depends
Those
on what they need.
subnets are
Like
directly
every
connected to
base
router one.
overseas,
So if we
they
were to look at the
hire
routing
contractors
table
for
router one, it would
computer
see the router
techs
for
to go out and swap out
10.10.10/24,
lines and computers. They hire at the
10.10.40.0/24,
help desk position because they need somebody to answer the phones if you got a problem. It's still IT. It's a whole IT knot. It's a network operating center.
The problem occurs
They hire
when
at all
Sam
positions.
would like to communicate to Jack. Although
No.
router one knows about the local networks,
No,
it has
they
no
care
idea
if it's a
that there are
higher
more networks
tiered
on the other
position.
side of
You are
router
now
two
a
and
manager.
router three.
You
And
get what I'm
these
saying?
particular ports of 10.10.20
If you're just looking for a job to get overseas, make 100 grand and change in 6 months,
are nowhere in this routing.
all they care is about you
This
having
means if Sam
Sec
wants to send
and whatever
traffic
else they
to
ask
Jack,
for. But that
Sam
Sec
puts
is the
this
one they
packet
looking
out
for.
on the network. It gets
Because
to
they won't
router
let you in the
one.
country
Router one
to do that
examines
job
the
unless you got
destination
security
IP
plus.
address of 10.10.20.2 and then looks through its table and realizes
Now there'll be some
is
advertisements that say all you need is Net Plus and CompTIA A Plus or CCNA. I'm not saying they won't list it,
one way that we
but
can
like
create
if it's
a
a
more
deployable
complete
position, they want to see some kind of security,
is the
something,
administrative creation
so you can
of a
trust, so
routing
you can
table
touch the
is referred
network.
to as static
Mhm.
routing. And if you would like to
Yeah.
build static routes as the administrator of your routers, then you will manually be configuring these routes inside
Hey Zeus, hey, a win is a win, baby.
It's a very quick way to configure a route inside of the router, and if you're managing a smaller
If Sec Plus right now is the only one you have, you're winning still.
manage where the routes might be.
And that's for right
As for
now.
static routing,
That's not saying the other ones you about to get.
normally see
Yeah,
a
you still
dynamic
winning.
routing protocol.
So,
we'll talk about
yeah,
dynamic
soak it up.
routing in a future video. So there's
The
no
win is a
CPU
win.
cycles, there's no memory usage. We are simply adding the route ourselves, and we don't have to
All right,
do
everybody,
any
tell you what,
additional
let's
processing to the
do
routing table.
10 minutes.
This is very
And
common
then when we
for
come
remote
back, we'll jump
locations
into
where you might
domain
have a
2.
single internet connection into that remote site,
See you in a minute.
and all communication takes place over that single connection. We often refer to these as stub networks. And because we don't have to worry about any type of dynamic routing updates or having any changes to the router configuration because of those updates, this is a relatively secure form of routing. However, this can be challenging to configure on larger networks. Configuring a handful of routers with their own static routes is relatively straightforward. But if you're managing hundreds or thousands of routers, manually configuring a static route in each of those routers could take quite a bit of time. This also relies on you adding the correct routes to every router. There have been times when I've configured static routes and I've set up my own routing loop within my network because of a misconfiguration. And as the name implies, these routes are static. They don't change once you've configured them. So if there are changes to your network, you'll need to manually log into your routers and make those configuration updates to the routing table that match the changes to your network. This also means that there is no automatic rerouting if something happens on your network. You will need to manually configure these routes if anything needs to be routed in a different direction. So let's configure some static routes for router 1. We know that we have our 3 locally connected routes, but we also have these additional 2 routes, one that's behind router 2 and one that's behind router 3. This would be the 10.10.20 network and the 10.10.30 network. So we might SSH into router 1, and at the command line, we would begin to add additional static routes. For example, we might tell router 1 that if it receives any packet coming through with a destination IP address that matches the range of 10.10.20.0/24, then send that particular packet to 10.10.40.2. So if the packet does come through with that destination that needs to go to the local network that Jack is connected to, it will send all of that traffic to the IP address 10.10.40.2, which is located on router 2. At that point, router 2 will examine its own routing table and know that the 10.10.20 network is locally connected and send that packet on its way. We can do the same thing with the 10.10.30.0 network, so we will manually configure a static route that if any destination traffic is going to 10.10.30.0/24, then send all of that traffic to 10.10.50.2, which means all of that traffic will go to router 3. Now that we've configured those static routes in router 1, anytime those additional networks are seen as a destination IP address, router 1 will know exactly where to send that traffic. Static routing requires the network administrator manually configure every route on every router in the organization. If you have 3 or 4 routers, that might not be a big problem. But if you have tens or even hundreds of routers, you might want to have a more automated way for configuring your routing tables. One way to do that is through the process of dynamic routing. Dynamic routing will have the routers handle this process for you, automatically discover these routes, and update each other as to where the best route might be. This means that you as the network administrator don't have to do any type of static route configuration. You don't have to SSH into the router, make any configuration changes, or update those routes if anything changes with your network infrastructure. Anytime you bring a new router online, all of the other routers will automatically know where the new route is, and if you happen to remove a router from the network, all of the routers also know that that route is now no longer available. There is a bit of overhead required inside of the router to be able to automatically discover these routes and update the routing tables. This will require some CPU and memory inside of the router, so you may need to do additional monitoring to make sure that your router is able to handle that load. This also requires you to initially configure the dynamic routing protocol. This may be a relatively easy configuration process, or it may require additional planning and engineering to be able to implement it properly in the config of the router. Let's look at this network configuration where we have Sam that may want to communicate across the network to Jack or to Tilt. You'll notice that there are 3 different routers, and for this particular example, let's focus on router 1. You'll notice that router 1 is directly connected to 3 different subnets, but there are 2 subnets on the other side of router 2 and router 3 that router 1 simply can't see. So we need some way to update router 1 with those additional routes. One way to do this would be to have router 2 send a routing update via EIGRP to router 1. Router 1 receives that update and then updates its own routing table with this new route to 10.10.20.0/24, and the way that you get to that network is to go to 10.10.40.2. We also have another EIGRP update that has come from router 3, and when that update is received, router 1 identifies a new route to 10.10.30.0, that's the subnet down at the bottom, and you can see that the next hop is 10.10.50.2. All of these updates occurred in real time behind the scenes without any type of user intervention. And if we happen to add or remove routers from this network, this routing table will be updated with an additional EIGRP update that will either add or remove those routes from the table. Although it looks relatively straightforward to perform these dynamic routing updates, there's actually a lot of work that occurs behind the scenes. First, the router needs to listen to the traffic that is on the local subnet and see if there are other routers that are sending routing updates that it can use to build its own routing table. These are very often sent directly from router to router, either directly or with a multicast. Once a router then builds its routing table, it needs to inform other routers of routes that it knows. So it will send its own multicast to other routers that are nearby, informing them of all of the routes that that router happens to know. Once the other routers receive this update, they need to interpret this information and determine if that's a better route than what they already have, or if they should use this as a secondary route. Different routing tables use different methods to make these decisions, and they will update their routing tables differently depending on the protocol you happen to be using. And of course, if there is any change to the network infrastructure, these routers need to inform all of the other routers that the change has occurred. So if we add a new link into a router, we remove a router, or we add a router, we need to make sure that all of our routing tables are updated across the entire network. There are a number of different dynamic routing protocols to choose from. So which one would be the best for your particular implementation? Different routing protocols make routing decisions in different ways. For example, would you like your traffic to be routed based on the state of the link, whether the link is up or down? Or would you like to be able to make that decision based on the number of hops that a link might be away from you, or the speed of that connection? Based on the routing protocol that you're using, that decision might be very different. Some routing protocols will use a different criteria to determine the best way to get to a remote location. You might also find that some routing protocols are able to make changes very quickly if anything happens to the underlying infrastructure. So if you add a new router to the network, it might take a number of seconds, or it might take a minute, depending on the type of dynamic routing protocol that you're using. And in some cases, we need to take into account the type of router that we're using. Some routing protocols, such as BGP and OSPF, are very common and can be used across many manufacturers' devices. Some routing protocols, such as EIGRP, may work best in a Cisco-centric environment, so if you have a lot of Cisco routers, that might be a better routing protocol for you. Although EIGRP tends to be very Cisco-centric, you may find EIGRP is also available on other manufacturers' routers. But there are some aspects of EIGRP that are proprietary to Cisco, so you tend to see it mostly in Cisco-related configurations. But one advantage of EIGRP is that it is relatively easy to set up. You would turn on EIGRP in your Cisco router, give it a few minor configuration options, and it's now up and running with the EIGRP protocol. When there are changes, EIGRP tends to converge relatively quickly, and it's also able to identify any loops and prevent those from occurring on your routed network. EIGRP is also very good at identifying other EIGRP enabled routers and sending updates over a minimum of network traffic. This keeps your network more efficient and leaves your bandwidth available for other applications. If you want a more generic dynamic routing protocol that can be used across different manufacturers' routers, then you might want to try OSPF. This is the Open Shortest Path First Routing Protocol, and is one that you'll find available on a number of different manufacturers' devices. This is often implemented in a network where you have complete control of those systems. We often refer to this as an AS, or an autonomous system. For example, if you're running a wide area network that has 50 different routers, those 50 routers would be part of your single autonomous system. Another advantage of OSPF is that it's available on many different manufacturers' devices. This is a common standard, and you can download the standard from the internet and read through every aspect of OSPF. We refer to OSPF as a link state protocol, which means it determines what the best route is based on uptime and availability between the different OSPF routers. OSPFs can be used to assign costs to an individual link, so certain links may have a higher cost than another. This allows OSPF to make routing decisions based on what the least cost might be. This cost is often associated with how much throughput may be available on a particular link, if that link is up or down, and how long it takes to traverse that particular connection. With OSPF, the lowest cost and the fastest path is going to be the best route to a remote location, and if there are identical costs on OSPF...
All right, everybody, welcome back for round 2 in domain 2.
If you need to route traffic outside of your
what we have in front of us.
system to other organizations, then you might want to
Vulnerability
use an external
management.
gateway
What's
protocol
happening in
such as
domain number 2,
BGP.
second highest
BGP
domain.
is the border gateway
30% of the
protocol.
questions
It's
and or
commonly used
PDGs
on
will be in
networks
here
and
in some
internet
shape,
connections.
fashion, or
Connecting
way.
the internet together
So let's get
will be
into
able
it.
to dynamically
2.1, given a scenario,
route
implement
the entire
vulnerability
internet.
scanning
It's a daunting
methods
task,
and
this
or
particular routing
concepts.
protocol was designed
First thing that we
with this
see
specific task in mind.
on
Sometimes you'll hear BGP
the
referred
left
to as
side
the 3
will
napkins
be
protocol.
discovery.
This was sketched out on napkins initially to solve this
Right
particular
there.
type of problem. If your
Asset
organization
discovery.
has one or more connections to the internet, and you
As a
want to
network
be able to
technician or
route
being in
to
the
those
IT field,
internet
you got to
sites,
figure out what's on
you'll
your
want to
network
use
at any given
protocols
time.
such as
So you have to
BGP.
do map scans. Now, you'll see why I say, plus they will present to you some different types of APIs, application interfaces, or commands you can use to do enumeration.
Evaluate incoming traffic, determine
What would be your answer
traffic, and then send it out the
of
appropriate
APIs
The routers
or
effectively
applications or
what
commands you
direction
can use to
goes
enumerate a
the
network?
knowledge it has about the rest of the network.
Hmm.
To be able to make this decision about
That
where
means to
traffic
find out
goes,
how
you need
many
a routing table. And fortunately, most devices have a routing
quantitative.
table. The workstation that you're using
All
has
right,
a
so
routing
what's your
table,
commands
servers
or
that you're
application
accessing have routing
interfaces
tables, and of course the
you
routers
can
themselves
use
maintain their own routing
by
tables.
command line, API, or commands?
The best route would be to a destination. It refers to this routing table.
And
So everything we
yes.
do when we're troubleshooting a router will begin
What else?
and end with the information contained within that routing table. One thing you
Nmap.
might find with the
I'm talking about
router is that
MSC
there may
console?
be multiple ways
Probably
to get to a
the
location.
Nmap
and
was
there
another
will
one
be
you
a
can use.
tie as to which route a router might choose. Fortunately, there are
That's
ways
that?
to break the tie.
Not really enumeration, but that's that.
We'll
That's
look
that.
at a number of ways that tie-breaking process might occur. Let's look at a routing table.
Ping
This is a
suite.
routing table I made from
Yes.
Cisco
What
router,
else?
But it's almost identical in form and function.
Catenate. Yes, you can.
In a workstation, in a
What
server,
else?
or in any other manufacturer's router. In this particular example, this routing table was built based on...
Think about an application you could open. There you go. Angry IT. What else?
Using the RIP dynamic routing protocol, specifically RIP version 2. If we look at the routing table, the top part
Nessus.
of this
What else
routing
you got?
table is a legend that gives us more information.
This is a
about
big one in
what's
Kali
within
Linux.
the
People
routing
love to
table
use. Starts with the
itself.
letter B.
At the
It's
bottom
involved.
is the routing
Bravo.
table, and you can see
Verb
the first
suite.
set of letters on each one of these lines.
What's another one that you
corresponds
could
back to
use
a different
for
set of codes that are shown.
Web
For example, you
applications.
can see the first line
And
of this routing table starts with the letter C, which means
actually,
that particular route is
I would take that answer for Wireshark, even though it's not built for that, but it does tell you what's on your network because you see all the IP addresses.
Yeah.
So you could use it as an enumeration tool. I'll take it, but don't pick that on the exam because that's not what it's used for. But you could use it for that. Splunk, yes you can. It's a scene source situation. Okay, so we got some good ones. Good stuff, good stuff. Okay, so those will help you map a network to figure out what's there. If you're doing device fingerprinting, now we can get back into NetStat, or we can do different things to figure out what's going on with that device. IP config/R, right? Nmap can do it for that device too, because it would bring back some tools. Let's look at some special considerations. Scheduling, operations performance, security levels, segmentation, regulatory requirements. This is the law down here. This is the law. Not just law, but local procedures and or instructions, right? And it could be some government regulation. Always remember to segment your network. Look at the sensitivity levels of the data so you can properly segment. And scheduling operations and performance comes into your considerations when doing asset discovery. Reason why I say that, you can do a ping sweep on a network that doesn't need to have it on there, and they say don't do it on this network because there's an IDS or IPS, more so an IPS, and it can shut down the server. So you got to be careful because some of these ping commands could do that. When you're looking at internal versus external scanning, what's some telemetry that you would get from an internal scan? Think outside the box. Don't give the usual answers.
Evaluating everything in this routing table to determine if this would be the best possible route to use to forward this traffic along to the next route. One of the first things
think of some different commands.
Is where this particular traffic is destined.
It is certainly cheaper because you can get somebody on the inside of the network to do it and you don't have to pay anybody. Windows Defender can help you out because it'll give you telemetry about that device. Sure.
This means that this IP address range and prefix length becomes an important consideration when we begin to forward traffic.
What does that tell you?
Both of those together to determine if this is the best possible route for this traffic. And if you were to look at a routing table,
that's a command that an administrator can run.
Listed to a particular subnet, but there might be different prefixes.
Got the brain going.
So you might need
all right. What about a
routing table to determine which
I got what you're saying, Mr. T, because it tells you uses of traffic that's applicable to what you have something connected to, right? So yeah, I got you. Yep. What does this tell you?
168.1.6, and your routing table has 3 different routes that would match that particular IP address. One of them is 192.168.0.0/16. The other is 192.168.1.0/24. And the third is 192.168.1.6/.
Yes, accounts.
All of these would be valid routes.
You think, there you go. User IDs. All that stuff could be attached to something. What about this? What's the command? If you can get to the command line, that's why I say internal versus external scanning. If you're doing an internal as well, and you can get on the network, because you'll have better success of this, because you don't have to jump through firewalls and all this stuff.
In fact, that is the most specific route.
What's the command in Linux where I can show everybody's GPO? Well, I don't stop. I said that wrong. What's a command that you could type in Linux? There you go. Change mods. What's the command you can show in Linux to show what they have as far as permissions? Remember, we said 777 was the greatest you can have. Yeah, ls-l
This can get even more complicated.
Yeah, so you can see what's going on.
There
you go, all right.
And
And of course, external, you gotta have somebody on the outside.
How do you know which next hop?
It's harder to do,
If everything
but
else
hey,
was identical.
what's an agent
One way that you would
versus
be able to
agent
make
list?
that determination is by
Scan.
examining the administrative distance. Different routing protocols are assigned different administrative distances within the router itself.
This is a possible question on the CYSA exam. That's why I want us to slow down. There you go. Thank you. Pretty simple.
For example, if this
Person versus a scheduled scan.
is physically connected
Way
to
to
the
go.
router, this
All right.
is the best
Then you have
possible
credential.
way to get to that
That's
scan.
you
So it
having a
has
sysadmin card, full access to the network. You're nosing around. You can see everything, so you can see the vulnerabilities
You have manually configured the static route. The
with a
router
bigger
says
scope,
that you must be the most
and you can
knowledgeable
write that
person
down,
for that particular
so you
route.
can nose around all day
Set an administrative distance
and
of
see
1.
what may be
If
at
this
fault.
route was added to the routing
A
table,
non-credential scan is you might be just a regular user, username and password,
and if you
able to get on.
receive this
That's
route
it.
via OSPF,
So you would
the
assume that
administrative distance
role
is 10. You can see
to
that
look
all
around to
the
see
routing
how far
protocols
you
and
can
methods
get.
are listed in this
So it's
table
the exact
with
opposite.
different administrative
One,
distance for
you can
us.
walk through every wall,
In some cases,
and as a regular
the
user,
protocol
you're gonna
itself
hit a wall.
may be in a position where
Allegedly.
there might be duplicate
So,
routes to a particular location.
that's when you find out what you can do. Then you have a passive versus an active scan.
In that case,
A
you
passive
would
scan
have
is
the
Wireshark.
routing metric to be able to break that time. Routing
This
metrics
catches
are
network
internal
packets,
values that are
or Kevin said a tap, network tap, he said that earlier, where you can tap the line, see what somebody's looking at specifically, right? Or an active scan, again, Mr. T said it, scheduled scan, something's going on, you're participating. You're not just sitting back watching it go by you. This scan is actually participating in what they're seeing. Yep, looking at exploits. Then you have your static versus dynamic when it comes to, if I was to say reverse engineer or fuzz, where does your mind go? Dang it, listen, give the keys a little break. They burning up there. I bet the letters are burning off the keys there.
Let's look at
Yeah,
the
thank
routing
you.
table for RIP version 2
Alright.
again. We have that one line in the
So
routing
you got that
table,
right. It is related to code.
10.0/24. It has an
All right.
administrative distance
So,
of
reverse
20
engineering,
because it is
we can
RIP
use
version
a
2.
program
It has a
to
routing
break it
metric
down,
of
like
1.
the gentleman we saw a video last week where we talking using a Visual Code Studio, right? You can use those type of platforms to run the code to see how it's gonna react. Reverse engineer to see what went wrong and how the code got into the system or effectively started running. Fuzzing, what you're using, you're throwing everything at the book, at this code to see if it's gonna break. Basically, that's what you're trying to do. You're trying to break it. You're trying to see the stress, a stress test. Critical infrastructure. Get to know your operating technology overall, or your operational technology. See how everything works together. Have a good roadmap on how each thing works together. What is the purpose of that one item that you have in place? And that's the one thing that I had started working on. I never completed it, but I got a good 75%. I'll lower that a little bit. Probably 65% of it was built, and I handed it off to the new sysadmin that came behind me, because it's cool to know, okay, this department has a wireless access point that the knock came in, put in, that it was approved. Key points, you need to make sure that this wireless access point works on WPA2 security. Here's the IP address, here's the MAC address. It needs to stay away from the super room, like 50 feet. It's positioned here because it's only for use for this department. Here's the login and the password. Here's the administrative password to make sure you can facilitate the, you get what I'm saying? Have something going on with each piece of equipment that's a core device on your network. So if you're out or you have somebody that needs to fill in, they'd be like, yo, let me grab the book. There's a book. 90% of their questions will be answered if it's an IT person that has to fill in for you.
right? So they got a good running start. They probably wouldn't even have to call you. But you want to make sure they do a change sheet. What is a change sheet? If they had to change anything, what needs to happen? Let's say Elaine was out for the day. I came to take his place. Couldn't get in touch with him. Not really logs, but let's say I couldn't get in touch with Elaine. He's on PTO. I don't want to mess with him. This is a minor thing, but I had to change the admin password because something else happened. What should I be doing?
You would seamlessly continue to have connectivity using that redundant router. Here's how this would work.
Bingo. Aaliyah said change management form. I have to do a change management form, put it in the book, because guess what? Elaine comes back from vacation 14 days later. I'm nowhere around. I'm on vacation. He goes to mess around with the wireless access point, the same one that had an issue. I can't log in. I can't. What the heck's going on? He should go to his book, and there should be a form in there and say, hey, Elaine, didn't want to bother you while you're on PTO. Wireless access point admin password has been changed to James. Here's my email. Here's my phone number. Now Elaine's like, thank you. He goes, life moves on. Right? It's a stick. Basically, it's a sticky note that you're putting in his binder or something to say, this is what I changed on your network while you were gone. Because you gave me the playbook, right? So that helps out. And it makes it look like you know what's going on around the organization at all times. All right. You might be working with industrial control centers, which are attached to SCADA. It's a supervisory control and data acquisition. They do work with an ICS, and then it's the programmable PLU, programmable logic. Thank you, Aaliyah. Between you and Brian, y'all got to get me on that one. Okay. Logical controller, which will make sure that everything's running smoothly and synced. Okay. Now for this, you need to remember for ICSs and SCADA, since they're using their own, time is of the essence. So you don't want just network time. What's that time you need that's very precise on the network? Because robots use it. Very precise time. It's atomic time, but what's the name of it for IT purposes? It's NTP that's being used, port 123. PTP, precision to Martin from the clutch. He shot like Steph from the bleachers. That man gets rockets. All right. So it's, there you go. Precision time protocol. All right. Way to go. All right, here we go. Then you have security baseline scanning. You simply just pulling out your binder, maybe 6 months from now, taking a new reading of your network. You scan it, look for vulnerabilities and stuff, or whatever you need to do, and you just match it up to what you had 6 months ago. Now, if you're gonna fully audit yourself, I would never do it all at one time. Why? Let's say everything in your feed, that everything that you get graded on, you say, oh, I'm gonna tackle all this. Yeah, it's doomsday. It's doomsday. So you try to tackle everything on your network and audit yourself at one time. Impossible. Pick something. Spread it all out. January, I'm auditing all my baselines for my workstations. You making sure all your configurations for your workstations are good. This is the way you set it up in the beginning. Through change management, it should have changed. Then you go through all your workstations again and say, oh, yep, they're all good to go. You might find some that are missing configs that they're supposed to have. Some are good to go. You don't have to touch them at all, right? That's one. Then you do something else for that month, because it's going to take you a long time. Like, I need to go around to my printers, make sure all the printers have what? Y'all tell me. Y'all the experts. Jesus, what you got? What's the experts? What's the experts say? What kind of things should you do for a multifunctional device that can do a lot of stuff? What's some basic things you can do to secure it?
way that we're able to make this work is through a technology known as network address translation.
What type of automation?
We often refer to NAT as being the way that we are able to extend the functionality of IPv4 and use.
Okay, yeah. So if you're monitoring it on I get you. That's a good one.
Use cases.
He's saying he's controlling it through SDN or something like that, and he can look at it and see. Okay, good. What's another thing you can do due to that multifunctional device? That's just like an audit. Network access control, correct. That MAC address belongs to that port and that port only. In this IP address, correct. What else can you do?
IP addresses that are not routable on the public internet, so we most often use these inside of our homes and inside of our businesses, and we'll perform translation.
Mike's drawing a blank. He's like, I don't know. What if I want to print from my desk, but I don't want to have it sitting on the printer because I might get sidetracked and not get it, and it's something of sensitive nature.
One IP address range that is private is 10.0.0.0 through 10.255.255.255.
Okay, it says
In a large
implement firewall and blacklist it for certain sites.
that you're using. This RFC also allocates 172.16.0.0.
You can do that through. You can do password to print, or you can. The whole thing is called secure print.
Address translation at home.
Yep. You're correct. So you either require a password, you send it to the printer, but when you get to the printer, you have to put a password in. So you do the token, and it may ask for a password. Or you do the token, and it might just print because it's no you. It was you with a print job, right? Mr. T says implement firewall and blacklist for certain sites. You can. I'm gonna tell you why. Because usually when you're running a printer off a network, it belongs to a print server, which is now again domain name. Yes, I got you. Charles says signing.
To follow this process,
The basic stuff, firmware update, and also
10.10.20.50.
go in there and never remember print jobs. Turn it off.
This packet will first hit a router that is configured.
You don't want it to remember crap.
This
Yep.
router knows that the source IP
So that's a
address
good one.
10.10.20.50
All right, cook this stuff. Let's move on.
is an internal IP address.
Know your
Use
frameworks.
this IP
Hard to
address
check to see if it's still
for
fun. Hardware check to.
So this
That's
router
another one
will
too.
change
Just do
or
some.
translate
Just
that
spread it
address
all
to
out.
something different.
Do 2
This
things a
router
month,
already has
so
the
it's always in
IP
rotation
address
every 3 months or so,
used.
right?
In this case, it's
So you don't get caught out there.
94.1.1.1.
PCI DSS, we got that. CIS, remember the Center for Internet Security Benchmarks? If you could tell me anything about CIS, and there was a question about it on the exam, what trigger words will come to your mind to help you answer this question? Oh my gosh, I said, y'all better not forget this. And Mike forgot.
When this router now receives
Okay, let me point you in the right direction. Can I give y'all a hint?
Yeah.
Who services the Linux OS?
IP address to be the internal address of 10.10.20.50.
You do.
Which obviously matches
Everyone.
the IP
No,
address
you're
of
right.
Paula.
So that means if you see the Center for Internet Security Benchmarks, who contributes to the benchmarks?
With standard network address translation, we are translating from one IP address
We all
to a
do.
different IP
Everyone,
address.
which is
This
now
means that
called
if we wanted to have
the-
many people
the community of
we would need to have
experts.
many more public IP addresses available. There's a way to make
SMEs.
this much more
There
efficient
you go.
using a different form of network.
All right, so
address
you'll
translation
usually
called
see
NAT overload
the community.
or port address translation or PAT. Let's take that same example where
Whis-
Paula would like to communicate to
Whiskey
ProfessorMesser.com.
Center for-
Paula's IP address is 10.10.20.50, but you'll notice we'll
So
also
CIS
use the source
benchmarks
port
are
number,
related
which in this
to a
case is
community of
32.3.
experts.
The destination
Blah, blah,
IP
blah,
address
blah, blah.
is obviously the
All right.
IP address of the
Cool.
Professor Messer web
All right, then
server.
you'll see OWASP, Open Web Application Security Project. I always say protocol, but it's project, just to be clarity. And then you have the ISO 27K, International Organization for Standardization. This is what people follow around the world. This is world. You can relate this to NATO.
You'll notice here that the private address of 10.10.20.50.3230
ISO
is converted
is to NATO.
94.1.1.1 with a port number of
ISO is the
5.
international
And when that
IT
translation takes
standards.
place, our source IP address
Agreements.
is now a public IP
Just like
address,
NATO has
and that's
international
received by
standards,
Professor Messer.
ISO does the
Because
same
we're
thing.
translating both the network address
All right?
and the port
So think of
number,
it that
other
way.
devices on this network could use the same public IP
H
address.
to the
For example,
ISO,
let's take
V
another
to
scenario
the
where we
ISA.
have Jonas at
Forilla,
10.10.20.60.
my IT pillars. That's
port
what
number
I'ma
chosen
say.
for this transaction is 5782.
ISO to
And
the
of course,
VA.
destination
Oh,
IP
see?
address is the same
Mike finally caught what I was.
.com web server with a port number of 40.
Craziness.
When that packet is received
All right,
by
moving
the
on.
address translation
Nothing to see
router,
here, people. Keep that move back.
address has not been used before, and it puts that into the network address translation.
Okay, so if we look at,
with a
I don't miss this.
port number on the public IP
So if
address
we're looking
side.
at tools,
So now we're using
yo.
the same IP address of 94.1.1.1 as our
This is what we
public
got.
IP. But notice that
Y'all
the
have already
number
mentioned
has
IT
been
scanner
limited by 1.
and
This means
Maltego.
we
That
can
is
now
another one
have
you can use for
people
scanning.
inside of our network
Tools you can help you
externally to
enumerate a
the
network.
all using the same public
Remember
IP
your web
address.
scanners, Burp Suite, which can help for look for vulnerabilities too. Zap, which is your web vulnerability scanning tool. Arachnide is another web vulnerability scanning tool. However, just so y'all can stay industry
For
current,
example, when we connect devices to a switch, all of those devices are
and
in
they
the
need to
same
update
broadcast
this.
domain. In this diagram, we have one switch on the left, that's our red switch, and all of the devices connected to that switch are in the same broadcast domain.
Arachnide has
On the left side is
changed.
the blue network. This blue network is also on its
Arachnide
switch,
has
and
changed.
all of the devices connected to this switch.
The
are on
Arachnide
the
Web
broadcast
Application
domain.
Security
Because
Scanner
there are
Framework
two
has
separate
been
switches,
replaced
and these switches are not connected to each other. No one on the
by
red network
Codename
can
Scanner.
communicate directly with anyone on the blue network. One of the challenges with this configuration, however, is that we have two devices
So
on the red
Codename
network
Scanner
and
is the
two
new one.
devices on the blue network, but you can see that there are 24 interfaces on the front of each of these switches.
Just wanted to
Which
show you
means
that.
we're running two separate
All
switches
right.
with two separate
Moving
power
on.
sources. They're both taking up space within our rack. And
Then
we
you have
to manage
Nitco.
each of
Nitco
them
is a
individually.
web
It would be
page
much
or
more
web
efficient, much
scanning
easier to
tool
manage, and much
where
less
it helps you to
expensive if we
find
could have all of these devices
vulnerabilities
reside on
and
the
can
same
show you
physical
exploits,
switch.
types
We
of
can do
exploits.
exactly that and continue to provide that
Some more
same
vulnerable,
functionality
and that's for
to the
web.
network
Okay,
and the
web
network
application
on the same
scanners.
switch.
Vulnerability scanners, of course, you can use Nessus, OpenVOS. We talked about that before. These are some debuggers. Immunity debugger is a API kind of, I wouldn't say API.
But all of these devices are connected to the same.
But this is
switch.
what you can use to
We brought
debug
it to the switch
code
and
or
defined
find an issue.
each interface
Now,
of
we
the
brought
switch
up
is belonging to either
a video of a
red
gentleman
VLAN
earlier
or the
this
blue
week. You remember that? It was like
VLAN.
10 minutes
Devices
long.
plugged
He was
into
going
the blue
through a
interfaces will be
debugger,
able to communicate with each other,
putting,
and only
there
the
you go,
devices plugged into the
looking
red
for
interfaces
vulnerabilities,
would be
tightening
able
up
to
code,
communicate
see
with
what
each
it
other.
means, cross-section the
Instead of
code,
colors,
drill
VLANs are
down the
defined
types
by
of
number.
line
So
code.
in this
What
switch,
is he
we have
looking
VLAN
for?
1,
Values,
VLAN 2,
variables,
and
integers.
VLAN 3.
That's what
You
these
can see that
debuggers
there are
do.
devices that are connected
It
to
allows you to
interfaces
drill
that are
down
connected
and look for
VLAN
something
1,
specific
other devices
inside
connected to interfaces
that
are configured
applicational
for VLAN
code
2, and still
to
other
see if there's a
devices that are configured
vulnerability
for
there.
interfaces that will only communicate on
Multi-purpose
VLAN 3.
tools, we already went
This
through
becomes
here.
a bit of a challenge when you want to
But for
connect
cloud
VLANs
infrastructure
across
assessment
individual
tools, you have
switches.
Scout
For
Suite,
example, you have two switches in this
Prowler,
scenario. One
and
of the
PACU,
switches has a VLAN
which
100
two
and
are
VLAN 200,
AWS
and the other
driven.
switch also has a VLAN
They're
100
proprietary.
and VLAN 200. We would like
Prowler's
VLAN
one,
100 on one switch
and
to be able to
PACU.
communicate
Thank you very
with
much.
VLAN 100 on the other switch.
Those two
Perform the same functionality for
are
VLANs.
AWS.
Of course,
That's
one of
their
the ways we do
proprietary
this is to
stuff,
simply
and
connect
they use
an
it on their
Ethernet cable
stuff
between VLAN 200
for
on
cloud,
both
of
switches
course.
and connect another Ethernet cable between VLAN 100 on both switches.
All right, we looked at
You can
CVSS
tell, however,
scores.
that we're going to run into problems if we want to connect
We noticed that in
100 or
in
even
CVSS
1,000
scores,
VLANs across both
this
of
is
these
what you're gonna
switches.
see. You have to
We
break down
can't
the attack
connect
vector. They may
1,000
ask you in the
interfaces
string.
across each of these.
Remember, there's a
So
code of
instead,
stuff
we
that's
should
at the
find a
bottom,
way
right?
to connect these switches together by
It
using
starts
a
with the,
minimum
we already
of
said that there's 4 different ones, right?
We can
And
do
then
this
in
by
each
deploying
one,
a
it may
VLAN
say
trunk.
it's talking about the
This is also
base, and then it
referred to
says,
as
what's
a
the attack vector in the base?
trunk. category.1Q
Then it
trunk.
may say, oh,
Instead of having these multiple
P for physical.
Ethernet connections between
That could be an
VLANs, we
attack
have a
vector,
single Ethernet
right?
connection between
So
these two
within the
switches.
string code, which goes left to right, it starts with the first metric, goes to the second metric somewhere in here, third metric, and ends at the last. The last metric usually has, if you see this,
So how is the trunk
they
connection
break this
able
down
to
in the
track
last
what
metric.
traffic is coming from
CIA.
VLAN 100 and what traffic is
Confidentiality,
coming from
integrity,
the way we do
and
this is by tagging each frame. This is a normal Ethernet frame. We have a preamble, a start frame delimiter, a destination MAC, a source MAC, a type, a
got
payload,
him.
and a frame.
Got y'all. Am I gonna get a point finally?
Tags into this frame.
Jesus,
We're going to add an
Mark.
additional field
Listen,
right in the
step
middle,
away
right
from
after
the
source
keyboard.
MAC address. And we refer to this as
Is it availability?
these
Yes,
VLAN
it's
tags
available.
are 12 bits
Gotta have it
long, and if
available.
we're not counting the VLAN
Look
numbers
at y'all.
that are reserved,
There you go,
we can have
Mr. T.
4,000
Thank you very much. That's what it looks like, going from left to right. You gotta look at it.
connection.
So,
This makes
we
the
give y'all
process
both some
relatively
rockets.
easy for connecting
If I
these
had
VLANs
basketballs, I'd do it.
between switches.
Listen.
Instead of having 4,000
be familiar with
physical
that.
interfaces that we are connecting to each other, we have a single interface.
It tells you about the attack complexity. It tells you in those different sections what privileges were required, was there user interaction needed, and then it talks about the scope. This is all in the CVSS score, going left to right. Then it talks about impact, and again, CIA. Then you have true, false positives, true, false negatives. Always researching. Okay, I don't know if y'all paying attention if I ask this question. What would it be? I'm over here now. What would it be if I see
that is connected to an interface defined as VLAN 200?
I shouldn't be in the system looking at the kernel's papers on his private drive, but the system never goes off.
It will be sent to the trunk interface on this switch. At that time, an additional
Remotely, I get into his share drive. I shouldn't even be there. But nothing goes off to tell anybody that I shouldn't be there.
The switch that receives that
Yes, that's a true negative.
tag, see that it was destined for VLAN 200. It will remove the tag from the frame and send that traffic to the end
Or is it?
station. So now we have a much more simplified design. Instead of having a
You're right, it's a
separate
true
cable
negative.
that's running between switches for
No, it is.
VLAN 1, VLAN 2,
Because there was
VLAN 3,
no
we can have a
reporting
single
done. There was
Ethernet
no
connection between
event
these two
triggered.
that simply
There was
turn all of
nothing.
the
There was a
traffic
negative
into
response.
when
right?
you first configure a switch,
And not only,
there
it
will
wasn't
be a
half,
default
but
VLAN
it was like
with a
fully,
switch
there was
that
nothing
means
that went
every
off.
device
That's a
connected
true
to the
negative.
switch by default
So when you go to research that, like, wait a minute,
commonly this is
nothing
VLAN
went
1
off? Yeah,
is
you really gotta
defined
adjust some
as the
stuff.
default VLAN.
It wasn't
There's
detected, but you were
another
there
type of
anyway,
VLAN
correct.
configuration that you would have
All right,
inside
so y'all
the
understand
switch
that, so I'm gonna
as
keep
a
on going.
native VLAN. A native VLAN is one that can traverse
All right, let's
the
get
trunk.
down. Y'all know
A
0
VLAN
days, so I'm not even
tag
gonna,
is not
we know
added to
that.
any of
All
the
right, let's go
traffic
down
going
to
over that trunk connection. So it's common to define a single
cross-site
native VLAN
scripting.
within
These
a
are the
switch
different
that will
attacks,
never
or different
be
things you
tagged
can,
as that
controls you can
traffic
put in
is sent
place to
over that
mitigate
trunk
attacks and
connection.
software
This is
vulnerability.
because there are some devices that will
A reflective
not
attack.
over an 802.1q network, and
Easiest
some
way
of
I
the
can explain it.
administrative functions within your switches, where switches are communicating with each other, may need to use the native VLAN to perform that
Okay.
communication. For example, management
Me and Elaine are,
switch
we're facing each
notification
other.
messages may use the native VLAN rather than
I
the
pick,
tag
okay,
that's
I'm asking Elaine
inside
something.
of that switch.
I'm on the external. I'm outside looking at him on the inside. Y'all with me so far?
Is identical on the other switch that you're connecting to.
I take vulnerability of his computer. But at this time, if we think how to relate this, this is a reflective attack. I have taken control of Elaine's computer. As an example to show this, I'm standing in front of Elaine, like right now. But you're like, okay, explain to me a reflective attack. Well, I'm going to use his host to send commands or requests to the server. I'm basically using his item. He said my brain hurts now. But Elaine holds up a mirror and reflects back to me. So now I'm looking at myself. So he's reflecting back. Then I hold up a mirror and reflect back. We're reflecting. I'm using his host to get information, to put it right back on him to get me some more information. We're gonna keep bouncing it back and forth until one of us stops. Right?
That is a reflective type of attack where I'm using his host computer as the originator to pull from. But if anything goes wrong and any request I need to further make, I'm putting it back on the lane to really set him up to take the fall. That's basically what I'm doing. I'm using his computer as a ghost host to get what I need and to put it back on him. So if it all falls, Elaine's holding back. He's got it. They're gonna come looking at his computer. It's like I wasn't even. You like that, huh, Brian? I see his eyes like, yeah, I like them type of text. Mr. Hacker, man. He's probably flying a drone over Turkey right now. We'll see. Okay, he's on a mission. But that's what's going on. The persistent attack, you know what that is. Buffer overflow, integer. Now, buffer overflow, putting too much into the buffer, it being virtual memory and or memory for fetch files. It's too much to handle. If we're looking at an integer overflow, all you're saying is all of these mathematical equations that belong to a program, yeah, we're gonna change some values in there and make it so much, we're pretty much gonna lock up the memory. Something that should take 5 plus 5 equals 10, we're gonna change that thing to be exatrillion amount of computations. Computer's gonna shut down. Y'all get me? I'm just taking advantage of the math. I'm taking advantage of the math. Okay? The heap. Whoa. Here's one here. What's the heap one? I've done two. You do two.
Wait, the what?
Leah says, true positive, yes, vulnerability, alerted. Which one is that for? Is that for the integer? Sounds like gummies.
What's for the previous one?
True positive, yes, vulnerability. Oh yeah, okay, here we go. False positive, she put the chart in there. No vulnerability, yes, alerted. True negative, that's the one we were talking about. No and no. That's like Frankie looking at somebody trying to walk in my house, and then he asked them, would you like something to drink? That's a no. And then false negative, vulnerability, nothing got alert. Yep, there you go, Mr. T. Heap data is data structured like a pyramid. It's like a pile of like a Dairy Queen cone, right?
This requires you to use
It's a pile of
recognize that you're connected to both a phone and a computer at the same time.
Yep. So Michael said, you do too, and I do too. Yep. So we're stacked.
So now with this switch configuration, we can assign.
I did buffer and integer. Y'all do heap and stack. What's stack?
All of that traffic to our switch, where it will be able to break those two apart and put them on the correct VLAN for that particular use. This means we can now download as much information as we like on our computer while we're on the phone communicating with others.
DQ is the what is my close place and the first out of code. Last in, first out of code. What's the stack? Last in, first out with code. Oh, I thought you were relating that to Dairy Queen. Okay, gotcha.
Interface, a switch interface,
coding that particular order. All right, gotcha.
There are a number of options
Good stuff.
available. In this
Now,
video, we'll look at some of
you might see one question talking about this.
We can start with the basic connectivity that we have to the
broken access control.
An Ethernet cable. There are a number.
We gave an example of the API.
And two of the most
the connection between the app on your phone connecting to an intermediate server and doing something, that access could have had a vulnerability and been exploited, and now you can't. That's broken access control.
1 gig connection.
And we're not just talking about just the link. We're talking about secure control, like
is the same on both sides.
the back door is open.
Computer that's connecting to
Somebody's
the
gotten
switch,
in there and taken it
speed of
over.
Both of them
All right?
has to be configured
Or they're
the same.
monitoring.
In many cases, we would set this to automatically configure itself, so you can simply plug in any device and
Mike,
the
I got
switch
your
will
business.
automatically adjust to the configured
All right.
speed.
So,
Another option we might
then
have available
cryptographic
is either half
features.
duplex or full duplex. In most cases, this is also
Okay,
set to
we want to
automatic.
talk about
But if
this.
you do
Why not
set
just
this
add some
manually
examples?
on both of these devices, you have to make sure that both of them
Cryptographic.
are set to be the same. If you have the speeds mismatched on both sides, the connection will not work at all. You'll never get a link like.
What's the purpose of a
If you
hash?
mix the duplex configuration, where one side is set to half duplex and the other
Even
side
though it's
is
not
set to
crypto,
full duplex,
it's integrity.
you'll
It
find
still
the
applies.
connection does
Cool,
operate,
thank you.
but you'll notice that it
What
doesn't
does, we already
optimize
talked about, what are the
as it should
elements
be.
needed to
In
make
fact,
a
you'll have very poor
certificate?
performance if you start putting a lot of traffic over that link. This is why
Key.
one of the initial configurations we'll look for
Hash.
when we're troubleshooting Ethernet
Crypto
is the speed
equals
and the
they
duplex to make
salt.
sure that
There's
they're
another
the same
one.
on
You can
both
throw some
sides
salt
of
in the
connection.
game.
If those match, then we'll shift
All right.
our focus to the
Sprinkle me,
Ethernet
man.
protocol, or the
Sprinkle me,
IP
man.
configuration
E40.
for that
Now.
interface. This might be an
So,
Ethernet connection. It might be a
you can have
VLAN
salt. Now,
config.
salt
You might be
is
setting up management interfaces. And all of
ooh-wee.
this will need an IP
Like,
address.
oh, I
a
said that like
sub-address,
Nate
a
Dogg.
bulk gateway,
Ooh-wee.
or perhaps other IP
All right.
configurations as well. These will usually
What you can have is a
be
password
assigned by a network administrator.
like
So
that,
you'll want to
and then you'll
make sure that
add
the IP address,
on the
sub-address,
end, you
default
could
key,
add
DNS
the
settings,
hash.
and everything else matches the configuration that we've received.
Now you have the hash. Now you can
This
add some
configuration doesn't
salt in the
match what
game.
we've been given.
Meaning
Let's
it's
say we're using a
randomized
different
extra
default gateway IP address, or we
bits
put in the
or
incorrect
integers
subnet
or
mask,
whatever
and we may
mathematically.
find
You
we're
can
unable
add it
to
on the
connect
end
to other
to
IP devices on
extend
this network.
the number
Fortunately, this is a relatively easy
randomly.
configuration to
It cuts
validate.
down on
You can
people
simply look at what we've
having
been given,
password
look at what
attacks
we've
or stealing
configured in the system,
credentials.
and make sure
So
that
if you
both
put all
match.
three of those together with like the
Another
password,
useful
with the hash,
configuration,
with the
especially
salt,
between
boom,
switches,
there you go.
would be one for
It
link
just extends it.
aggregation. This
All right.
is sometimes referred to as port binding, or you might see it abbreviated as
Cross-site
LAG,
scripting and injection.
aggregation.
Put
This
something in
means
some
that we are
web
connecting
code that
multiple
shouldn't be there.
interfaces together on
We've
those
already done
devices,
directory
which
traversal.
normally we would not want to do because we would be
Do I need to go through
If you
into life
configured all of those
or anything
interfaces
outdated?
as
Who's
link
unsure about
aggregation,
that by this
the
time?
switch will interpret them as one
This
very
point in time in
large
the whole
connection
course.
rather than for
Oh.
individual
All right,
connections.
Elaine,
So
like, I
all
got
four
it.
of these
Move
were
on.
gigabit Ethernet connections between the switch. We would configure those.
Charles
as
says, is that why you make a
now
password and when you go back and look it up, it could
to
be
able to
mycc123, but it
communicate
looks
between
like
those two
ooh,
Some
like Nate Dogg
switches
would say,
will
ooh,
support an
ooh,
automatic
ooh, wait.
configuration of
Yeah,
this
to fill in
aggregation
the position.
using a protocol
Yeah,
called
it's extending it.
LACP. This is the link
putting some
aggregation
salt in the
control
game.
protocol. This allows you to simply configure the
Identification
interface as
and
LACP,
authentication fit. Well,
plug
we
in
talked
the
about that.
interfaces,
Boom,
and
boom,
all of
boom.
the
All right, let's go
underlying
to
link
some
aggregation
real
configs
stuff. How
will
about that? Let's
automatically
move down.
configure themselves between those two devices. If you were to capture
Controls,
traffic between
baby.
these devices, you would see LACP traffic being transferred from one switch to
Okay,
another.
we're gonna tag team this one.
To be able to have the most efficient communication from one device to another, we need
what
to
is
be
one
sure
managerial
synchronize
control
across
that you
will not be
could put in place?
fragmented along the way. Since we don't always know what networks are located between
Nice.
two devices,
That
there
was
may
quick.
be times when our data
What's
is
one
fragmented
operational
and
control
therefore is
you can
less
put in place?
efficient
Policy?
to
That's a good
transfer
one.
across the network.
Ah, damn, he just answered it. Policy. Way to go, mister. Man, listen, y'all got the keyboard smoking.
Then we have to
All right.
resend the
What's the
entire
technical
frame
control?
again. Normally, the determination
Charles,
of the most
list.
optimal MTU or maximum
All right, list the rest.
transmission
Prevent
unit is done automatically when you first connect to a device. But sometimes
Y'all way ahead of me.
firewalls
They're like, James, keep
allow the
up. All right,
automated
I'm
process
trying to.
to work
Shoot.
properly, and you may need to manually
What's the
configure
preventive?
an MTU
Guard,
on your system.
detective,
On some networks, we're not trying
Camera,
to
honey.
minimize the
All right,
size
responsive.
of communication. Instead, we're trying
Us.
to maximize the size of
Oh,
and one of the ways we can do that
they
is
not like
what we
us.
call jumbo
They not
frames.
like us.
Ethernet frames by default are 50
Rockets,
bytes
baby.
in length. If we're transferring large amounts
All
of
right,
data,
motion
we may want
detectors,
to
correcto.
increase the size of those frames to make the
What's the
communication
corrective?
that much more efficient. And with jumbo frames, you can increase the size of an Ethernet frame up to 9,000.
Something shouldn't be working the way it's working.
16 bytes of
Pay up.
MTU. On many devices, you'll find that they'll use 9,000 as the accepted high end of a jumbo frame.
Could that be a corrective
Here's the
control, a
configuration
payout through
on my
insurance?
computer that says that I can configure frame sizes on my network.
Like
to
buy
between
new stuff to correct a
1280
mistake,
and
it
9,000
transfers.
bytes. This means I can transfer.
Kevin
a
says
single
anything that
frame
is fixed
contains
because of a
the same amount
vulnerability
of
is
information
identified. That's a
as
corrective.
6
Yes, that is a
normal on the
corrective
same
control.
network. This
I'm
means
looking
there are
at
fewer packets
patches.
to have to switch or
I'll
route
take
through my
that.
network, and I can
Yeah.
transfer much more in a shorter amount of time.
I can see that.
The
Patches,
challenge, though,
corrective
is
control.
all of the devices
Or
that are
shim.
in that communications path must understand.
But if you did
jumbo
notice something,
frames.
he's like, oh,
So
this is
all
jacked
of your
up. You ain't got
switches,
nothing yet.
all
A
of your
shim is
routers, and
good.
other devices you're communicating to
All right,
have
y'all
to
got it.
also be configured to use
Moving on.
these jumbo frames. If there is any device in the middle of this
Y'all good with all
that
this?
doesn't
Patch
understand
management,
jumbo frames,
maintenance
then they can
window.
drop these frames and you won't be able to
All right, here's the
use
risk
that
part.
device at all.
You can accept it, transfer it, avoid it, mitigate it. Accept is point blank. I think we understand that one. What's the transferring risk? What's transferring the risk? Insurance.
If you
Gotcha.
had two switches
Avoiding is
and
avoiding.
you connected them together.
What's
with an
mitigating
Ethernet
it?
cable, and then you connected another
How can I
Ethernet
mitigate?
cable to those switches, you would
There you
create
go.
a
Reduce
loop
it.
on the network.
By
This
using
means an
firewall
Ethernet frame
rules or
would
something
loop
else.
around
All right,
that
gotcha. All
particular
right.
connection until you disconnected one of those cables.
You'll
There's
see
no
this one.
mechanism at the MAC
This is
address
one
level to
that's
count
important
how
out of
many
this.
times you've seen a
What's the
frame.
bug bounty?
So as these frames are going around this loop, you're adding more and more frames to the network.
It
all
is
the
on the
time.
dark web,
Those
usually.
are continuing to go around this loop. And
Or it's
eventually
through
you'll
a
overwhelm
proprietary
the
website where they're
passwords of the
inviting
switches.
you to do
This can
something.
happen relatively quickly. Once you create
There you
a
go.
network,
Charles said it. Pay
might
someone
be
to
a
find
number
a
of
hole.
seconds until people
Yep.
start calling the help desk stating that
And
the
then this
network
will
is
help
down.
you to
Fortunately, this is
reduce
relatively easy
your
to
attack
resolve. You
surface.
simply go back to the switch
Way to
where
go.
you plugged in that cable, you disconnect the cable, which removes the loop from the network, and now everything is back up
All right.
and running. But of course, we're
Threat
not
modeling
understanding
is
that
taking
there's
all of
plug
your
or unplug
telemetry,
cable from a switch.
anything that
It's
we've
some
talked
type of
about today,
automated method to recognize
and what you've
the
learned
network
from the
and
beginning of
prevent
this
those
class
loops
to
from
this
occurring.
point today,
Fortunately, we have
all
a
goes
standard
into
table to
threat modeling.
recognize and prevent loops on a network. This is the
That's all you're doing.
802.1
You're using what you learned to look at your network to say, how can I be taken advantage of, meaning my vulnerability,
on our switch in a number of different ways.
ports. Okay, I'm looking at this computer, it's out in the open. Remember I said I went to the hospital this weekend in the ER? I saw the computer with the back of the printer facing to me. I see an exposed Cat 5. I see where I can plug in a thumb drive. That's an assessment. It's vulnerability assessment. That's threat modeling. Then I can say, through all of these vectors I can get in, what can I do from there? What known threats can be used to exploit that? What can I do to combat that? That's all threat modeling is. You make yourself a playbook and a chart. That's all you're doing.
And then it will configure
Okay.
an interface to
So,
be forwarding, which means
that
traffic
is what it is.
transmitted through that interface, or will it configure an interface
All right.
to be blocking? We might
We
also
good?
have interfaces that are administratively
We good for
disabled. Those obviously would not participate.
That's the review for
in the
today.
spanning tree
Aaliyah
process.
says, is input
There's a
validation
network
like
that
when
is
you can
already
only
running
put
the
a
spanning
birthday
tree.
in a
There are number
specific
of switches
field
that
and
are
nothing else?
identified as
That
bridge
is.
1, bridge 6, bridge 5, and
On the
so
back end,
you can see there are
for
5
you to
of them
only
in
do
this
that,
particular
somebody
design.
had to be
And you can see
testing
that
it,
many of these switches are
the
connected to each
input,
other.
to see
And
what
in that
replies
spanning
back.
tree running, there would
So
be a loop
they pay somebody to put
already.
all day. That's like me paying Martin to come in and say,
It's operational.
thanks for joining us, Martin. We're paying you $10 an hour to sit here and throw anything you can into this field, but we're trying to get it where it only returns this.
This is the interface.
He could be a coder,
that is
and they know he's real good, and he's gonna try to break it.
bridge on the network.
That's input
There's also
validation.
a designated port, which would be
And
any
then
other
something might pop up,
traffic
and Martin's
that is
like,
not
got
the
you.
port that
How'd
is
you do that?
directly
All I did was
to the
this.
bridge.
Well,
And
how do
there
we
are
fix it?
blocked
He's
ports.
like,
These are ports where spanning
this is what you
tree
need to
has
do.
disabled that port from sending or receiving
And like, okay,
traffic.
try it again.
You can see on this network
You know,
that
agile
bridge 21
method.
has a blocked port,
Agile
and
method.
bridge 11 has
Mhm.
a blocked port, and those have been blocked so that there
Yep,
is
has to
not
be in a
loop
specific
on the
format
network.
because it
If
cuts
we were
down
communicating from
on
bridge 11, you can see there's
folks
a
like
single
Martin
root
that
port,
know how to
and
use
follow
its
that all
code
the way back,
against
those
itself.
root ports to the final root bridge.
Right?
The designated ports are
Yes,
also
indeedy.
available to be able to send and receive traffic.
All right, and any
In this
questions so
scenario,
far?
let's say that we're on network A
Those are the
and we've been
top two.
communicating with the device
Top
on
two.
network M. You can see that we can
Highest
communicate
percentage
with bridge
domains
6,
on this
which
example.
has a designated port and
So that's
a root port
60%.
that allows us access to network in.
All right, everybody take
What if there is a problem on this network and we lose
Mike, I read your
connectivity
message.
between network A and bridge 6? Now we
You
need
talk
some
about it like
other
it's
way to
nothing.
communicate to network A.
This took years. This ain't like,
Port on bridge 11,
yeah,
so we would not be able to communicate through
years.
that connection. Fortunately, Spanning Tree
Didn't happen overnight.
recognizes that we have this disconnection.
All right, everybody, take a break. See you in 10 of.
And relearning the topology of the existing network. Spanning Tree has changed bridge 5 so that the root port is now on the other side, and it has removed the block port on bridge 11, allowing us on network A to be able to now communicate all the way through the network back to network M without having another loop on the network. On many networks, we do talk about enabling Spanning Tree and making sure that our Spanning Tree configuration is turned on inside of our switches, but in reality these days we're probably running a newer version of Spanning Tree called the Rapid Spanning Tree Protocol. This standard is the 802.1W standard. In the original Spanning Tree protocol, it might take 30 to 50 seconds for the convergence process to occur. And on today's networks, that is a very long time to wait without any type of connectivity. With Rapid Spanning Tree Protocol, this convergence process goes down to about 6 seconds, which means anytime there's a disruption on the network, we can be back up and running relatively quickly. Fortunately, this Rapid Spanning Tree Protocol is backwards compatible with the original Spanning Tree, so if you have a mixed set of devices on your network that support one or the other standard, you can run them all at the same time. Fortunately, Rapid Spanning Tree Protocol works very similar to the original Spanning Tree configuration. It simply operates much faster. There are some shortcuts and other configuration settings within the Rapid Spanning Tree Protocol, but it has such familiarity that if you understand Spanning Tree Protocol, it will be very easy for you to understand the details of Rapid Spanning Tree Protocol. We become so accustomed to wireless networks being available that we often forget that there's a lot of work that happens behind the scenes to create these wireless connections. This work is done primarily by the Institute of Electrical and Electronics Engineers, or the IEEE. There's a committee in the IEEE called the 802.11 Committee, and that is the committee that focuses on creating worldwide standards for wireless networking. In the past, we've referred to the standards name to be able to describe the network. For example, we'll describe 802.11ac, 802.11ax, or 802.11be. The IEEE committee realized that these numbers and letters combinations weren't very appealing for most people, so they've also assigned separate names that are a little easier to keep track of. For example, 802.11ac is Wi-Fi 5. 802.11ax is Wi-Fi 6 and Wi-Fi 6E, the extended version of Wi-Fi 6, and 802.11be is also called Wi-Fi 7. As additional major releases of the 802.11 wireless standards are released, they will also increment those Wi-Fi numbers, so in the future we should see Wi-Fi 8, Wi-Fi 9, and so on. There are a number of technologies used by 802.11 wireless networking, and the first is the frequencies that are in use. 802.11 commonly uses 2.4 gigahertz, 5 gigahertz, and 6 gigahertz frequency ranges. Sometimes there's a combination of those. You may have an access point that supports both 2.4 and 5 gigahertz, and some access points may support all of those frequencies at the same time. Instead of having to memorize individual frequency numbers, the IEEE has created groupings of these frequencies known as channels. These channels help us easily understand what frequencies we may be using. For example, on this access point, we're using both the 2.4 gigahertz range and the 5 gigahertz range. The 2.4 gigahertz range is using channel 6, which is centered on 2.437 gigahertz, and the 5 gigahertz band is using channel 44, which is centered on 5.220 gigahertz. You can see that referring to this as channel 6 is much faster and more efficient than saying that this particular access point is centered on 2.437 gigahertz. The amount of frequency that we use is referred to as the wireless bandwidth. And when I say that channel 6 is centered on 2.437 gigahertz, there's actually more frequencies that we're using for that single channel. Different frequency bands have different sizes of bandwidths that can be used, but it's very common to see 20 megahertz, 40 megahertz, 80 megahertz, and 160 megahertz bandwidths. Here's a diagram that shows the 2.4 gigahertz range, the 5 gigahertz range, and the 6 gigahertz range that's used by 802.11 wireless networks. We'll start with the 2.4 gigahertz spectrum. You can see there are 3 non-overlapping channels in that particular range, and it's using the 20 megahertz bandwidth to describe those 3 channels. Next is the 5 gigahertz spectrum, and you can see there are many more frequencies available in the 5 gigahertz range. You'll also notice that we might use different bandwidths depending on the access point that we're using. So we might use anywhere from 20 megahertz to 160 megahertz, and you can see the ranges that are available for those particular frequencies. And in the 6 gigahertz range, we have even more frequencies available, giving us options to be able to transmit and use these wireless networks without conflicting with other wireless networks that might be nearby. As you can tell, there are many frequencies available to choose from for your wireless networks, but not every frequency is going to be the best one to use. There may be differences in the environment where you happen to be, where one frequency might work better than the other, or there may be other access points that are already using certain frequencies. You might also be using older devices that aren't able to communicate on the 5 or 6 gigahertz ranges and may only be able to communicate on 2.4 gigahertz frequencies. But if you have a modern wireless device, you might have options. Your phone, for example, may be able to support 2 or more different types of frequencies. It just needs to be able to choose the optimal frequency for where you happen to be. Your access points can be set up with a feature known as band steering. This allows you to specify how the users might be able to use the frequencies in the best possible way. For example, you might have a user that has a mobile phone, and that phone can support either a 2.4 gigahertz connection or a 5 gigahertz connection. And you might have access points that also support both of those frequencies. So which frequency does your phone choose when it's connecting to that access point? If band steering is not configured in the access point, the device will simply use the one that has the best possible signal. Sometimes that best signal will provide you with the best throughput, but that's not always the case. And you may find that you get better throughput using a different frequency, even though that frequency may not be the one that has the strongest signal. If band steering is turned on, the administrator of the access point can determine what frequency a user will choose if they have a choice. For example, if a user is connecting to an access point with band steering enabled, and that device can support either 2.4 gigahertz or 5 gigahertz, you can force it or steer it into using the 5 gigahertz frequencies by default. One of the challenges with these wireless networks is that each country makes its own decisions about how this wireless bandwidth is to be used. For example, in the United States, we have the Federal Communications Commission, and they are responsible for managing all of the frequency allocations in the US. Of course, the FCC can't control how other countries manage their frequencies, but they do work very closely with other countries around the world to make sure that everyone is properly managing these very important frequencies. Another challenge with this is that we are coming up with new technologies and new ways to use these frequencies all the time, and we sometimes have to make sure that different services can use similar frequencies without any type of conflict. The popularity of these wireless networks has almost required that all of these countries work together to come up with standards that everyone can agree on. A good example of these organizations working together can be found in the 802.11h standard. This adds a number of interoperability features to 802.11 wireless networks so that you can have many different wireless networks in one area and still allow all of those networks to work together. There are a series of guidelines for wireless communications that are published by the International Telecommunications Union. The ITU provides a worldwide approach to managing these many different wireless technologies. One of the things that is included in these standards is called DFS. This is Dynamic Frequency Selection. This allows our wireless access points to use frequencies that are not going to conflict with other access points that may already be operated. This is one of the reasons that when you turn on your wireless access point today, that you don't have to manually configure any of the wireless settings inside of that device. It automatically looks at the frequencies that are in use and chooses a series of frequencies for you that are not going to conflict with anything that may already be operating. And if something does change with the wireless environment and your access point needs to change its channel, it will tell all of the devices on that network to also move along with the access point. Another interoperability feature is TPC, or the Transmit Power Control. Traditionally, we've set the power that we would use for these wireless networks on our clients, but TPC puts the transmit power control in the hands of the access point. This means that the access point can tell a client to use less power to be able to communicate over this wireless network. This means that we can have many devices communicating at their optimal power level without having any type of conflict with other third-party services. When we think about wireless networking, we often think about connecting to an access point. But of course, you can communicate directly to another device without an access point. We refer to this as Independent Basic Service Set, or IBSS. You might also see this referred to as an ad hoc connection. This allows us to configure one device as an ad hoc connection, configure the other device as an ad hoc connection, and simply connect those two devices to each other over those wireless frequencies. You might have used this functionality when you've configured an Internet of Things device, such as a door lock or lights in your home. This is a way to connect to a device over an ad hoc connection, provide that device with information about your existing wireless network, and then have that device connect directly to the access point. And in most environments, we have an access point that many different devices are connecting to be able to network everyone together. Behind the scenes, we're using different parameters to configure this device. Two of those parameters are the SSID and the BSSID. SSID stands for the Service Set Identifier, and it's the name of the wireless network that we're connecting to. So you might have an access point with an SSID of SGC1, and when you bring up the list of all of the available access points in your area, you will see that SSID name appear in your list of available networks. Of course, this same SSID might be configured on multiple access points, especially if you have a very large home or you're in an environment where there are multiple areas of the building and you want to have wireless connectivity wherever you might be in that building. To be able to differentiate between one access point and the other, we need some type of hardware address on that access point, and that hardware address is known as the BSSID. This is the Basic Service Set Identifier. So although there is a wireless network name that we see, such as SGC1, there is also a hardware address that we normally do not see behind the scenes. In this case, this wireless access point has a BSSID of 603 Delta 26112233. As we've already mentioned, in your home or a very large business, you may have tens, hundreds, or even thousands of access points to manage. All of these access points need to be able to work together so that as you are passing from one building to another or from one area of the building to the other, you're able to seamlessly move from one wireless access point to the other. This is often done by using the same SSID or wireless network name on each of the wireless access points. We refer to this shared network name that's used across access points as an ESSID. The E stands for the Extended Service Set Identifier. With the ESSID configured across all of these different access points, you can start on one end of the building, walk to the other end of the building, and you will be moving automatically and seamlessly from one access point to the other. Here's a configuration that uses ESSID to provide that seamless roaming from one access point to the other. In the middle at the top, we have a network switch. This switch has an Ethernet connection to an access point on the left and an access point on the right. And you can see that the BSSID, or the Basic Service Set Identifier, which is the hardware address of the access point, is different on this access point than it is for the other. Although these are obviously two different pieces of hardware, they are sharing the same SSID. You can see it's configured as SGC1 on this access point, is also configured as SGC1 on the other access point. As we move outside the range of one access point and move into the range of another access point, that access point will automatically pick up that we are nearby and seamlessly connect this device to that same SSID without any notification on your mobile device. This means you can continue to surf the internet, transfer files, and use the network normally, even if you happen to be moving at the same time. When you first connect to a wireless access point, you may be prompted with a screen that gives you information about the network or requires you to authenticate to gain access to that network. We refer to this screen that appears and the prompt with the authentication credentials as a captive portal screen. For this captive portal to work, there is a centralized access table that identifies individuals that are already authenticated to the wireless network. And if it notices there's a new device that has not previously authenticated, it will present this captive portal screen to the end user. On the captive portal screen, there may be a series of terms that have to be agreed to, or it may prompt for a username, a password, or some other type of authentication factor. If those credentials are entered properly, then that information is added to the access table and you gain access to that wireless network for a predefined amount of time. For example, your captive portal may be good for 24 hours, and at the end of that 24-hour period, you have to re-authenticate to gain another 24 hours of access. There are many different ways to configure security on a wireless network. And if you look at the configuration of your access point, you may find that there are a number of different options that you can choose from. For example, on this access point, the security level is currently defined as WPA2 personal. This access point can also disable security. It can configure a security mode on this access point known as OWE, which stands for Opportunistic Wireless Encryption, which effectively allows someone to connect to the wireless network but prevents them from communicating directly to any other wireless device. This access point also supports WEP, different flavors of WPA, WPA2, and WPA3. An open system, of course, means there is no security, there's no authentication process, and anyone on this wireless network can communicate to anyone else on this wireless network. This access point supports WPA, WPA2, and WPA3 using a personal type of security. Sometimes you'll see this referred to as PSK, which stands for pre-shared key. This means to gain access to this wireless network, we need to provide someone with a pre-shared key that everyone will use. For example, you may be at a coffee shop and there may be a notice at the coffee shop that the pre-shared key that everyone can use to access the network is hot coffee. Of course, if you're in a business environment, having everyone share the same password for the wireless network is inherently insecure. So most enterprises would use a different type of wireless security known as enterprise or 802.1x security. This allows the network administrator to require a username, password, or some other type of authentication to gain access to the wireless network. And most people will use their own personal credentials to be able to provide that access. This means you would use the same username and password you would normally use to log into other devices in that same enterprise network. This means if someone leaves the organization and their account is disabled, they no longer have access to that wireless network. If you look at the different antennas that are used on many of today's wireless networks, you may notice a number of different styles. The style of antenna that you see connected to this access point is an omnidirectional antenna. It's a very common antenna type to find on our consumer or home-based access points. An omnidirectional antenna will evenly distribute that wireless signal on all sides of the antenna. So you can put your access point in the middle of the room and everyone in the room will have the same signal strength as everyone else. This means you can put your access point in a centralized area and anyone who's nearby will be able to gain access to the wireless network. But this may not be the optimal antenna type to use. For example, your access point may be in the corner of an outside room and you're effectively only seeing a portion of that signal while the rest of it on this omnidirectional antenna is sent to places where no one will ever connect. In that scenario, you might want to use a directional antenna where you can take that wireless signal and send it into a single direction. This allows you to focus the transmission and receiving of wireless signals to a device that may be in the corner of a room or may be connecting different buildings to each other. You'll often see these antennas measured as a total number of decibels. For example, a directional antenna may increase the performance of that signal by a certain decibels of gain. For example, you may see in the specifications of a directional antenna that it effectively increases the overall power by 3 dB. And for every 3 dB, we are effectively doubling the amount of power available. One type of directional antenna is a Yagi antenna. This is an example of a Yagi antenna. It is very directional and has a very high amount of gain. We also have other directional types such as a parabolic antenna, where multiple signals can come in and bounce into a single feed horn in the front, so it's focusing all of those signals into a single point on the antenna. This is especially useful over longer distances where you need to collect that signal and focus it into a single spot. Most of the access points that we use at home are autonomous access points. This means that the access point doesn't require any type of additional hardware or software to be able to operate. It's effectively a standalone device that doesn't rely on anything else to be able to maintain that wireless connectivity. But in an enterprise, you may not be using autonomous access points. Instead, you may be using lightweight access points. This separates the wireless functionality into the hardware that you would mount into the ceiling, and the configurations and intelligence of that device are often maintained on the switch the access point is connected to. This not only allows us to have less expensive access points that we can deploy, it also gives us functionality for being able to manage those devices. One standard for managing wireless access point is known as CAPWAP. This is control and provisioning of wireless access points, and it allows you as the network administrator to manage and configure all of these wireless access points from one central management station. We refer to this central station as a wireless LAN controller. It allows us to connect and view the entire wireless infrastructure from one single screen. We often refer to this as a single pane of glass. From this single management station, we can deploy new access points. We can monitor the performance of our existing access point infrastructure. We can make changes to the configuration of our wireless network and deploy those changes to some or all of our access points. And this might also create reports showing us how much of the wireless network is being used and by whom. This wireless LAN controller is often paired with the wireless access points themselves, so you're often getting the access points and the wireless management station all from the same manufacturer. There are a number of different ways to connect and configure wireless networks, and in this video we'll look at some of these different wireless network types. One popular wireless network type, especially in home-based environments, is a wireless mesh. This is where you would have multiple access points that can all communicate to each other within a relatively close area. And then you would have other devices that are located on the outside of those access points that are able to communicate to that single access point and ultimately to the rest of the network. This meshing of access points in the middle is something that you would configure on the access point, and if you were to add additional access points onto this network, they would also be included in that same mesh of access points. Of course, this doesn't have to be access points. There are some devices that can mesh amongst each other in an ad hoc form. This allows for different options for sending data over these networks, because all of these devices are now communicating to each other. And if one device leaves the network, it can automatically identify that that device is no longer there and self-heal itself to maintain connectivity to everyone who's left on the wireless network. If you only have two devices, you might want to connect them together without an access point. We refer to this type of connectivity as an ad hoc connection. This is where you would use the 802.11 wireless functionality of your device, but you would not be directly connecting to an access point. This uses the 802.11 wireless network functionality of this device, but instead of connecting to an access point, you simply connect to the other wireless device. You might also see this referred to as an independent basic service set, or an IBSS. This might be something that is a very long-term connection. If all you have are two devices, you can simply connect those two together and they will communicate as long as that connection is available. But you might be using this on more of a temporary basis. This might be used in conjunction with an Internet of Things or IoT device, where you would initially connect to the IoT device over an ad hoc connection. This may allow you to transfer configuration details, such as the name of your larger wireless network and any security configurations that have to be included to connect to that wireless network. At that point, the ad hoc connection is then disabled and the Internet of Things device can connect to the larger access point network using those configuration parameters. Some wireless access points allow you to connect two devices directly to each other over a point-to-point mode. The point-to-point mode is commonly used to connect larger distances to each other. For example, one building connecting to another building. I've run this exact configuration between two homes, so you could have an access point in one house connected to a switch and all of the internal devices of that network connected to the same switch, and then you would have the same configuration in another home and have all of those networks now connected to each other over that point-to-point mode. Not all access points support this point-to-point mode, so you want to be sure that the software of the access point supports point-to-point, and you'll want to be sure that the hardware on this device is also able to transmit over that extended distance. You may, for example, require additional types of antennas to be able to bridge that gap between the access points. There might also be a requirement to change the power output between these two devices and to make sure you're using frequencies that are able to communicate over that longer distance. And perhaps the most common way to connect to a wireless network is in something called infrastructure mode. This is where you would have a centralized access point, and this is probably the type of wireless networking that you're using at home and in your office. All of the wireless devices in your home or office connect to that central access point, and you're able to communicate out to the wired network or between other wireless devices over that same access point. Some wireless access points give you the option to allow devices to communicate with each other over that wireless network, or to isolate each of these wireless devices to only be able to communicate directly to the access point and any networks beyond that access point. You'll want to check your access point to see how it's configured for these devices and make sure the proper security is configured on that device. The wireless networks we use both at home and in our businesses are sending private, confidential, and sensitive information all the time. And we're very concerned that someone might have access to that data, especially on a wireless medium that effectively could be tapped into and listened to by any device that happens to be nearby. One way that we provide security on this wireless network is to limit what users are able to access the network. We would commonly do this with some type of authentication method, such as a username, a password, or some type of multi-factor authentication. And of course, we want to be sure that everything sent over this wireless network is protected, so we need to add confidentiality in the form of encryption. And to be sure that we've received the correct information over this wireless network, we include a message integrity check so that we can verify the information that we've received is exactly the information that was originally sent. One of the first encryption types on wireless networks is a method known as wired equivalent privacy, or WEP. Unfortunately, WEP was discovered to have some significant cryptographic vulnerabilities, so we needed to very quickly replace WEP with something that was much more secure, and that replacement was known as WPA, or Wi-Fi Protected Access. WPA was implemented as a temporary stopgap between the insecure web and a more secure version of WPA. This first iteration of WPA was designed to work on exactly the same hardware as that older style web that we were replacing, but we knew that we would need enhanced security that we would not currently have available in this initial WPA. This replacement to WPA we named WPA2. This is Wi-Fi Protected Access version 2, and it's a version that's been around since 2004. You'll often see WPA2 referenced with a block cipher mode known as CCMP. If we were to to spell this out, it would be counter mode with cipher block chaining message authentication code protocol, or counter/CBC-MAC. This effectively combined encryption and integrity in the same protocol. The encryption was available with AES, and the message integrity check was enabled using CBC-MAC. The update to WPA2 is WPA3. This is Wi-Fi Protected Access version 3, and it was introduced in 2018. This includes a different and more capable block cipher mode known as GCNP. This is Galois Counter Mode Protocol. This continues to use AES for data confidentiality, and we are using a message integrity check with the Galois Message Authentication Code, or GMAC. If you're planning to implement any type of security in your wireless network, you want to use the highest level of security available in your access points and on your client devices. And if you have the option, you should consider upgrading all of your devices to use the most capable security method available. A distribution frame is an area of the network where you are passively terminating cables. This usually involves punch-down blocks like the ones we see here. It could be patch panels or any other method where we are terminating those cables, usually in a data center or some other large facility. You will usually find this distribution frame on the back wall of the data center, and it's often terminating cables that are coming in for your local area network and voice communication. And although the punch-down blocks and patch panels that we have on the wall are technically the distribution frame, we often refer to the entire room as the distribution frame room. For example, the primary distribution frame is called the main distribution frame, or MDF, and we often refer to the entire room where it's located as the MDF facility. The MDF is usually a single room. It's often the data center or central point of the network, and this is where we might bring in wide area network connections and punch those down, along with all of our internal local area connections as well. Since we have all of this connectivity in one place, it is a perfect testing point, especially if you need to test both your internal local networks and your external wide area network connections. And even if your network doesn't have this large set of punch-down blocks in the back, we sometimes even often refer to this central data center room as the MDF. Here's a view of one MDF. This one contains a number of different racks with computer equipment and the networking components as well. Here's another MDF. You can see a large number of punch-down blocks or patch panels that are on the single rack and some on individual racks as well, and it's intermixed with the equipment that we need to run inside of this data center. Another type of distribution frame is the intermediate distribution frame, or the IDF. Usually the IDF is in a separate floor or a separate building, and it's often directly connected to the MDF. Most IDFs these days include switches, routers, and other equipment that you need to be able to connect this area of the network to the larger MDF. You usually find this combination of MDFs and IDFs in medium to larger scale environments where you need to have many different remote rooms all connecting back to the central data center. Here's a view of what that would look like, where you have the MDF. Maybe this is where our internet connection comes in. There might be a core router and a core switch. You might even have file servers and database servers in the MDF. Maybe on different floors of the building, you would then have individual IDFs. In this case, there are two, but there might be more than that in this particular environment. And in the IDF, you might be connecting users on the floor to a central switch in the IDF, and that switch is connecting back to the main core switch in the MDF. We've already seen an example of an IDF and MDF, and one of the things that you'll notice is there are racks that are very common in each of those environments. That's because the racks that we use in these environments are standardized, and most rack sizes are 19-inch racks. They're 19 inches across in each of these, and we design our equipment to fit perfectly into that 19-inch width. You also notice that the equipment in these racks might also have different heights, and we have a standard for those heights known as a rack unit, or a U. One U would be 1.75 inches, and we can measure a different number of units based on that value. So you can easily tell somebody that we need 2U or 3U of space to be able to install a piece of equipment. And most racks, like the ones we see here, are generally about 42U in height. Although the width is standardized, the depth of these racks can often vary. There might be racks that are very shallow or others that might support a much longer piece of equipment that you would install. Fortunately, most devices follow this standardized form. We know that if we're receiving a piece of equipment that is rack mountable, that it will most likely be 19 inches wide. We'll just need to make sure that we have a rack that is deep enough to handle that particular piece of equipment. Since we have these standard widths, we can start stacking this equipment and using every bit of real estate that we might have available. For example, this system administrator has installed a server that's about 3U in height, and they're installing another set just above it so that they can stack them one right on top of the other. Now that we have all of this equipment in the data center and it's all running constantly, it's creating quite a bit of heat. We need to make sure that we have a way to cool this data center so that all of this equipment continues to work optimally. We would do this by implementing an HVAC or HVAC system. This stands for heating, ventilating, and air conditioning. This is very different than simply purchasing a window-mounted air conditioner and turning it on. There's a lot of engineering that goes to designing and implementing an HVAC system in these large data centers. For example, we not only need to make sure that the HVAC can support the amount of heat that's going to be created by these systems, we also need to make sure we have enough power to run the HVAC, and we also need to make sure this is integrated into the fire system so that we're able to turn this off automatically if a fire is detected. One thing that you'll notice in a data center is that the different aisles of the data center may be designated as a hot aisle or a cold aisle. This hot and cold aisle is an important designation, especially as we're installing new equipment into the data center. We want to be sure that we're installing the equipment in a way where the hot air is being blown into the hot aisle and it's pulling in cold air from the cold aisle. Here's a cross-reference of a data center. On the left and right sides, we have our HVAC system, and in this particular environment, the cold air is going under the floor and the hot air is being pulled out of the ceiling. The cycle starts with the HVAC creating the cold air, and that cold air is going underneath the floor in this raised floor environment. There are vents and holes in the floor that will allow the cold air to flow into a cold aisle. This is often the front of the servers, and the servers are pulling in that cold air to cool the inside of the server itself. Once that air is heated up, it will be sent out the back of the server into a hot aisle, and that hot air is going to rise into the ceiling, where it will then be pulled back into the HVAC, recooled, and the entire system repeats again. Here's a data center where we can see both the hot aisles and the cold aisles. You'll see the cold aisles are covered with this plastic to keep that cold air inside, and the hot aisles would be the ones on the outside without the plastic. You'll also notice this is a bit different than the previous diagram because there is a concrete floor and there's no way to have a raised floor in this environment. So it looks like they're blowing the cold air directly into the cold aisle from above. It's being pulled through into a hot aisle, and then it goes back into the ceiling where the entire process repeats. When we install network cabling, one of our goals is to not move or touch that cabling again. We want to be sure that once it's installed, we can trust that that cable will always be working optimally. One of the things that we'll commonly do is have all of the desks that are on a floor of a building all have single runs of wire all the way back to an IDF. Inside of the IDF closet, we'll have a patch panel, and commonly we might have a patch panel with a 110 block where we will punch down those wires onto the back side of the patch panel, and on the other side of the patch panel will be the traditional RJ45 modular connectors. This means that if we need to connect any user on the floor to any switch on our switches, all we have to do is run the appropriate cable from the RJ45 connector. We no longer have to touch any of the cable that's running from the back of this patch panel to the end user's desk. So we can begin installing all of the connections we need through these patch cables from the patch panel itself into the switch that we might be using. This also allows us to address any type of moves, adds, or changes. If someone out on the floor moves to a different desk, we can simply move where their patch cable happens to be and plug them into a different connection. And of course, if we hire new employees and we want to make sure that they have the correct network connectivity, we don't have to run additional cables because we've already run those cables. All we have to do is add new connections from our patch panel to the appropriate switch connection. Here's what this patch panel looks like in our IDF. You can see on this side of the patch panel, we have the RJ45 connections. We're coming out of those RJ45 connections and we're plugging them into the switches that are directly underneath. This means we can keep all of those cables in place between the patch panel and the desk out on the floor. All we have to change are the internal connections inside of our IDF. Here's another view of a patch panel. This one is connecting from the patch panel directly to the switch that's above it. And notice there are numbered connections on that patch panel, so we know exactly which desk we're connecting or disconnecting. There are similar but slightly different configurations for fiber optics. This is a fiber optic distribution panel where we're bringing in fiber runs from another building or another floor, and we're bringing all of those back to connections that we have access to on the distribution panel. One of the important characteristics when installing fiber optics is making sure that we don't exceed the bend radius. And you'll notice in this distribution panel that we are looping together in a very large loop the fiber to make sure that we don't break the fiber by bending it too far in the panel itself. And it looks like in this distribution panel we have some additional fiber that is wrapped around. We refer to this as a service loop, so that if we need to move this distribution panel or add additional fiber, we can simply extend it with the fiber that's already run. This gives us flexibility in the future to be able to make changes without having to rerun a very expensive fiber optic connection. In some of the previous pictures of the data centers, you saw that some of the racks were open, but there were some racks that were completely closed that had locks on the front of the rack. This is not uncommon in any type of data center because it allows the system administrator a level of additional security and control over the components inside of the rack. We'll often install these racks side by side directly to each other to optimize the space that we have in the data center. And it's not unusual to have a door on the front of the rack where we can have a lock and a way to prevent others from gaining access to the equipment inside of the rack. Here's a good example of racks that are completely locked up. You can see in this case that we do have ventilation in the front. There's often ventilation in the top and the bottom as well, so that the equipment inside is able to be cooled properly. Here's a closer view of these racks. You can see that each of these racks has a handle with a lock on it, and you can see where you would add the key to be able to gain access to the equipment that's on the inside. In this video, we're going to talk about power, and an important thing to remember is that you should never put yourself in a position where you will be able to, in some way, come in contact with any type of voltage. You want to be sure that when you're working with the device that you are always disconnecting from the power source before ever putting your hands or any part of you near that particular component. Even when you disconnect from the power source, you should also keep in mind that some devices will store a charge in capacitors. Older CRT monitors, laser printers, and other devices can easily shock you even when they're not connected to a power source. Your goal should never be to connect any part of your body to anything that could potentially be energized. For example, you should never connect yourself to the ground wire of an electrical system or anything else that might have some type of voltage go across it. If you respect electricity, you will have no problems keeping yourself and others around you safe as you're working on these devices. When you start looking into the electrical specifications and the design of electrical systems, you'll see a lot of different terms being used. One of those is an ampere. We often refer to this as an amp, and it's often abbreviated with the capital letter A. This value measures the rate of electrons that are moving past a particular point in a single second. You'll often hear electricity compared to a water hose, where electricity flowing through a wire is very similar to water that may be flowing through a water hose. The amount of water that you can fit through a hose will depend on the diameter of that hose, and the diameter would be the number of amps. We also measure electricity in terms of voltage. This is often abbreviated as volt or the capital letter V. This is describing a pressure of electricity flowing through a particular wire. If we go back to our hose analogy, as we are turning the water on, we are increasing the amount of pressure of that water through the hose, and as we increase the pressure, we are increasing the voltage. For example, you'll often see electrical systems described as a 120 volt system or a 240 volt system. And if you need to describe how much power is being used, we would describe that as a number of watts. You'll often see this abbreviated with a capital W. We can calculate watts by multiplying the number of volts times the number of amps. For example, if you're connected to a 120 volt power source and you have a device that is using 0.5 amps, you are using a total of 60 watts. The type of power that we usually get from our wall outlets is alternating current, or AC. AC power is relatively easy to distribute over long distances, so it is perfect to use for bringing into a home or an office. You'll often see alternating current abbreviated as AC, and it's often represented as the wavy line. This wavy line demonstrates the directional change of this power as it's moving through the wire. That up and down frequency of that wave is different depending on where you happen to live. If you're in the US or Canada, we commonly see 110 to 120 volts of alternating current, and it's usually running at a frequency of 60 hertz or 60 cycles per second. If you're in Europe, it's common to see 220 to 240 volts of AC current, and its frequency is 50 hertz. Our electrical components often use DC power to operate. This is direct current, where all of the current is moving in a single direction with a constant amount of voltage. This is often abbreviated with a DC, and the symbol for direct current is this solid line on top with the multiple lines across the bottom. This is why when we look on the back of our routers, our switches, and our other devices, we often see that we're plugging into a wall outlet with this alternating current, and we are converting that alternating current to direct current using the power supplies that are in those devices. This conversion may be occurring in power supplies built into the device, or it may be in the power cord that you're using to connect that device. And obviously, as an information technology professional, power is one of the most important components we have. None of these systems would work without this power source, so it's important to consider how our switches, our routers, and our other devices will continue to operate even if there is an interruption of that power. One way to protect yourself against a power outage is to use a UPS. This is an uninterruptible power supply. This is usually a device that is connected to our power source, and inside of this device are a number of batteries that provide us with additional power if we lose that main power connection. This can also help if the voltage on our line tends to drop a bit. We refer to that as a brownout. And if the voltage tends to spike or go much higher, we refer to that as a surge. The UPS will even out that particular surge or brownout and provide us with the power we need to remain up and running. There are a number of different types of uninterruptible power supplies. One of the least expensive are the offline or standby UPS, which is simply waiting for the power to go out before it kicks in. As you can imagine, there's a small amount of time where there would be no power available to your systems, and often with switches and routers, that small gap of time is enough to cause that device to reboot. One step up from that is the line interactive UPS. If you happen to have brownouts and your voltage begins to drop, the line interactive UPS will begin to increase the amount of power provided to be able to compensate for that drop. But many data centers prefer to run an online or double conversion UPS, where you are always running from battery power and the batteries are constantly being refreshed by the power source. If you lose the power source, it has no effect on the systems that are connected to the UPS because they've always been running from that primary battery power. There are many different types of UPSs with many types of features. There are some that can automatically shut down your system if the batteries happen to become very low. Some of them have a higher battery capacity than others. The number of outlets on the back of the UPS can vary, and some of them have additional interfaces to plug in phone lines or cable modem connections. Another useful power component is a PDU. This is a power distribution unit. And although it looks like a normal surge suppressor, these are actually relatively intelligent devices that allow us to remotely connect to the device, manage each of those interfaces, and even allow you to power off and power on a device from a remote location. You can see this one is a rack mountable unit, and we would put that in our rack and connect our routers and switches to these interfaces. There's also an Ethernet connection. We would assign an IP address to this device. Inside is a web server, and that allows us to connect and manage this device from wherever we happen to be. In the United States and indeed around the world, we have many different data centers that are operating 24 hours a day, 7 days a week. It is estimated that approximately 2% of all U.S. power consumption is used by these data centers. Much of the power we use in these data centers is to manage the environment where all of this equipment resides. This allows us to manage the humidity, the temperature, and other environmental controls. Managing humidity in a data center can be a bit of a challenge. If you have a high humidity, then you've got condensation, and having any type of water in a data center is never a good idea. If your humidity is too low, you could have excessive static discharge, which is also potentially harmful to the equipment. Many industry guidelines put the ideal humidity levels somewhere around 40 to 60%. This is high enough to prevent any type of static discharge.
All right, everybody, let's get our last break in for today.
This
See you
can
in
vary
10
a bit
minutes.
depending on the geography, but these humidity levels tend to be the average that you'll find in most data centers. A lot of this power also goes to keeping the data center cool. As this equipment is running, it's generating heat, and all of that heat needs to be cooled down. There is an optimal temperature range, and many data centers are trying to keep the temperature somewhere around 64 to 81 degrees Fahrenheit. The cooling equipment in our data centers is constantly working to keep the temperature at that range. But of course, there are external influences that can affect the temperature inside the building. For example, the outdoor temperature may increase or decrease, and that may add additional load to the cooling systems. You might also find that as your system load increases and you're creating more heat from the systems inside of the data center, that we will need to add additional cooling. Most data centers will have a well-engineered heating, ventilation, and air conditioning system. This is an HVAC. This HVAC system is designed to maintain a particular humidity and temperature level. Most of these HVAC systems have sensors that are located throughout the data center, and they're working to make sure that the same temperature and humidity is the same across the entire data center. Another important concern for data centers is what you do if there is a fire. Data centers contain a large amount of electrical equipment that are in a very large area, so we need to be sure that we have some way to suppress any type of fire. Normally, we would use water to be able to control a fire, but in an environment such as a data center, when you have this much electrical equipment, you'll want to use other means for fire suppression. If you were to look into the back of the data center, there's probably a tank that contains some type of inert gas or chemical agent that is designed to either suppress the fire or remove any type of oxygen from the air. If somebody pulls the fire alarm, all of those chemicals are dispersed throughout the entire data center, and although this may cause damage to the equipment, it will prevent a fire from spreading. You'll often see these fire suppression systems integrated with the existing HVAC. This means that if a fire is detected, the HVAC system will shut down and prevent any type of oxygen from feeding that fire. One common type of network documentation is the network map, and there are different types of network maps that you might want to create. One type is a physical network map, which shows the physical layout of the equipment, the cabling, and everything in between. This is an example of a physical network map. It shows a connection in from the internet with the physical cable plugging into the internet router, which can be found at 10.1.1.1. There's a physical wire connecting to the internet firewall, and then another wire connecting to the core router, which is located at 10.1.10.1. This physical connectivity continues on through the rest of the diagram, and if you were to go into this room, you can track back that cable to this equipment using this physical network map. We can often create these network maps using third-party software such as Visio, OmniGraffle, Glyphy.com, and many others. This software can be used to create physical network maps. It can also be used to create logical network maps. Logical network maps show a higher level view of connectivity where you're not focused on individual interfaces and cables, but more on how the entire network is connected. This is a logical network map that shows a cloud connection in the middle and different headquarters buildings connected from different locations into that single cloud. Obviously, in the middle of all of this are a number of routers, switches, and other servers, but all of that is broadly shown as a single location in a logical network map. These might be good maps to use if you're planning additional locations. You can view the layout of the existing wide area network cloud and then decide where the best location might be for another installation. And if you wanted to get into a detailed view of exactly where equipment is located and what that equipment looks like, you might want to use a rack diagram. Rack diagrams are designed to give you a physical view as if you were standing in front of that rack in the data center. It's very common to have restricted access to the data center, so a documentation like this can be used for individuals who may not have that level of access into the building. You can then use this documentation to tell someone to stand in front of the rack, look about 3/4 of the way up on unit 14, and you'll see the power strip. You can even use this documentation to locate the exact rack in the data center. You might have on the documentation that this is in row 3 of the data center, and this is rack W. This gives us a way to provide detailed documentation for someone who may be standing in front of the rack when we may not be in the same building. So instead of telling someone to reboot a server that's in this rack, we could specifically say, go to unit 15 in this rack and reboot that individual server. Another useful physical piece of documentation is the cable map for your office. This will allow you to see a view of the office and exactly where the wires are installed in that facility. You'll often see one of these diagrams in the IDF or MDF that's usually on the wall so that you can understand where these wires are going when they leave that closet. This will show you where the physical wires are running either under the floor or above the ceiling, and you can see that each drop for each one of these is numbered. This allows you to correlate the network drops out at each individual desk with the network drops that are connected to the patch panels inside of the wiring closet. These are not just useful during the installation process, but they're also useful when troubleshooting. You can track back exactly where a wire was run inside of the building and be able to correlate that back with problems that you might be having with that particular network drop. You can also create network diagrams that combine layer 1, layer 2, and layer 3 views of the network. Layer 1 would be the physical layer, layer 2 would be the data link layer, and layer 3 would be your network layer. Here's an example of a network diagram that includes a number of switches, routers, and end stations, and we have labels here for layer 1, layer 2, and layer 3. We can start with the layer 1 connection, which shows the physical interfaces for the switches and the routers where all of these wires are connecting and providing this connectivity. We can overlay on top of that a layer 2 perspective, which now includes MAC addresses for all of these different components. And if you wanted to include IP addresses, we can overlay the layer 3 addresses so that you know exactly what IP address is associated with which MAC address, which is also associated with each physical address. Another important part of documentation is a need to track your assets. This means that we need to put tags or labels on every asset that we're bringing into the organization. This would be laptops, desktops, routers, firewalls, switches, and anything else that we're buying and installing into our network. Once we have all of these devices tagged, we can use that tag when we're referring back to a trouble ticket or some type of problem. For example, we could say that a router in the data center that's labeled with number 42 is the one that's causing this particular problem. We can also use these tags for financial purposes. We may need to track these devices over time to be able to track their depreciation, or you may need to reference the asset tag to know when the device is purchased, which would also tell you if that device was currently still under warranty. These asset tags are usually very visible so that you can find them when you're on the phone with someone in the support team. There might be a barcode or RFID associated with this, and there might be additional information if a third party runs across this device. They'll know exactly who owns that particular piece of equipment. The asset tag that's connected to the device, the components within that device, and then the user who is using that particular device may all be combined within one single asset database. This becomes a centralized database that can be used by the asset support team, by accounting, by folks that are in the finance department, and anyone else who may need access to this data. If we need to know the physical location of a device, we can look at our asset database and see what user has been assigned to this particular component. If we then know the user's location, then we also know the location of this particular device. As we've also mentioned, we may want to use this also for warranty tracking to be able to understand when a device was purchased and what the status is of that particular warranty. And if we're tracking the number of devices, we can also track the software that's running on those devices. This can be very useful if we need to determine how many licenses we need to purchase for our organization. We can determine very quickly how many of those units we own by referencing back our asset database. Another important piece of documentation relates to the ongoing use of IP addresses in our organization. We would commonly track these by using an IP address management or IPAM solution. This is something that can provide us with a way to plan, track, and configure the DHCP and IP address schemes that we are using throughout our company. Using IP address management, we can document what users may be using what IP addresses. Since we often use dynamic IP addressing, it's useful to be able to map a user with a specific IP address during a particular date and time. This might also give us the ability to identify any problems or shortages that we might have with our IP addressing configurations. And based on this information, we might need to modify IP address ranges or add additional IP addresses to our DHCP infrastructure. This gives us a way to manage all of our IPv4 and IPv6 addressing throughout our organization, all from one central console. Here's a console from an IP address manager showing different subnet details, statistics about the IP addresses that we're currently using, changelog entries, warning and error logs, and other details that can help us manage our IP address configuration. If you're working with a service provider, and most organizations are, you'll need some way to verify that you're getting the proper level of service. This is often done contractually with a service level agreement, or SLA. This defines the minimum level of service required for this contract that you have with this third-party organization. For example, if you're contracting with a wide area network provider or an internet provider, you may have an expectation that you'll be up and running 99.99% of the time. And you might want to have that level of service documented as part of this SLA. You can use this for any type of service level. For example, you might have an SLA that your organization will have no more than 4 hours of an unscheduled downtime. This means that your service provider will need to have something in place to be able to bring you up and running if you happen to have an outage. They might have a process for quickly dispatching a technician, or they might have equipment that they keep on your location that you can pull out of a box, put it in the rack, and get up and running as quickly as possible. As we're increasing the amount of access points and other wireless infrastructure in our organizations, we need some type of documentation to understand the impact of all of these different wireless components. For that, we will create a site survey. This would allow us to identify all of the access points that we might be using, even if they're access points that we may not be in direct control of. We can at least see the frequencies that are in use and be able to document those as part of the site survey. Once we understand all the frequencies in use, we can then document those and configure our systems to have the minimum level of interference for all of our access points. If you're in a building with a lot of different companies, or you happen to be in a large campus where there are many different buildings owned by different organizations, you may want to perform these site surveys very often to understand exactly what the wireless infrastructure may look like. One common way to document this is with a heat map. You can walk around and use a mobile device to be able to document how the wireless signal may be propagating depending on where you may be standing inside of your building. One of the challenges we have when installing new equipment into our data centers and our networks is that eventually this hardware and software will be outdated. We refer to this as end of life, or EOL. This is when the manufacturer of that piece of equipment decides they are no longer going to support that particular product. They may continue to provide security patches and updates, but they are no longer going to provide new versions of software or enhance the features associated with that product. And eventually, the manufacturer of this equipment may decide to no longer produce any type of security updates. When there are no type of updates coming from a product, we refer to that as end of support, or EOS. You won't receive any patches, any updates, any new features, or anything associated with that particular product. When a product moves into end of life, we can put together a plan and a budget for replacing that product over a period of time. But when a product hits end of support, this becomes a significant security concern, especially since we know that we will never receive another security update for that product. These ongoing patches and bug fixes can be very important for maintaining the uptime and availability of these devices, especially when these updates are associated with stability fixes. But these might also be fixes that close security holes, which may be just as important as maintaining the uptime of the device. We often see this with operating systems, where we may receive a service pack every quarter, and we may have to install a large number of updates to these systems when we first install the OS. Many organizations provide monthly updates on a recurring schedule. This means we know exactly when the latest updates are going to arrive, and we can set up our plans for deployment around those update timeframes. And occasionally, a manufacturer will introduce an update outside of the scope of that normal monthly update. This is often associated with a security concern, especially when a 0-day or some other type of significant security event occurs. It's not unusual to see updates to operating systems occur constantly across many aspects of that operating system. For example, we can have updates for Windows, Linux, our iOS and Android devices, and anything else that might be running an OS. It's very common to see these monthly updates occur for the operating systems. These might have bug fixes and security patches, but we might also be making changes to the operating system ourselves. We might be modifying user accounts and changing the way that users interact with the operating system. For example, we might increase the minimum password lengths, we might change the complexity of the passwords required for the operating systems, or we might change the way that users are able to access the operating systems, and we might deploy those updates to the operating systems on demand. We might also change the configurations of the built-in firewalls on these devices. These operating systems provide us with a way to limit where a user may visit by IP address or URL, or there might be changes that enhance the security features on that device. And there are constant changes to the embedded anti-malware and antivirus that's included with many of these operating systems. If we're managing a purpose-built appliance or a purpose-built piece of hardware, then we don't usually have access to the operating system that's on that device. And often these devices have their own operating system and configurations. We refer to this software that's running this piece of hardware as the firmware of that device. So if you're working with printers, cable modems, or other devices that have their own embedded operating system, you might be required to update that firmware occasionally to close security holes. This update may be done over the network, or it may require you to visit the device and physically connect to the device to perform the update. We know that we can't use this hardware unless the software in this device is working properly. So it's a good idea to have a plan for upgrading this that would include a way to fall back to a previous version if that newer version runs into a problem. It's often a good idea to save those firmware binaries in a safe place so that later on down the road you wanted to go back to a previous version, you would have access to all of that code. One of the challenges with managing firmware in your printers, your modems, and other devices is that these companies are very good at manufacturing hardware, but they may not be as good at maintaining the firmware that runs in those devices. An example of this would be the Train ComfortLink 2 thermostats, where you could control the temperature on the thermostat from your phone. There were 3 vulnerabilities presented to Train in April of 2014, but we didn't receive updates to the firmware until April 2015, and it took until January of 2016 to be able to get the final update for that device. It would be up to the security team of your organization to determine if that device should remain on the network or if you should find other alternatives instead of that thermostat. Another important aspect of lifecycle management is what you do with the device when you don't need it anymore. This would be the decommissioning process, and it's the way that you dispose of an asset once you no longer need to use it. We see this often with desktops, laptops, mobile devices, and anything else that becomes outdated and is no longer supported by the manufacturer. But there's data on that device that we want to be sure doesn't get into the hands of someone else. We need some way to sanitize the media or simply destroy the device to protect all of that data. This might also involve legal issues, especially if there's certain types of data that your organization is not allowed to destroy. So you may end up storing this equipment off-site or in a secure location until such time that it's able to be destroyed or disposed of properly. And what you do not want to do is simply dispose of this in your normal trash. Eventually someone will come across that equipment and they will either get access to the data or they'll sell that equipment to someone else who will then get access to the data. Although we often want to recycle this hardware, we want to be sure we do it in a way that protects the confidentiality of the data contained on all of these devices. An ongoing part of lifecycle management is change management. That's because we are constantly making changes in our computing environments. We're upgrading software on a switch, we're making changes to a firewall configuration, we're modifying a router table, or making some other modification to software or configurations. This needs to be a managed process and something that we can track, monitor, and be able to modify if we run into a problem. Most organizations will have a very clearly defined change management process. This would include how often you're able to make changes, the window that you have to be able to make those changes in an environment, the process itself for installing those changes in your environment, and then finally, a process for rolling back if you run into problems. And if your organization does not have a formal change management process, this might be difficult to implement. You need to make sure that everyone understands the importance of having a centralized change management process and that everyone follows that process before making any modifications to any device. Another important aspect of lifecycle management is how we handle ongoing service requests. This is often done through a help desk. They'll receive a phone call, they'll input a ticket into a centralized process tracking system. Those tickets will be triaged and provided to someone who can resolve the problem, and then they will close the ticket and move to the next one in the list. Almost every organization has a process tracking system, and although there are many different types of software to provide this function, they're all very similar in how they operate. Change is inevitable, and we need to have some type of process on our network to be able to manage all of these changes. There might be updates to operating systems. We may have to patch a series of devices. There might be updates to applications that we need to roll out. And of course, we have network devices, firewall configurations, new applications that need to be installed, and many other changes that will occur on our network. Instead of simply making a change without any processes or thoughts to what may occur in the future, we need to have a formal process for managing all of these configurations. We need to know when these changes are going to occur. We need to be able to plan for those changes, and we need to inform everyone that the change is going to take place. This documentation becomes very important if this system needs to be rebuilt, especially if there's some type of disaster and you're required to get that system back up and running as quickly as possible. Having some type of documentation that leads you from the installation of that software through all of the changes that you made will be extremely important in getting that system back up and running. When we first install a switch, a router, a firewall, and we make our initial configurations and get everything working perfectly, we now have a production configuration. This is the configuration that everyone will use when we roll out a new router. This is the configuration that will be the standard for that production system. When we install a new firewall, we have a standard production configuration for that firewall. This is not just individual configurations inside the device, but it covers all aspects of changes to that device, including all the hardware and firmware versions, any device driver updates that need to be made, and any updates to the software, especially since there are certain versions of the software that might work better or worse than other versions. This is not something that we would usually install into production to see how it runs. We would usually do extensive testing behind the scenes, make changes to all of these aspects of the system, and then deploy that final configuration into a production environment. Of course, not every possible scenario can be tested in our lab, so we need to have a plan if something was to happen in production to be able to revert that back to a previous configuration. In these situations where something does not go as designed, we need to have some type of backup that we can revert to. This applies to our firewalls, our switches, our routers, our operating systems, and anything else we might be making a change to. The standard operating procedure is commonly to make a backup of that system before making any type of change. Once you make the change, you can then decide whether that's something you want to keep in production, but if there's a problem, you may need to revert back to that previous backup. Sometimes this can be accomplished by simply copying the files that will be updated during that particular change. It might be a single configuration file, but now we have a copy of that file prior to those changes taking place, and we can simply copy that file back if there's any problems. If this is a virtual machine, this process can be relatively easy. You can click a button to create a snapshot of that VM that saves everything, the files, the configuration, and everything else associated with that VM at that point in time. If you run into a problem when you're making a change to the VM, you can then easily revert back to that date and time of the snapshot. This is also useful if later on you decide you would like to revert back to the previous configuration. You now have a backup that's stored either as a snapshot or as separate files that you can then revert to if you run into future problems. When we're deploying a new application, it's usually often more than a single server and a single executable. There are usually many different components that allow that application instance to operate. This might include configurations on the user's workstations, changes to the firewall, and of course the application server itself. To truly understand the scope of this application, we need to document every aspect of that application installation. This allows us to create a golden configuration that certifies that this application will work properly if all of these configurations are in place. We can also use that golden configuration as a way to verify that we are using the proper software and the correct configurations. We can create integrity checks that will compare the configuration running in production with the configuration on our baseline or golden config. If we find there are changes between those two environments, we can make changes either to the production environment to match the golden config, or we can update our baseline configuration so that it matches the new configuration in our production environment. Once we make those changes, we now have a new version of our baseline configuration, and we can use that as our integrity check going forward. As a network administrator, you will install switches, routers, servers, firewalls, and many other pieces of equipment into your infrastructure. Once you install that equipment, how do you ensure that it's running optimally and that there are no errors or problems that you need to address? One of the ways to do that is by querying this device through a protocol known as SNMP. This is the Simple Network Management Protocol, and it is designed to provide a management interface to these devices over a standard set of protocols, regardless of who happens to manufacture that device. Usually the network team will have a central network management console, and that management console will query devices via SNMP and ask information that it would like to receive. For example, it would request from a switch how many bytes have gone into a particular interface, and that device will respond back with a particular value, and that information is stored in the management station. The query that is being made to this device is querying a number of different parameters that are stored in what is known as a MIB. This is a management information base or central database of data that is stored on that remote device. SNMP queries specific values in that database by referring to an object identifier. Sometimes you'll hear this referred to as an OID or an OID. All of this polling occurs over UDP port 161 and allows us to access any of the devices on our network and gather information about how those devices are performing. When configuring SNMP on your network management station, it may ask which version of SNMP that device is using. There are usually 3 different versions you can choose from. The first is the original version, or SNMP version 1. This provided a way to query those structured tables that are stored within the management information base on this device, but it sent all of that information across the network in the clear. There was no encryption associated with any of the transmission using SNMP version 1. A newer version of SNMP was released that we named SNMP version 2. You'll sometimes hear this referred to as SNMP version 2C. This is an improvement to SNMP version 1 because it's able to query large chunks of data and have a more efficient communication to that device. But that entire communication remained non-encrypted or in the clear, so anybody tapping that connection would be able to see the entire communication. The latest version of SNMP is SNMP version 3. This provides encryption and a number of different cryptographic capabilities such as message integrity and authentication. When we are performing a query to a device using SNMP, we need to refer to a specific variable that we would like to pull back to our management station. That individual variable is called an object identifier, or an OID. That object identifier is a series of numbers. In fact, here's an OID 1.3.6.1.2.1.11.28.0. Each one of those numbers is associated with a particular set of values. For example, the 1 is ISO, 3 is org, 6 is DoD, 1 is internet, 2 is management, and so on. And you can go all the way down this line until you can see that we're looking for SNMP out get responses, and that would be the number 28 at the end of that OID. This is how we're able to have hundreds or even thousands of different variables inside of that management information base, and we can query each of those variables individually by referring to their OID. Sometimes these object identifiers are very standardized across devices. One of these standards is the MIB2 standard. It's referred to here as the SNMP v2-MIB. That MIB2 standard is a set of OIDs that are identical across multiple devices. But sometimes a manufacturer has unique variables that are specific to that device. And in that case, the manufacturer will create their own OID, and so you'll need to refer back to the manufacturer's documentation to determine what OIDs are associated with what values within that MIB. Sometimes the manufacturer will provide a file that documents the MIB, and you can add that file to your network management station. At that point, you can retrieve those OIDs from that device and know exactly what that OID is associated with. One of the ways that you can query a device for SNMP information is to use a MIB logger. This is software that will cycle through every possible MIB value and pull down everything associated with the MIB inside of an individual device. This is a MIB logger on my Mac OS device called MIB Browser, and you can see that I have it directed to a host at 10.1.10.64. It's using port 161, and I've configured this MIB logger to use version 2C of SNMP. The default community string on this device is public, and my root OID is 1.3.6.1. And when I click the fetch button, it begins gathering information about every possible MIB value that could be contained on that device, and when it finds a match, it adds it to the list. For example, it found a number of SNMP v2 MIB values, and you can see the list of those here. In fact, it even pulled back a system ID information, some contact information with my email. It even shows me the name of this system and how I can then correlate that back to a specific physical device. If we scroll down a bit in this list, we can even find individual variables as part of this MIB and see the individual values associated with each one of those. For example, SNMP in get request has a total number of 4, and SNMP in get next has a value of 1,540. If you start collecting that information over time, you can begin to build out very large visualizations of how the network may be performing. For example, this is a graph that has been created through a series of SNMP queries that take place on a standard basis. So you can see that going for an entire day, you can start to map out information such as response time values, any type of errors, or anything else that might be contained within that MIB. This implementation of SNMP assumes that your network management station will be querying all of your SNMP enabled devices on your network at regular intervals. It would be common, for example, for a management station to query every device on the network every minute, every 5 minutes, whatever interval makes sense for your management station. But if there's a problem on that device, you may not know the problem has occurred until the next time you perform that poll. For that reason, you may want to configure a different feature of SNMP referred to as an SNMP trap. You can think of this as a proactive alarm that is sent from the device to the management station without the management station needing to pull that device first. These SNMP traps use a different port number. They use UDP 162. For example, you could configure a switch or a router to look for a certain number of CRC errors to occur. And if you get a large number of errors, for example, it increases by 5, that device will proactively send a trap message back to your network management station. As soon as that trap is received by the network management station, it can then alert other people on the network of the problem or start running scripts to help resolve whatever issue that might be. In the MIB walker that we were using earlier, there was a value that we were adding to that MIB walker to be able to gain access to that system. That value is referred to as a community string. You can think of this as a simple password that allows you access to the SNMP data on that device. You can usually set up multiple community strings within a device, so it's not unusual to have a read-only string such as public. There might be a read-write string such as private. There might be a separate string that you would use for traps. These community strings are relatively simplistic, and they're only used for SNMP version 1 and SNMP version 2 or version 2C. There are other ways to authenticate using newer versions of SNMP, and in SNMP version 3, we use a username and password that is sent across the network as a password hash. This is a much more secure way to authenticate. If you're running SNMP in your environment, it's probably a good idea to use SNMP to have the most secure type of monitoring available. On your network, you're probably using routers, switches, firewalls, and many other network infrastructure devices, and all of these devices are running 365 days a year, 7 days a week, 24 hours in every single day. We'll need to monitor these devices to make sure that they remain up and running, and we may want to query those devices to determine what type of load they're seeing, perhaps log file information, and other details from each individual device. This allows us to see if people are able to authenticate properly to the device, if there are any security concerns, or how much utilization may be used in CPU or network. Many times the network administration team will have a central console, and that console will roll up all of this different information from these many different sources, put everything on one single screen for analysis. One of these data points gathered by this network management station could come from a service known as NetFlow. NetFlow is a summary of statistics based on the flows of traffic that are traversing the network. NetFlow has a standard way to collect this information from these devices, and there are many different NetFlow products available from many different manufacturers. NetFlow usually starts with a probe that you would put onto your network. This probe may be sitting in the middle of a connection using a physical tap, or maybe using a switched port analyzer interface on a switch to be able to gather that information. Raw packets are being sent to this NetFlow probe, and that NetFlow probe is compiling statistics based on all of the packets going across your network. The summary of all of that information is then sent down to a single NetFlow collector. This means you don't have to go to separate NetFlow probes to be able to gather all of this detail. You go to the single collector, and you can create all of your reports from that one central place. The collector is not only keeping a database of all of this information over time, but often the collector will also include a report generator. This might allow real-time reports and summary views on your console, or you may be able to configure long-term reports to be generated every day. This is a NetFlow console, and the current screen is showing a NetFlow traffic analyzer summary. You can see that it contains top 10 conversations, which are ingress and egress data for all of these devices. This is over the last hour. You can also see a top 10 endpoints on your network. This is listed by IP address or the name of the device. Here are the sources of that NetFlow data, and you also have traffic analyzer events that are coming from those NetFlow devices. NetFlow can also summarize information by port number so that you can see how much application traffic is traversing the network. These are the top 5 applications on this network. Looks like SSL is the largest amount of traffic on this network, and then there's SQL Server, other web traffic, NetFlow UDP traffic, and port 0 traffic. All of that NetFlow information is effectively metadata that was created based on the packets going across the network. But you could also view the raw packets themselves using a protocol analyzer. This allows you to see the exact bits and bytes sent across the network from one device to another. Protocol analyzers can collect frames from a wired network, a wireless network, and it can present this information in a form that is easy to read. Instead of viewing all of the hexadecimal data, you can view a summary of these packets going back and forth, and then drill down into the details associated with each packet. If you're trying to find unknown traffic or you're working to troubleshoot a slow application, you can view all of the conversations taking place over the network using this view inside of your protocol analyzer. And in some organizations, this data is also collected and stored over a long time frame. This usually includes a very large array of storage drives, and every packet from the network is being stored on those drives for later analysis. Once we begin gathering all of this data from these many different data sources, we can start building a picture of what a normal day on the network might look like. We refer to this as a network performance baseline, and this can be a very useful set of statistics, especially when we begin troubleshooting the network. If you're trying to determine if a large amount of utilization on the network is normal, you simply look at your baseline to know what the normal amount of utilization would be during a standard workday. You can then compare that to the value you're seeing now, and then determine if that's better or worse than what would normally occur on the network. We can also drill down into these baselines to see what normal performance might be for an individual device, for example. So you're able to get a very detailed view across many different devices on your network by simply compiling this data into a central baseline. If your organization is using a management console or a SIM, this would be a security and information event manager, then you may already be collecting data files and other useful statistics that you can use to build out a performance baseline. This management console or SIM console may be able to look through the data and identify an alert when certain anomalies occur, or it may be able to present normal baselines for an extended period of time so that you can see when things happen to change over a normal workday. That management console or SIM console is collecting log files from many different devices. There's log files inside of your switches, your routers, your firewalls, your servers, practically any other device you would connect to the network. There is a standard way to transfer log files from all of these devices, even though each one of those devices may be manufactured by a different company. This standard for transferring log files is known as syslog. You'll usually see the syslog configuration inside of your switch or router, and you'll tell the switch or router where to send all of its log files using that standard syslog transfer. This is commonly sent to a SIM, which is a security information and event manager, and usually we are storing that on a large drive array inside of that SIM. That SIM is identifying what device sent that log file. It'll identify what's known as a facility code, which is the program that originally created that log file, and it will also include a severity level for that line within the log file. So you should look at the configurations in your enterprise switches, routers, and other devices to see what options you might have for sending that syslog information to your SIM. If you were to log into that security information and event manager, you would find a large amount of information available to you. It's not just page after page of this log information, it's also all of that information rolled up into reports that you can then use to make decisions. For example, there might be a dashboard on the SIM that gives you a real-time status of information about your network. You can see alerts and alarms if there happens to be a large number of failed authentications, or if a device happens to go offline, you may see that in the dashboard of your SIM. Most SIMs also have very advanced reporting capabilities, so you may be able to go back in time, start comparing and contrasting different statistics across multiple devices, all using that large database that you've compiled within the SIM. So you might be able to track application usage when it starts on a server. You can track that traffic as it traverses a switch, watch that traffic as it goes through a firewall, and then analyze how much utilization that's taking on your internet. And since you've now stored all of this log file information over an extended period of time, you might be able to use it for forensics. This will allow you to go back in time and track when someone may have authenticated to the network and then which services they may have used when they were logged in. This log file information can be sent from nearly any device. This could be a NetFlow collector, it might be a server that has syslog capabilities, or it might be a switch, a router, or a firewall that's currently running in your infrastructure. One of the things you may find when you first turn on a SIM and start sending it syslog data is that it will be receiving a large amount of information. Some of this information might be useful for that individual device, but it may not be necessary to store that for a long period of time within your SIM. So you may want to change some sensitivity settings on the SIM to be able to perhaps only capture warning or urgent information and perhaps not store informational details within the SIM database. Here's an example of an ad hoc data query made on a SIM. You can see that we're doing a query here for anything that starts with fail, so this might be failure or failed, or the word fail itself, and any records that include the word password. So we're looking for situations where password authentication has failed or is not completed successfully. And you can see the series of statistics that are gathered. This creates a single chart across the top, and then we can view individual event records. For example, these appear to be event records from Windows Server, where there's a login failure. It says unknown username or bad password. The username used for that authentication was Haxor. You can see it's Acme Text domain, and it has a login type and other lines associated with that record. We can now track this over a long period of time to see, is this normal, or have there been instances during the day when there's been a large number of failed authentications? This might be able to identify times during the day when there will be a brute force attack or a password spraying attack, and then we can use additional security tools to track that closer or to prevent that event from occurring again. If you've ever had to administer a switch, a router, a firewall, or any of these other infrastructure devices, you know that you would normally SSH into the device, perform a series of commands at the command prompt, and then disconnect. And if you need to make that change again on a different switch or router, you will need to SSH to that additional router and make those changes again. This is something that can be relatively tedious and almost impossible to manage in large environments where you may have hundreds or even thousands of these devices. For that reason, we need some way to automate this process, and we can do that by using API integration. This allows us to have a central management station communicate directly to a switch, a router, a firewall, or some other device using an application programming interface, or API. This allows us to create applications, scripts, and other programs that can communicate directly to that device without using the SSH console or communicating to that device over a web console. This means that we can effectively communicate with the native language of that device. So we can send commands, make configuration changes, or query information on that device without having to interactively log in or sit at an SSH prompt and look for that information. And if you're managing those hundreds or thousands of devices, you can make those changes automatically with one click of the button using this application programming interface. A lot of the monitoring and features we discussed in this video needed the raw packets from the network to be able to gather those statistics. One of the ways to gather those packets is using port mirroring. This allows you to use an existing switch and redirect traffic from one port on the switch to a packet gathering device that you have connected on a different port on that switch. We also use port mirroring for security features such as an IDS or IPS, and we may also use this for performance monitoring. For example, we might connect a NetFlow collector to one of these port mirrors. Some switches even support the ability to mirror traffic from one switch to another, so we could have a switch in the data center with our monitoring systems and be able to gather packets from a network switch that may be in another building or another location. The port mirror may also be referred to as a switched port analyzer or SPAN, or we may have a physical network tap that's connected somewhere between two devices. If we are using a switch, we're simply taking a copy of this data and sending that copy to a third-party device such as an IPS or NetFlow collector. So when a user is communicating to a server, they first are communicating through a switch. So a copy of that data is sent to our IPS, and the original copy of that data is sent on to the server. We can do this for single interfaces or multiple interfaces or VLANs on the same switch so that we're able to see all of the traffic that is available on that switch. When you sit down to troubleshoot a network issue, you're starting with no information. So we need to start gathering more details using a number of different techniques. These would commonly be things like LLDP, which is a link layer discovery protocol on switches. There's also CDP, which is Cisco's version of this called the Cisco Discovery Protocol. You might also use scanners that are able to perform ping scans or port scans of the network to identify devices that may be up and running. There may also be commercial network scanners in place, or you might use simple network management protocol. Some organizations will run these types of scans every night on their network to gain an understanding of exactly what devices may be installed. Or this may be a scan that we simply do anytime we're trying to do some troubleshooting, and it's not something that commonly runs every day. But if you do have a daily cycle of scans and information gathering, and you can perform reports on that information, you may be able to build an interesting view of exactly what type of traffic is on your network and what devices may be sending that traffic. We often refer to traffic analysis as a detailed frame-by-frame or packet-by-packet description of exactly the traffic that's flowing across the network. Often this is summarized into simplified views so that you don't have to sift through hundreds or even thousands of lines of frames just to understand what type of traffic went across the network. For example, if you were looking at a detailed firewall log, you would be able to see exactly how much traffic was sent across the network at which time frames. You would know which IP was the source of that traffic flow and what IP address was the destination. And you might also be able to gather additional details such as the port number that was used, the application in use, or exactly how many bytes were transferred between those two devices. And if you're collecting this information and storing it over a long period of time, you can use this for creating long-term reports or being able to go back in time and perform detailed forensics. Here's a view of this firewall log. You can see there are a number of different columns of information that are collected. One is the timestamp of the traffic flow. You can see in this view it starts at 7:49 and 38 seconds and goes down to 7:44 and 57 seconds. There's quite a number of traffic flows that have occurred on that network during that time frame. You can see the protocol in use, whether it was TCP or UDP, and you can see port numbers are also listed in this log. We have a client IP address and a server IP address, so we know exactly what two devices were communicating with each other. And if we have a DNS server, we may be able to take those IP addresses and convert them into host names. In this example, the host name is the same as the client IP address. This provides us with a wealth of information for every single flow of traffic going across the network. So if you were ever wondering if someone was able to see exactly what you were sending across the network, there may be ways to gather a great deal of that information using these firewall logs. If we're troubleshooting a problem, we may be interested in overall performance from that device. This might include network utilization statistics or an overview of any errors that may have occurred on that device. You can usually gather this type of information using SNMP, the Simple Network Management Protocol. Maybe you're gathering net flow statistics, you're doing protocol analysis and looking down at the frame level, or maybe there's a software agent running on that device and it's providing you with a summary of this performance information. Based on these statistics, we can begin to understand if our network is highly utilized, if we're seeing a large number of errors, and try to get an idea of where the problems may be occurring with that device. Sometimes the statistic that is most important is a device up or is a device down? We can find this information by looking at our availability monitoring. This provides us with green for up and red for down, and we can instantly see where a device may be active or where it may no longer be on the network. This could also be rolled into a set of alarms and alerts, so we can constantly monitor these devices, and if any one of them happens to turn red, we can instantly start sending email messages, opening up help desk tickets, and sending alarms and alerts to the people that can solve this problem. The view that we have here is a real-time view of the devices and whether they're up or whether they're down. But we could also collect this information over time, allowing us to build a report that shows overall performance and availability over an extended period. This is obviously a very simple metric. The device is either active or the device is not active. If you need additional details about the performance of the device, you may have to drill down deeper and gather net flow statistics or information via SNMP. All of the devices on our network have configuration files. These may be files that we can easily see and list on the screen, or they may be stored in different places on the switch, the router, or the firewall. Many of these devices also allow us to back up the configuration files and restore those configurations if we need to update or make any changes to the device. These configuration files might also be specific to a particular version that's running on that device. So if we have an older configuration file and a newer version of software running on that switch or router, we may not be able to load that older configuration file back onto that device. In those situations, we may need to downgrade that device back to that previous version just so we can now install that older configuration file back on that switch or that router. This means we not only need to collect our configuration files and store those for future reference, but we also need to keep our firmware or previous software versions just in case we need to go back to that previous config. If we have multiples of these devices, we can also compare and contrast the changes between those configuration files on all of those different devices. For example, you might have 10 identical web servers, and each of those web servers should have a very similar configuration. There may be a way to use the configuration files to be able to verify the configuration across all of those. Many organizations will also perform ongoing monitoring of those configuration files, and there will be an alert or an alarm if anyone makes any change to that configuration without prior approval. This is usually part of an overall management system that is integrated with the change control within your organization. So you may have software that's monitoring the configuration files and a larger process that is involved with changing and modifying those configuration files in a very standardized way. Most organizations will create a plan that they will follow if they happen to have an outage or a significant problem that could affect the overall goals of the organization. This is often referred to as the Disaster Recovery Plan, or the DRP, and it will cover every aspect and detail of how to handle these situations when they occur. And if you think of all of the different types of technologies involved in recovering from a disaster, it is many and varied. You have backups that you need to consider. There may be offsite data replication that might be involved in this disaster recovery. Perhaps you set up alternatives that are located in the cloud. So instead of having a server on site, we can create that same server in a cloud-based environment. Or maybe you've got a completely separate remote site and you move all of your operations to that fully operating remote location. There are also many third parties that can provide additional services for disaster recovery. For example, you can contract with a third party that will provide you with a location so that you can move your operations to this temporary facility. Or you may want to contract with recovery services that can come into your organization and manage the process of recovering from a disaster. There are many different metrics that can help us understand the scope and the breadth of an outage. One of these metrics is a recovery time objective, or an RTO. This is an amount of time, and we want this RTO to be as close to zero as possible. RTO is a measurement of how quickly we can get back up and running if an outage is to occur. So we need to define what a normal service level would be, and then we can calculate how long it will take to get to that particular service level. We refer to that gap in time as a recovery time objective. For example, we know that if our web server was to fail, that the normal recovery time objective for that web server becoming available again is approximately 1 hour. So 1 hour would be the RTO for that outage. Another useful measurement is an RPO. This is a recovery point objective. This is also measured as an amount of time. And again, we would like that RPO to be as close to zero as possible. RPO represents how much time we lost when that outage occurred. We have a certain amount of data that goes back in time that was not stored, it was not backed up, and when that outage occurs, we would lose all of that data. Generally, this is a value that you've already determined. You would make this determination based on what resources you have to recover this data and the types of backups that you may be doing throughout the day. And this RPO may be different depending on the type of business you're in. For example, if your organization handles banking transactions or you manage patient information, you want to be sure that you don't lose a lot of that data. So you may put methods in place to be sure that you are only losing a small amount of time when an outage occurs. This might be, for example, a very short time frame that would be less than an hour. But maybe your organization works with other types of data that don't require such a short RPO. For example, any updates to your website or updates to internal documents may only be backed up every hour or 2 hours. So there would be a longer RPO associated with that type of data. If we were to look at both of these values on a timeline, you can see that as time is going by, we have a certain data recovery point. Maybe this is where data is backed up, maybe we are replicating data to a different site, but we are making a copy of that data or storing that data in a way that we can recover later. Sometime after that point, we would have an outage, and the time that we have between that outage and the back in time period to that data recovery point would be the recovery point objective, or the RPO. So now we're focused on resolving this outage. We need to resolve the issue with the servers, deploy new servers in a different location, move the data center to a backup site, or do whatever we need to do to recover from this disaster. And then finally, when our services are back online, we can measure that time frame between the outage and the online time frame as a recovery time objective, or an RTO. When these issues occur, it's useful to know how long it's going to be to resolve this problem. And it might also be good to be able to predict when problems might occur. We can provide estimates for both of those values by using MTTR and MTBF. MTTR is the mean time to repair. That is, on average, how long it will take to resolve the issue associated with that particular problem. Maybe it's a router that's failed and we need to replace that router to get back up and running. The average time frame for replacing that router would be our mean time to repair. A better plan might be to use systems that are designed to stay up and running as long as possible. So we would need to put in equipment that would have a very long mean time between failures, or MTBF. The MTBF is generally based on a number of criteria, but it's presented as a single time frame. For example, if you purchase a firewall, that firewall's MTBF may be 20 years before you would expect that device to fail. So you can then make disaster recovery plans around that time frame. If you see that your firewall has an MTBF of 20 years, you might only need one additional backup unit instead of purchasing multiples, because you know that device is going to last, on average, a relatively long period of time. If we're dealing with a significant disaster, we may need to move out of our existing data center and into a temporary facility. But making that change is often not a simple process. There are a lot of different moving parts and things that have to happen to move your entire data center from one location to another. And then once you've moved to that other location, you then have to move everything back once you're up and running again. We refer to this moving of one location to another as site resiliency. One example of this site resiliency may be the process you go through to prepare that disaster recovery site. You need to make sure you have power, you may need to bring in additional hardware and have it staged prior to a disaster, and you may want to have data that's transferred over. Once that disaster occurs, you will have a process where you move from your primary location to this backup facility. You would then work from this backup facility until the problem is resolved at the main location. This might take an hour, it might take a day, or it could take months, depending on the problem that's occurred. Every disaster will be different, and we have to think about that time frame when we're preparing the alternate site. And of course, when we are ready to move back to the original data center, there is another process where we would take all of our assets and our data and move it back to the original location. If you're going to be using a separate disaster recovery site, there are a number of different ways to set up this particular facility. One is with a cold site. This is effectively an empty building. None of our equipment is in this building, and none of our data currently resides at this location. We need to grab backup tapes or equipment that has our data and move it to this location to be able to perform disaster recovery. We also don't have any people at this
All right,
location,
everybody.
so we may need to transport people from one location
Elaine,
to another so
I
that
will
they
have
can
your
work at this
Network
physical site.
Plus voucher
This obviously
in the
means we have a lot
morning.
of work to do if we call it disaster,
been
but it also
requested,
means
so
that this
I'm gonna
is
get it
a
for you.
relatively inexpensive place to use
Good
as a
review
backup
today.
location.
Everybody's catching up
If
on
you
their
needed to have a
stuff.
disaster
Good,
site
good,
where
good.
you could very
Just wanna
easily
walk
move
into
in
Wednesday,
and be up and running,
take some
you may want to
exams,
consider a hot
graduate.
site. A hot site is an
Take
exact
exams,
replica of your data center,
graduate.
or as exact as you
I don't
can
want
make
y'all to
it
do
for
no work
something
on
that's a
Wednesday.
disaster recovery
Yeah.
location. This means
No.
it has the same
So be a
hardware
relaxed
that you
day,
are currently
right?
using in
Not
your
relaxed like
data
that, but you
center.
get what I'm saying.
And it's very
No
common
stress,
when
just
you're
finish
purchasing
off
new
everything.
equipment for a data center.
But
that you
everybody's
also
doing good.
purchase
Hours are where they're
additional units
supposed to
for
be
your
for
hot
everybody
site.
right now.
And of course, not only do we need
Let's keep
equipment
the
at this
momentum
hot site,
for
we
2
also
more
need our
days.
applications and our data.
You're right at
It's
the
very
end.
common to have
Right at the end.
replication systems or ongoing backups.
Anything for me
so
today.
that the data at your hot site is as close to the data that you're running at your
All right,
primary
if I crack a
location.
cold one in
And by
class,
putting all of
I
this in
get
place at the hot site, we
do
can
it
then
all
move
over again.
relatively
Nah,
quickly
they'll just
from
drop you.
our primary data center to this disaster recovery location. And since we don't have to install
Look,
any
nope,
hardware,
nope.
install any applications, or recover data from backups,
But,
we'll be up and running
if it's
relatively
non-alcoholic, you're fine.
a warm site would be somewhere in the middle between.
But if you
a
need
cold
me, reach
site
out to
and
me. I'll
a
check
hot
my
site.
text at least once
This is
before I
a
go to
site
bed
that might
tonight,
have some
or my
level of
email.
infrastructure. They
And
might
y'all have a
power
great
and
night.
racks
Carry
and
out the
cases,
order
might
and
even have additional hardware that you could
skibby
use.
hip.
And so all you would need to do is show up with your data, recover from your backup tapes, and you would be up and running. There's different levels of service that you can use for a warm site, so you can decide just how much hardware or how much data you would like to have staged at that location. It's always a good idea to practice and run through tests so you know exactly what to do should a disaster occur. But that process